Hello, and welcome to Dgraph Day. I'm your host, Zoe, and today we celebrate all things Dgraph. 5 years ago, Dgraph was little more than an idea. Since then, Dgraph has grown to become the #1 open source graph database with 1.6 million monthly downloads and has run over 100 billion queries. None of this would be possible without you, our amazing community. That's why we created Dgraph Day to celebrate and share what Dgraphers around the world are building with Dgraph. From cutting-edge innovation to unique use cases, our global community is using Dgraph in amazing ways. So this is our chance to step back and say, wow, you can do that? But this day not only covers Dgraph. We'll see talks that cover Badger and Ristretto too. Badger, for the uninitiated, is the powerful key value store that Dgraph uses under the hood. Ristretto is a Go caching system that we built to enable Dgraph to do its distributed things. Before we kick things off, some quick housekeeping. Dgraph has a code of conduct for events, which basically means we expect you to be kind and respect all of our speakers and each other in the chat. Speaking of chat, please chat with each other and speakers. Some of them will join in the live YouTube chat and are happy to answer any questions on the spot. We will also drop the link in our chat to our feedback opportunity. This is a survey that will let you tell us how we did today, plus could result in a cool surprise. If you want to take the conversation out of the chat, please feel free to tag us on social media. We're using hashtag #DgraphDay for everything, so tag us and share your experience. Oh, and the event will be recorded, so if you miss something or you don't get to hang out with us all day, you can check out the replay videos on our YouTube channel, which you should totally subscribe to. Okay, that's all the housekeeping. Now, let's get to the good stuff. There's a lot of excitement in the air right now because we've just released a new version of Dgraph. And to tell you more about it and some other cool news, our esteemed founder and CTO, Manish Jain.
Hi, everyone. I'm Manish Jain, the founder and CTO of Dgraph Labs, and I'm really excited to welcome all of you to the first ever Dgraph Day. I would also like to thank Dgraph's marketing team for helping put together this event and made it available via live stream to everybody around the world. So welcome. And before I go further, I would really like to thank the open source community that has made Dgraph the most popular open source graph database out there. This started off as a small project that I ran. I started back in 2015, and it has grown into this thing where we have hundreds of contributors around the world. We have built a company of 50 plus people, and we are seeing a huge traction around Dgraph. So I would really like to thank all of the open source community who has helped us by contributing to Dgraph, who have helped us by providing feedback, by running Dgraph, by helping test Dgraph system, by contributing to the documentation, everything that you guys have done over the last 5 years. I would really like to thank you because all of those efforts are what made this event possible today. Dgraph's journey in open source started in 2015, as I just mentioned, but Dgraph's real journey started back at Google in 2011. My own journey at Google started in 2006 as an intern, and I joined Google in 2007 as a full-time employee working on web search infrastructure. And for the first 3 years, I was helping build a real-time distributed one of the biggest real-time distributed systems at Google, which was building an incremental indexing system. So we could, from the time we see a web page to the time we serve it, we could really reduce the amount of time it takes. And so I learned a bunch about how do you work with big, large, real-time distributed systems. And Google then happened to acquire a company called MetaWeb, who brought Knowledge Graph to Google. And I started to look at Knowledge Graph to see how we could use it in web search. Now, this is before Google started answering queries. This is the times when Google was still only serving blue links for every query. And so we sort of like put together a team to be able to build Google's first graph indexing and serving system, and I happen to be one of the tech leads of that project. And the idea was that we had all of these fragmented backends like weather and events and movies and flights and so on and so forth, spread all over the company, run by different teams, just because they had different data models. So each data model ended up having its own backend, and the backend had to be ran and maintained and so on and so forth. So the idea was to be able to unite all of those different data models and backends into a single graph indexing and serving system. And the system had to be hit by a good chunk of web search queries. So it had to be performant, it had to be scalable, it should not have a single point of failure. And when you're hit by web search, you really like have to think about the latency requirements and the throughput requirements of the system. So we put together a system which was low latency, high throughput, and could do arbitrary depth joins, so could run arbitrary depth queries. So we can traverse the relationships between all of these different data models which existed, and be able to serve knowledge to the world. And so I learned a bunch about how you could build a sort of, web scale graph serving system, and that's the knowledge that sort of inspired Dgraph. Now, Dgraph is obviously inspired by all the work that we did while building the distributed graph serving system, but it is not just a graph serving system, because outside of Google, when we were building Dgraph, we decided to build a distributed graph database. So we took ideas from the graph serving system at Google, but then also married it with a lot of ideas that we took from another project at Google called Spanner, which is their geographically distributed SQL database. And we brought a lot of the good ideas from there, like distributed ACID transactions, synchronous replication, strict consistency guarantees, fault tolerance, and so on and so forth. So all of that stuff, which was pioneered at Google, we also took a lot of inspiration from there and brought that into Dgraph. And then finally, we just had a lot of research that we did ourselves in Dgraph Labs, because there was no one paper that we could follow to build this distributed graph database. A lot of this is very unique, and so we had to build up on the ideas that we had learned before, but then bring in new ideas to be able to build this really unique system, which can scale like a NoSQL database, and which can do the distributed transactions and consistency like Spanner, but then really execute these complex graph queries like no other system out there. And so if you look back at what we were trying to solve at Google, we had this big problem of the knowledge graph. Now let's look at what knowledge graph is. Knowledge graph has lots of knowledge, lots of data types, in fact, thousands of data types into a single system, into a single sort of like data store, if you will. We have thousands of data types, and each of these data types have hundreds of properties, and these properties are not always defined. They are sort of sparse. Sometimes they are defined and sometimes they are not. And so serving thousands of different data types with hundreds of sparse properties is not something that existing systems or existing databases in the market are well suited for, right? And so what happened was each of the backends that was designed to serve what they call one boxes. One boxes are sort of like knowledge, limited knowledge backends, if you will. So if you were to search for weather in San Francisco, you get shown the weather weather in San Francisco, which is actually not, I mean, there are obviously web pages below it, but at the top, what you see is the weather. You see the Fahrenheit or the Celsius right there, and that's a one box that gets triggered because the Google engine understands that you're looking for weather, and it routes it to the right one box to show you the information without having to click on a blue link. So what we had at Google was that we had lots of backends with different data models, each serving one kind of data model, and then the web search had to iterate over each of these backends to be able to serve the corresponding one box. But the problem was that one, it is fragmented, and so you have to maintain all of these different backends separately. And secondly, it's you cannot query across any of these data models because they are very different silos of information. So the kind of complex queries that lets you say something like, well, when I land in New York, recommend me an event to go to, that requires you to figure out the flight information, to figure out when you would land. Then it requires you to figure out the weather at that time. And then depending on whether it's raining or it's sunny, you can find the events which would be very well suited to that. And so in a single query, you are traversing three different essentially data models to be able to answer that query. And that kind of sort of ability to query that was just not available at the time. And so what we wanted to do was to build a single service system which could operate upon the relationships and be able to query these by traversing the relationships and so on and so forth, and infer unique, interesting data points. And that required us to build a graph serving system. Now, it might be tempting to say that you need a graph system if you have to serve knowledge graph. It makes sense, but this problem of data modeling is not limited to just knowledge graph. In fact, this problem of data modeling complexity is everywhere, and you see this echoed in different blog posts by different companies. I've been reading blog posts from Facebook and Twitter and Dropbox, Airbnb, LinkedIn. They all had to go build custom graph solutions. Not everybody is serving a knowledge graph. So why do they need that? The problem is that the existing solutions, which are non-graph based solutions, they are not very good if you were to introduce new data models which are related to existing data models, and be able to run queries with them at scale. Also, you have to modify your code to be able to deal with these introduction of new data models. So every time you introduce a new data model, you might have to change your app. You might have to migrate some data. You might have to re-architect how the schema is, and so on and so forth. And that is hard. That is hard, particularly at scale. And so to solve for data modeling complexity, a lot of companies want to use or end up using a graph solution. Now, if there was existing graph solution which would work really well, they would all go and use that. But that's not the case. The problem is that we don't have a really great graph solution in the market, or at least we didn't before Dgraph. we didn't really have a great graph solution in the market which could scale well. Right, and all of these companies needed something which could really scale to terabytes of data. That just did not really exist. The second problem was that a lot of these graph solutions in the market are not general purpose. They're designed for very specific graph problems, and the moment you venture out of those graph problems to do something as simple as searching on full text or doing regular expression queries or just matches of strings and regular things that you would expect to do in a typical SQL database, they just don't exist in the existing graph in the existing graph solutions. So you can't operate on a broader set of data problems. You imagine sort of a SQL database without indices, right? It would work. It would still be able to do something, but it would not be able to do a lot of things. And that would limit the how many use cases you could throw at that system, and that is a problem with that was a problem with the graph ecosystem. And the third problem that I saw with the ecosystem was just accessibility to modern developers. The languages used by graphs were just not mainstream. They were very research focused, and in fact, they were being used for doing very research focused analytics. And some of these things were just not legible for modern developers, which made graphs even more scary than they needed to be. And so these are the three big problems that I see, or I saw when I started Dgraph, is that they were not general purpose, they were not scalable, and they were not accessible. That's when I thought about building Dgraph. Right? And Dgraph is designed to solve all three of these problems. First, scalable. Dgraph is scalable to hundreds of servers and terabytes of data. This is something that we had to design for at Google, and that part of the design and the ideas from there, we were able to. They were the guiding light, the pole star for us when building Dgraph. So the D in Dgraph stands for distributed, and we always made it so that it's part of our open source offering. It was never an enterprise feature like you might see in other databases, which don't start off as being distributed databases. But Dgraph was distributed pretty much from version, I think 0.2 was it, which was introduced maybe a couple of months since version 0.1. So Dgraph was distributed from the get-go, and and that was the pillar for the pillar for us to build on. And second is Dgraph is a general purpose. We didn't limit Dgraph to just the graph feature set. We thought about what all would a user need to be able to build their app or their platform on Dgraph. What all stuff would they need? And so, we obviously did a lot of string-based indexing, which is sort of pretty crucial for a lot of apps. We did full text search early on. We did regular expressions a bit later, I think. We did term matching, equality indices, hash indices. All of them actually went in very early on in the system. We also did support geo queries, which are not yet supported by very popular databases either. But that's another hangover sort of from Google days, because we needed to be able to search across locations. And so we took Google's S2Cell indexing library and built geolocation search on Dgraph in very, very early days. We also supported date time, floats, and ints, and we even supported a very unique data type called password, which we hadn't seen anywhere else. But we felt like to be able to serve an app, you need to be able to store your user's username and password in the database in a very secure way. There are just too many hacks out there, and we felt like having a native way for people to store their passwords would just make things a bit more secure and make things a bit more accessible to developers. And finally, talking about accessibility, we realized that a lot of the graph languages were just not very readable. They're just not very accessible, and we were looking for a sort of like a modern language which could speak JSON and which could be easy to comprehend even to people who have never seen this before. And this was a time when GraphQL was introduced, and we felt like that's just the right language for us to build this database on. So pretty much in sort of October 2015, we were, if you go back and look at the commits of Dgraph, very much in like October or November 2015, we were already like introducing GraphQL into Dgraph. And if you guys might remember, GraphQL was a draft version of the GraphQL spec was put out by Facebook, I think in June 2015. So it was within like a few months that we sort of adopted GraphQL, and it's been a great journey with GraphQL. We ended up obviously forking it to make it to build Dgraph query language, which we were previously calling GraphQL plus minus. and to add a lot more power, a lot more sort of like database features into it. But then we also in 20, I think 18 or 19, we ended up supporting the official spec of GraphQL as well, because as you might know, GraphQL is everywhere. GraphQL is being used for by a lot of companies, and it's just really become very popular. Again, I think other people see the same benefits of GraphQL that we saw back in 2015, is that it is just so accessible. And so by building a graph system focused around developer accessibility, we come to Dgraph, which can have a GraphQL-like query language and then can return results back in JSON. Both of them are extremely popular standards. And so the end result of all of this thought and effort that we have put into Dgraph is that Dgraph has become really popular. In fact, it is the most popular open source graph database in the market. We have 16,000 GitHub stars. We have reached 10 million Docker pulls. In fact, I think just a couple of weeks ago, and this is up from 3.6 million Docker pulls 6 months ago. So there's a big jump that we have seen in just the last 6 months itself. Similarly, we are seeing 2 billion queries executed on Dgraph clusters across the world every week. And that's up from around 500,000 queries executed per week just 6 months ago. Overall, we have seen 24 billion queries executed in the last 6 months. And that just goes to show how popular Dgraph has become and how important Dgraph has become to users who are using it as part of their production setup, as part of their source of truth database, where their user traffic is directly hitting Dgraph instances. And Dgraph is fast. Dgraph is an interesting mix between a graph survey system and a graph database, and it shows in the benchmarks. In fact, we ran benchmarks against the leading competitive cloud-based graph system, and Dgraph is at least 2 times to 20 times faster than the competition. Not only that, Dgraph executes queries which the other system is unable to. For example, in this case, IC09, we just could not make it run in the other system. It kept on running out of memory. But in Dgraph, it's a very complex query, and we were able to run it. We are planning to write a blog post about what we have done here, but this is just to give you a taste of the benchmarks and how fast Dgraph is compared to the leading competition. Now, as I mentioned, Dgraph is meant to be easy for developers. It's meant to scale, and it's meant to be general purpose. But that's not the end of it. You still have to run Dgraph, and we have been sort of focused upon making Dgraph easier and easier to run, to make Dgraph system itself accessible to our users. And part of that, of what we have learned, is that most users don't actually want to run Dgraph themselves and maintain Dgraph. And it's not just a Dgraph. A lot of users just don't want to run a database. And you can see this by the success of like cloud-based databases in the market. It's just easier when users don't have to run their own databases. And that was our vision, to go build Dgraph Cloud. Dgraph Cloud is the only cloud graph platform in the market. It allows anyone to run not just Dgraph, but a full-fledged graph platform. They get access to the database, they get access to GraphQL APIs, they get access to caching, Lambda functions for business logic, authentication, all the things that you need to run in your backend. They are all accessible via Dgraph Cloud. And it's the only only graph platform in the market which is designed to replace the entire backend stack. And that's what's really exciting, because we wanted to build, when we were designing Dgraph Cloud, we didn't want to limit it to just the database part. Again, we went back to the first principles and thought about what is it that the developers would need from a backend. And it's not just a database. It's also caching. It's also the ability to run business logic, authentication, etc. And so we really sort of like put all of them into one package, into one umbrella of Dgraph Cloud. And so if you look at the history of Dgraph Cloud itself, we sort of launched it last year, but every new region in the cloud, we had to go manually sort of run some things and make it available, and would take 2 or 3 days. And honestly, I feel like you're not in the cloud until it is self-service. And so we have put a lot of work into building and rebuilding Dgraph Cloud, so it provides a very simple way for developers to get going with both Graph and GraphQL technology. And part of that is to allow the users to be able to spin up their backends wherever they are, the closest public cloud data center or region that they are in, and put it right next to their apps. And so the focus of the Dgraph Cloud has been to make that part of it, to be able to spin up Dgraph in regions all over the world, to be fully self-service. So the user should be able to go in, choose a region of their liking, and click on launch, and be able to spin up a backend in under 2 minutes. So far, the Dgraph Cloud has only been available in 5 AWS regions, and today we are launching Dgraph Cloud to be available in 11 more regions, making it a total of 16 AWS regions all over the world. And as I speak, the team is probably trying to launch it in 4 more AWS regions, so that it will be a total of 20 AWS regions. And that required a huge redesign on our part, and I'm really glad of what the team was able to achieve. So let's look at some of the regions that Dgraph Cloud is available in. So available in California, Ohio, Oregon, Virginia, Canada Central. In North America, in Europe, it's available in Frankfurt, Ireland, London, Paris, and Stockholm. And in Asia Pacific, it's available in Mumbai, Seoul, Singapore, Sydney, and Tokyo. And then finally, in South America, it's available in Sao Paulo. And not only are we available in the 16 AWS regions, you can also be up and running with the Dgraph backend in under 2 minutes. And that's a significant achievement for us, and required us to rework the entire cloud architecture. The entire Dgraph team has been working really hard over the past few months to make it possible and to launch it just before Dgraph Day. And I'm really proud of all the stuff that we have done to achieve this. In the next coming weeks, we'll extend its availability to GCP and Azure, so we can be present in the cloud and the region of our users' choice. In 2019, we decided to build the support for official GraphQL spec, which we launched in early 2020 under /GraphQL, a cloud experience focused solely on the GraphQL developers. But over the past year, we have learned that our GraphQL users really want the power and the expressiveness of DQL. And conversely, the DQL users really want to expose part of their data via GraphQL. And so we rethought how these two work together and built a unified interface by which our cloud users can see both DQL and GraphQL schemas. Our users no longer have to choose between a GraphQL or a DQL upfront, or which mode Dgraph should run in. Instead, they can use both DQL and GraphQL at the same time. And so with that, we decided that /GraphQL can just be called Dgraph Cloud. With Dgraph Cloud, our users can get the power of the graphs and the power of GraphQL all under the same Dgraph managed cluster. So whether they choose free, shared, or dedicated instances, all of these Dgraph clusters would support this unified approach to DQL and GraphQL. I'm really excited to show you all the stuff that we have built into the cloud. The team has been really hard at work over the past few months in unifying the DQL and the GraphQL interface in a way where it is intuitive and allows people to run both DQL and GraphQL queries at the same time. So let me go to my cloud instance here. And I'm running this site called the tweet site. It's something that me and a couple of other engineers put together to be able to find interesting tweets on and be able to showcase them. So the tweet site, as you can see, there's a bunch of data transfer, a bunch of queries. All of these metrics are now available to you on the dashboard, and we'll have more metrics coming in some time, including the ingress, egress, and so on and so forth. Now, one interesting thing that we did is that we used to have only the GraphQL schema here, but now we also have the DQL, which is the Dgraph schema here. And what we have done is that we have shown you very clearly how some of the GraphQL schema actually maps to the internal DQL schema. So if you look at this DQL schema, it's tweets.featured, and the reason is that is because we have type tweets, and we have featured as a date time in the GraphQL. And so the corresponding predicate mapping internally is flagged as being used by the GraphQL over here. So if you then need to run interesting DQL queries, you know exactly which predicate to use to run those queries. And if you try to modify it, you know that you can't modify it over here because it's only editable in the GraphQL schema. So you can go back to GraphQL schema, and let's say switch to UI mode, and I can go to featured, click on it, and I can change that to, let's say, array or lambda or month or whatever, right? So all of that is now possible. There's one more thing that we want to get to, is to make these auth rules in GraphQL a lot easier to comprehend, and also be editable via the UI, and that's something that we want to get to in the next quarter. One more thing that we have done is that, the GraphQL schema, you saw there's an auth over here, which is really advanced, but it's a bit not as intuitive. So we've added a cloud access control, which sits above the Dgraph database and more at the cloud level. And you can use that to decide what you want people to be able to read or not. So if I turn off my read permissions here, what will happen is the tweet side probably would stop running. It will not be able to run because we have disallowed anonymous access to the backend, and this adds one extra layer of security above whatever Dgraph already supports. And the great thing is that because it's a lot more simpler, it is a lot more intuitive for users. So we hope that by having this, our users are able to really fine tune the access to their backends, and just rest assured that security is something that their backends are secure, right? Now, what I'm going to do is I'm going to launch a new backend, and I hope to launch it in a interesting location. But before I do that, let me just talk about some of the different tiers that you see over here. The first one is the free instance. Then we have shared instance, and then we have dedicated instance. The naming is relatively sort of, I hope, easy to understand. But I'll start by explaining the free instance. Essentially, lets you run your Dgraph. Gives you like a Dgraph backend, but it limits you to 1 megabyte of data transfer per day. So if you want to go beyond that, you can switch to shared, which costs you like $10 a month, and comes with 5 gigabytes of data transfer for free included. And for any additional gigabyte of data transfer that happens, you get charged $2 a month. Both in starter and in shared, the storage is limited to 25 gigabytes of data, and if you sort of go beyond that, then you come to our dedicated instances. Now, the shared instances are essentially running multi-tenant Dgraph clusters. So we have namespaces and so on and so forth, and that's how it allows us to make it available to our users for such a cheap price, or for free in this case. With dedicated instances, you get your own dedicated hardware, and the great thing is you can also choose which regions you want to be you want to run your instances in. So for example, we have all this long list of instances that are available. So let me run an instance, let's say in Sydney, and I set it to HC. I'll make it, I'll run on Jaeger as well, so I can see how my queries are performing. I'll set it to organization founder team. In Jaeger, you can also set the sampling ratio. So I'll make it, set it like around, let's say, set it to 10%. Let's increase that to maybe 20%. Yep. I'll set a name for this is, and the subdomain would be, let's try that, and so I'll launch it. And so what's that going to do is it's going to spin up our Dgraph backend, and we'll get a notification once we have the backend up and running. Now, if it's a new region where nothing else is running before, it might take around 7 to 8 minutes to spin up. But for any of the existing regions where Dgraph already sort of exists, it will be done in under 2 minutes. And we're trying to bring down the 7 to 8 minute time window down to 2 minutes, because ultimately that's the goal that we have, is that wherever in the world that you might want, Dgraph can be up and running in under 2 minutes. All right, our cluster is up and running in Sydney, Australia. And I'll just show you quickly the schema. We haven't set any GraphQL schema. We do have some automatic internal Dgraph predicates exposed here. And we have by default anonymous access. Now I'm going to copy this and I'm going to run some queries. And the way I'll run these queries is to use Dgraph incremental. So we have this thing over here which sets the cloud. So I'll make Dgraph talk to the cloud interface. The address is, this is the address over here. So I'm going to copy this address. And the other thing is the JOT token. So our JOT token is, I'll do that by going to settings, clicking on API keys, create a new key. This is for increment tool. Create, copy it over here, and let's try running that. Oops, the address should be here. Okay, so now it's complaining about schema not defined counter.val. That's because our we haven't defined a schema, and in our settings we have set it to strict schema mode. Now we can make it flexible, but that's going to take a bit of time. So why don't I go to schema and just define it in DQL? So I'll add a new predicate, call it counter.val, make it int. It's already int, and just add it. And it's there. So now I think we should be able to run an update. There you go. So we were able to increment the counter.val by 1. If you run it again, we increment it another time. And I'm going to run it 1,000 times, just so that there's a steady stream of like queries and mutations happening here on this backend. And now we can actually start to use Jaeger. Now the next thing I want to do is to show you Jaeger, and for that I'm going to click on this thing and go to Jaeger. And for that, the one thing that I had to do in between was to go to API keys and create a new admin API key, and we call it Jaeger. Created that, copied it over, and so in the interface it asked me for it, and I put that in. So now you can see Dgraph alpha. And you can see server.query, and you can find the traces. It shows you all the queries that are happening. You can sort by the longest first to see which one took the longest, and you have all of this interesting information here, which kind of like gives you an insight into what's happening behind the scenes for what Dgraph is doing. And this is pretty amazing because this allows you to see where your bottlenecks might be, which part of the query could be slower, which part is really fast. And all of this is just directly integrated into Dgraph Cloud, so you don't have to do anything separately. We are already running Jaeger for you, and soon we plan to run other stuff as well, potentially like Grafana, so that it's easy for you to consume some of these metrics too. Now, there's one thing that we can do from here is to upgrade to high availability cluster, and that's a possibility as well. So essentially, and similarly, you have access control lists and so on and so forth. So essentially, what we have tried to do is we have tried to really put together all of the different options that would make it easier for you to spin up not just one instance of Dgraph, but an entire cluster, along with all the relevant services like Jaeger, which is what you need to run a proper backend. There's a lot of other interesting stuff that I haven't shown you in this demo here. There is API Explorer, which shows you which you can use to run GraphQL queries. There's a data visualizer, which we are sort of working to improve. It's going to become a lot more interesting in the next month or so, and allow you to like run a lot more interesting queries here. Lambda functions, which allow you to run your business logic. And Lambda functions actually work quite like the AWS Amazon Lambdas, where you can write your function in right now it's in JavaScript, but we plan to extend it to other languages too. So you can write your business logic in the Lambda functions, which Dgraph calls automatically for you. Rattle right now is an external integration, but we plan to integrate Rattle into Dgraph Cloud as well. Settings-wise, we have tried to simplify this quite a bunch. We will continue to work on it and make it as simple as possible to understand. And then finally, for our dedicated instances, in which case, let me go to Mate, they get access to some of this monitoring over here. Again, it's a bit bare bones right now, but we plan to improve it in the next coming months. So that concludes the demo for Dgraph Cloud interface. I'll jump back to talk about Dgraph Rocket release next. Apart from all the work that has gone into Dgraph Cloud, we have also been very busy building new features into Dgraph, and we recently launched Dgraph version 21.03 that we nicknamed Rocket. In Dgraph Rocket release, we have lots of new features that I will talk about now. First off, we have multi-tenancy. Multi-tenancy has been such a heavily asked for use feature for a while now. What multi-tenancy provides is the ability to use the same Dgraph cluster across tens or hundreds of thousands of tenants logically partitioned from each other. So they cannot accidentally or maliciously access each other's data. So it practically works as if you have tens of hundreds or thousands of Dgraph clusters, but instead of having to spend all of the resources running all of those clusters, you can just have all of these tenants in the same Dgraph cluster. And that's been such an asked about feature for us, and we had it on the roadmap last year as well, but we couldn't get to it. And this year, the team really put together a lot of effort to make it to build it, to test it, and to make it available in time for Dgraph Rocket release. Next up, we have learner nodes. Learner nodes is a very interesting concept. As you might know, Dgraph cluster works by having by operating in a Raft quorum, Raft group. Essentially, multiple Dgraph alphas would form one Raft group and run elections to figure out which one is the leader, and all the others would become followers. And the leader then essentially replicates data as data gets written across the system. So in this system, in one Raft group, all of the servers are participating in leadership elections. The thing about learner node is that it does not participate in leadership election, which means that it does not need to achieve a quorum, and it does not introduce any delays in all the reads and the writes that might happen. So you can take a learner node and put it somewhere really far away. For example, you could put it in a region which is at least 200, 300 milliseconds away from the cluster, and it would not affect the main cluster. Rather, it would act as, you can make it act as an edge computing device, which is getting all the updates from the cluster, so it can serve local traffic in this faraway remote region. That's one of the really big use cases of a learner node. The other use case of a learner node is to be able to spin up a bunch of these when you expect a spike in traffic, or when the spike in traffic hits you. This sort of gives you this automatic scaling, which is typically hard in a database, but with learner nodes, that is very much possible. So you can spin up these things. You serve you get heavier throughput. You are able to serve more throughput. You get through a spike of traffic, and you can then discard these learner nodes. And so these are two very big useful things. Learner nodes are available again in Dgraph Rocket release, and we will soon make them available in Dgraph Cloud as well. And that would be incredible, because Dgraph Cloud is already available, as we mentioned before, in 16 AWS regions, soon to be like 20 plus AWS regions. So you could have your cluster in US West, but your users sitting in Europe, in Far East Asia, or in Australia could be having learner nodes right next to them, so that you can serve the local traffic at a much lower latency than having them talk to the main cluster in the US. The third feature that we have here is change data capture. A database is never running in isolation. Typically, the updates from the database are being sent over to other systems for various kinds of processings, and capturing these data updates has been a much asked for feature by our community. And we thought, Kafka is extremely popular for this event-based processing and event-based streaming. And so what we did was we took the concept from chain data capture and merged that with Kafka. So Dgraph now natively supports pushing change data capture events to Kafka, so they can then be used by then be shipped wherever they need to be shipped to be used by other systems. And we built it in a way where even if Dgraph alphas crash and they come back, the stream would not be would resume from where it was last. So you might get some duplicate entries, but they would always be, they're guaranteed to be in the right order, and you're guaranteed to never lose an update, which is really, really kind of important to making sure that you always see a full uninterrupted stream coming out of your database. The fourth feature I want to talk about is audit logs. Security is really important to us. From very early on, we introduced TLS communication between client and the Dgraph server, and we even introduced a special data type that I had mentioned before called passwords. So all the users' passwords can be stored safely in the database without any fear of leaking them in plain text. And we even introduced encryption at rest, I think last year, so that the data before it touches the disk is already encrypted. And there is a data key rotation that happens, that is configurable, that happens every a number of days, and the master key can then be stored in the vault. So we really have gone through a lot of effort to make sure that Dgraph is really secure, and part of that security is also about accountability. And so we recently introduced audit logs, so we can capture all the activity that's happening in the database. so that in case there is any malicious activity in the database, the DBAs and the users would get to know about that via the audit logs. And these audit logs, the way we have built it, they can also be encrypted, so they can be stored safely as well. And this audit log feature is again available in Dgraph Rocket release and would soon be available in Dgraph Cloud. Now we talked about all these features that Dgraph Rocket Release has and would be soon in the cloud. Let me actually demo you some of these features. We'll start with multi-tenancy. And for that, I'm going to log into my workstation, go to Dgraph. We have this tool called Compose tool, which lets us create a Docker Compose. So we can easily run Dgraph cluster. Let me just walk you through that Compose tool. It will run 1 alpha, it will run 1.0, it will run set it up for change data capture, and also run change data capture consumer. Now, if you remember, change data capture is being pushed out to Kafka. So we're going to push out the updates to Kafka, and then CDC consumer would be a Kafka consumer, which would allow us to see what's happening. --ACL would support access control lists. We're going to set the servers, Dgraph instances, to have this host name, which is the host name of my workstation on Dgraph's internal VPN. And then we'll add some extra alpha flags to set the audit log output to, let's call it audit. All right, and I'm going to quickly show you the Docker Compose that we have built here. It exposes the 3 ports. We have the volume set up here. We have ACLs enabled. And then we have Kafka image, Kafka consumer image 0, and Zookeeper. All right, so we'll run this. It's the run.sh script essentially compiles a Dgraph binary, and it would spin up all of these containers from the Docker Compose. And so now we have a Dgraph cluster up and running. The first thing that I want to show you is that we can do is multi-tenancy. And the way we'll do multi-tenancy is that we will create a bunch of namespaces in the cluster, and we can then send updates to them for the same predicate, and show that they are not interacting with each other. They are essentially acting as logically separated, logically and physically separated. Now, before I go there, let me use a tool here, which we call a Dgraph increment. And the Dgraph increment tool is just something that we're going to use to connect to this running Dgraph cluster and make some updates. So the way Dgraph increment tool works is that it was designed to test out Dgraph's transactionality. So it starts off with the value of 0, and it adds 1 to it and commits it. And so in this case, we ran the tool once, we logged into it. If people notice, because we have ACLs enabled, we have to log in. And so we set the username to root, password to password, and namespace 0 is the default namespace. So we were able to log into namespace 0, which is the default namespace, and then update the counter value from 0 to 1. Now, if you run it multiple times, you will see the counter value is increasing from 1 to 2, 2 to 3, 3 to 4, and so on and so forth, right? Now, let's try something. Let's try to run this on namespace 1. What happens is that we actually get a crash because namespace 1 does not exist. So it complains about invalid username password because namespace 1 does not exist. So the first thing we need to do is to add the namespace. So let me go and add namespace here. So we are talking to Dgraph's admin endpoint, and we have a mutation called add namespace. So we're going to try to run this. And it has created namespace 1. So if I keep running this a few more times, it's going to create more namespaces for us. So every time, as you can see, the namespace IDs are increasing. Actually, maybe it's not very very visible. Sorry for that if it's not very visible. Insomnia is a bit trickier to adjust the fonts for. But I just run it 10 times, so we have 10 namespaces up and running. Okay, so we got namespaces 1 through 10. Now, going back to this thing, now if we were to run this counter in this increment once more, let's remind ourselves where we were. So at namespace 0, we are at counter value 5, right? And let's run this for namespace 1. For namespace 1, it has never seen this this thing before, so it is just setting it to value 1. And if you look carefully over here, this is the Kafka consumer. This is doing change data capture. We'll get to that in a bit, but I just wanted to show you that it's actually talking to the same exact predicate counter.val in namespace 1 as it was doing in counter.val namespace 0. So they are both talking to the exact same predicate, but because they're separated by namespaces, they're not seeing each other's values. So a 5 over here would not see the 1. So if I go back and try to increment namespace 0, it would be 6. And if I were to increment namespace 1, it should be 2, which it is. So now let's run a bunch of them. So I'll just do and this command. So basically in sequence 1 to 10, we will echo namespace equals to namespace dgraph increment, and the every namespace gets its own GROOT and has its own password. So you can create a namespace, and then that namespace can get its own guardians and its own list of users with their own login password. So it's really sort of like separated out. Now let's see. So if we were to run this, okay. So if you look very carefully here, sorry, it might not be as clear. Let me see if I move it over here. Okay, let's go back here. So if you go to with the namespace 1, the counter value was 3 because it was 2 before. So we increased one more time, it became 3. With namespace 2, it's 1, and all the namespaces from there onwards, it is sort of 1. Let's make some changes here. So what we'll do is we'll say --num equals to $i, so that each namespace gets incremented namespace number of times, just so we have a different value for each one of them. Okay, and I'm just going to do a read right now. So RO means read only. So you can see namespace 1 is 4, but namespaces 2 through 10 are increasing, 3, 4, 5, 6, etc. Now let's just run this in a while loop. We'll just run this like that. Okay, so now we are iterating over the namespaces and adding the counter values. What I want to show you in this one is to show you change data capture. So let's go to the right-hand side over here, log into my desktop, and we were running a bunch of Dockers. One of them is the Kafka consumer, this one. So I'm going to just follow the logs of Kafka consumer. And as you can see over here, all of the updates to namespaces 1 through 10 are coming over here live. And the values as well, along with the UIDs which were updated, whether it's a set operation or a delete operation, it's a mutation. And so this is getting streamed via Kafka to this Kafka consumer that we are listening to, and basically we are printing it out. And so we're listening to over here, right? So now if I stop doing these updates, then these updates stop too. And let me just do one quick update here and we'll remove the true. And we will run it just one last time. Oops. All right, so you can see all these updates to namespaces. Along with the namespace, the value and everything is all coming down to is all getting captured via the change data capture and getting streamed to Kafka, which we are listening to. All right, so so I showed you multi-tenancy and I showed you Kafka streaming of change data capture. Now, next thing I want to show you is audit logs. So for audit logs, we had, let me run this thing again in the while loop so we will have something to look at. All right, so this is going on. Now for audit logs, we're going to go into the Dgraph alpha instance. And we had asked in our Docker, actually, if I look at we had asked in our Docker Compose that the audit logs should go into the audit directory. So we have an audit directory created over here, and let's just follow the audit logs. Audit logs are a bit more complex to read compared to the change data capture because that's a lot more simple. But if you look at the audit log very carefully, let's look at one of them. Actually, let me just print out. So we can look at one of them really carefully. Let's look at this one. It starts with the timestamp, so we know exactly when this event happened. It knows the endpoint that was called, which is Dgraph query. It mentions which user was logged in this case, Groot, which namespace the user was from, the server which they accessed, and the client IP address along with the port where we ran the commands. And it mentions like, which method did they use? Did they use gRPC or HTTP? So in this case, it is gRPC. It mentions what was the request. So in this case, it was a mutation. So it mentions the exact mutation. It mentions the value that they set and the fact that it was meant to be commit set to true. And then in the end, it mentions whether this mutation was successful or it failed. In this case, it was successful, therefore status was okay. Now, let's do one more thing. Let's just create one more namespace. So I did create namespace 11, and let's see how it affects the audit logs. They might have, let's see, unauthorized user. Let me run that again, just so that I get a clean log here. There it is. So as you can see, we ran the add namespace query, and it was run as root of namespace 0. In fact, the guardians of namespace 0 are the only ones who are allowed to add or delete namespaces. So in this case, we captured the audit log captured the time, who was logged in, from which client IP address, the request that they ran, and whether it ran successfully or not, and it did. So that shows the audit logs. The last thing I want to show you guys. Now for the last part of this, I want to show you learner nodes. And for that, I'm going to just run the Dgraph cluster again. So while it's getting set up, I will pick up a Dgraph Corp machine, which is all the way in India, and I will show you the ping latency of that machine. So it's a machine called dginbravo.co.io. And as you can see, that the ping latency from my workstation here in the US to this machine in India is 250 milliseconds. And what I'm going to do is I'm going to log into that machine. And as you can see, it's already a bit slow. And I have Dgraph binary copied over here. Remove the P, T, and W. Remove the previous directories. I have Dgraph binary over here. Our cluster is up and running here. So the ping latency, as you can see, is pretty high. I will run Dgraph increment tool here. And let's not, actually we might still need to log in. So password equals password, but we'll just use namespace 0 in this time. And I will set the wait to 3 seconds. Okay, because we just restarted this cluster, it started from scratch, so the counter value is back to going from 1 to 3. All right, so this increment is going on, and at the same time, let's start the Dgraph cluster, Dgraph learner node here. So we'll set raft equals to 1, idx equals to, let's say, 101, and learner equals to true. My address here would be tginbravo.com with the 7080 port, which is the gRPC port for alpha internal. And the 0 it should connect to would be the 0 of the main Dgraph cluster running in the US. So that would be in my workstation. Which, and the 0 port is 5080. So I think this should run our learner. Let's see. Okay, so what this has done is that it has gone and asked the 0 leader, collectively 0 leader, gotten the state of the membership, and then went and connected with the group 1 leader. And the way the learner nodes work is that they pretty much can do all the stuff that a normal alpha can do. The only thing that they don't do is they don't participate in elections, so they don't end up slowing down the quorum achievement for the main cluster. So if you look at the conf state that was set for this group 1, is that it has one node, which is the main node, which participates in elections, and then we have the learner 101, which is only a learner node. Now let's log into this machine again to get another terminal here. And what we'll do is we'll start to read the Dgraph increment. We'll run the Dgraph increment so we can read the updates that are happening. And let's say num equals to 1000 and best effort, and we need to set the alpha equals to dginbravo.core.dgraph. You can think of it as a local client that's running in India itself. So what is happening over here is that it's doing a best effort query and talking to the alpha that is running over here and getting the value of the counter directly from this alpha in India. And you can notice that by looking at these latency numbers. So the time it takes to query is only 2 milliseconds, which is pretty much like, it's on the same machine. Now, if you notice these numbers over here, so it's 65 and 66. Actually, let me move this over to this so we can see both of them together. So this is our main workstation, and this is our DGIN, which is the India machine. And as soon as they have updates over here, the updates pretty much get reflected immediately. Let me increase the frequency of this instead of waiting for, just waits for 0.5 seconds. So we had 76 and immediately 76 gets reflected, and we have 77 gets reflected, and so on and so forth. Now we'll do one thing. We will, instead of doing a best effort, we'll actually just let it run some updates. So now what it's doing is that it's actually trying to increment the counter. And as you can see, it's having to talk to the Dgraph cluster all the way in the US. So the latency numbers are pretty high here. The query took 230 milliseconds, which is exactly the kind of ping latency that we see, and the mutation took double of that. So overall, the server took 600 milliseconds to execute these writes. And this is the same counter, and you know that because you can see that this one got 100, and this one actually got 100. This one got 100 and 101, so this one did not see 100 and 101 because of the transactionality. Only one client can see each number. And so you can see the huge latency distortion here. But then if you make it just a best effort is eventual consistency read locally. It happens really fast. It happens really fast, and it can see the updates. So that way, now if you have essentially a client in India, it can get the updates from the US cluster while it's connecting locally to the client in India, and can get really great numbers, latency numbers. So that concludes the demo around learner nodes. And I'll go back to the slides now. Thanks. Now that I've shown you a demo of all the features that we have built so far in this year, I'm really excited to share with you the roadmap that we have for the rest of the year. And the roadmap for this year is really built around two things. One is performance optimization, and second is ecosystem integration. So talking about performance optimization, Dgraph query performance is already really good, but the fact is that we don't even have a query planner right now in the system. And so what we want to do is we want to build a really solid query planner so we can really optimize the queries even way further than where they are today. Already, as you saw, we are already beating our competition 2 times to 20 times in query execution. But with these upcoming changes around the query planner and query optimizations, we feel that the difference would widen significantly. That's one part of the equation. The second part of the equation is that the data loading speed. We already have a commit in our main branch where we have double the speed at which data can be loaded into Dgraph, and we have more changes coming in, which we expect to further double the speed by which data can be loaded, and that would make really easy for our users to bring in large amounts of data into Dgraph, and then be able to run really complex queries extremely fast. So we're really excited about that. That's one. The second thing is around ecosystem integration, and what we have seen is that a lot of our users are migrating from SQL database or a MongoDB or other graph databases. And to support this, we'll be introducing automatic migration paths, automated migration paths. We'll focus on the Dgraph Cloud first. And the experience that we want for our users should be that they would upload their exports from the database, or potentially point Dgraph Cloud to their database, and we will take care of the entire process of migration into Dgraph for them. And we also want that if they have a system already running which they cannot completely migrate over to Dgraph, we will be able to take a live stream of updates from that other database into Dgraph, so Dgraph can become the unified data store and become the unified graph platform for your application. And the important thing here is that by allowing migration and allowing streaming of data from these different data silos, whether it be a SQL database or a MongoDB or whatever other databases that might be, or other data sources that might be, by pulling them into one graph platform, we get to the most important use case for Dgraph, which is data unification. Now, if you go back to the inspiration for Dgraph, that was that we had this big knowledge graph, and we had these fragmented backends, each with their own data models, which were running separately. And the big thing that we wanted to do at Google was to be able to unite everything into a single graph platform. And that's exactly the kind of use case that we see other people, our users, doing with Dgraph as well is that they take data from all of their vertical data silos, which they probably can't even run queries across easily, and put all of that into Dgraph, making it the unified graph platform, so that they can then run really interesting queries across it, really complex queries, be able to traverse relationships and identify interesting patterns and surface that to the users. And that is the big underlying vision that we have for Dgraph Cloud, is to become the cloud graph platform which you can rely upon for running your microservices, for dumping all of your data, for serving user traffic, and for all of the interesting use cases that are possible when you can unify your data. Thank you.
Thanks, Manish. There's nothing quite like seeing cool new features in action. Super exciting stuff happening at Dgraph. Now, for our next talk, we have Mike Hawks, the CTO of CapVentus. They're an integration and analytics consulting company based in the UK. CapVentus serves some of the largest global brands in delivering integrated solutions around analytics, customer engagement, and experience management. Mike is a longtime Dgraph user who's followed Manish since Dgraph's inception. He'll be talking about how Dgraph is the key to integration of different data sources. Please welcome Mike Hawks.
We deal with data every day. Data has become the key ingredient when running a successful business. Data now arrives over every channel. We get emails, phone calls, messages, chats. We're bombarded by social media, and we get it 24 hours a day, 7 days a week, 365 days a year. Online retail customers now expect deliveries within 24 hours of placing an order. They want flawless engagements with ordering and supply processes while still demanding that personalized service. Thanks to the evolution of the internet, customers compare products, services, and prices across numerous systems before buying. Meanwhile, artificial intelligence now helps us find the products we need, even when we didn't know we needed them. Psychological models and complex search algorithms drive us towards specific products, with analytics tools monitoring our every mouse click, gesture, or purchase. A business has to react in near real time if it wants to keep its customer base. A modern business has to gain insight and predict as far as possible what the future holds. In order to support this, we need the right information presented in the right way at the right time. And underpinning all of this is data. At CapVentus, we consider data to fall broadly into one of two categories: experience data or operational data. Experience data helps drive what you might think or do, and we can ask questions. How do you rate our service? Would you recommend us? And so on. In a simple shopping model, we might need to ask only a few questions, but these can identify real problems throughout the entire manufacturing and supply chain. Applied properly, survey platforms and analytics tools can help identify problems, reduce customer churn, and increase brand satisfaction. Operational data, by contrast, deals with processes and systems. Operational data provides the lifeblood of the business, helping to connect things, specify activities, and manage processes. With the right amount and type of operational data, businesses can predict what they need and when they'll need it. Way back in the 1st century, Hero of Alexandria invented the steam turbine. This, however, was only seen as a novelty, and few could think of any practical applications for such a device. It was an after-dinner novelty, a plaything. And there it languished for nearly 1,600 years, until in 1698, Thomas Savery created a steam pump originally based on Hero's design. He needed something to extract water from his coal mines, which constantly flooded. Unfortunately, Savery's design lacked several fundamental components, and this made it inefficient and expensive to run. Some 80 years passed before James Watt, the noted Scottish inventor, mechanical engineer and chemist, added a condenser to steam engine designs. This addition transformed steam technology and springboarded the entire industrial revolution. James Watt, therefore, is the first of the curve jumpers I'd like to mention today. While there were many other steam designs starting to emerge at the time, none could offer the reliability, efficiency and performance that Watt's engine could provide. I could mention a few more innovators and curve jumpers throughout the Industrial Revolution, the discovery of electricity, radio and wireless communications, or on to the development of integrated circuits. But instead, I'll focus on a few of the more recent innovators. Throughout the 1950s and 60s, computer technology started to mature. Storage was becoming cheaper, and with the evolution of the hard disk, databases became more common. And after departing Ampex, Larry Ellison, Ed Oates, and Bob Miner launched their first product. That product, a relational database manager, was finally rebranded as Oracle in 1995. It is, of course, the largest database company in the world today. On the 12th of August in 1981, IBM launched the personal computer. Now, the IBM PC wasn't necessarily the fastest or best computer at the time. Certainly from a technical perspective it wasn't. However, IBM held a dominant position in the computer industry at the time, and it created a competitively priced machine that sold way better than any of the analysts thought possible. However, I don't consider IBM a curve jumper. Instead, I think that trophy goes to Compaq. Compaq took the IBM BIOS, the computer's firmware, and reversed engineered an entire hardware platform from its API so that its machines could comply with the IBM BIOS specification. In effect, Compaq demonstrated that any hardware manufacturer could make a computer capable of running any IBM PC compatible software. This created a whole industry of IBM-compatible machines, and some of that original design ethos became so standardized that it still persists to this day. Curve jumpers take more than just an evolutionary step. While the rest of the industry gradually improves or introduces point changes, curve jumpers take an entire market sector in a new direction. On the 9th of January 2007, Steve Jobs did exactly that with the introduction of the iPhone. Here, he presented a handheld device that combined many other technologies available at the time. For the first time, a consumer could have a touchscreen phone complete with internet browser, music player, map viewer, and even a YouTube client. Overnight, this device displaced other dominant technologies from the likes of Nokia, Microsoft, and BlackBerry. Dgraph earns its place on the curve jumpers list because of the way it handles data. In a conventional SQL database, we have to represent data in a list of fields, each identically structured. Let's take an invoice as an example. Here we need a unique reference and a date of issue. Talking of issue, we need to have someone to receive it. So here's a person, and the person needs to work or live somewhere, so let's add an address store too. An invoice has one or more line items, giving the quantity and price of products. Then we have the product information itself, in this case another reference and description. So here we have our basic entities. However, in any database model, we need to define how these various entities link together. Here in the SQL world, this comes at a cost. We need to add additional intermediate lookup tables. These intermediate tables should only represent methods to cross-reference things. Person to address, person to invoice, invoice to line items, and line items to products. However, in reality, these often end up defining the business logic for the entire application. And this gives rise to a few problems. Anyone looking at the tables alone has no way to understand the relationships between each of the entities. How do I know, for example, whether the person's address represents the home or billing address? I lose sight of how these entities relate to each other and, more often than not, Queries end up holding intermediate values or managing context rules, meaning that I have to search through database queries to find out what my system is really doing. And the queries themselves become ever more complex. At some point, I have to understand whether I need an inner join or an outer join, whether inner selections will invalidate other parts of the query, and I have to understand the table schema from a design perspective before I can expand my system. In many cases, we come across horrific SQL, put in place by some database administrator with a personal vendetta against anyone daring to use their database. And yes, this is a single query. And yes, it's real. That's enough pain. Let's talk graph again. We still have the same entities to consider: person, invoice, address, line items, and products. But when I come to linking these, I can define the context in the link itself. I'll go ahead and add a billing edge to a person. And that would point to an address node. Note that I called this billing because I might also want to point to a home address, and I can do that by adding a home edge and calling it home. By looking at person, I know instantly that I have their first and last names along with their billing and home addresses. At this point, I don't care if I don't have all the information. The business logic will define the rules. So if a person must always have a billing address for the invoice to run, that's up to the business invoice logic, not the database. Now I'll add a link to the invoices themselves. In this case, the square brackets define 0 or more invoices. The database is telling me the context of the link and how it expects to see them. We can do the same things with items and products, and if I want to get flashy, I can start adding facets to each of the edges to carry additional information about the link itself. Generally, I try to avoid this. I prefer to do this kind of thing via edges in and of themselves. Now we start hitting the curve. Dgraph lets me query directly against the database using GraphQL. And this means a single query like this can do the invoice run. And the data I ask for comes back in the result. Where I start getting excited is the ability to use RDF. And actually, this shows a major curve. Dgraph's concurrency. I'm vastly simplifying things here, but in principle, I'm starting at an invoice record. It has edges pointing to other nodes. Dgraph shards on these, meaning that each edge can sit on its own server if it wanted. Each of the requests runs in parallel. This means I get a huge performance gain from using Dgraph. This is the main advantage of using a native graph database that doesn't rely on fixed structures. As I introduce new edges, Dgraph will sort out how best to shard and handle it accordingly. Continuing along the curve, Dgraph also lets me do things via single queries that would be difficult to model otherwise. This, for example, shows a real-world data cleansing case. When we ingested the data, we found an entire section of the business was disconnected from everything else. Another view showed that these entities also had different management teams. Again, not connected to the rest of the business. After we worked out where these tasks should go, we ended up with an integrated model where all the processes and associated business activities joined up, and we removed a lot of duplication or redundancy in the process. Dgraph has taken us into an entirely new direction. We don't worry about scalability, and we have blinding performance compared to other graph and database systems. We use GraphQL and, via Dgo, use a DQL client a lot too. Because Dgraph also provides native RDF support, we also employ that when doing a lot of edge grouping or linking activities. This improves our development throughput, reduces maintenance costs, and helps us grow organically. In the day job, I look after a very technical landscape. We deal with customer engagement through support systems and ticketing platforms. This crosses over into experience management, where we can measure employee and customer experiences and collect key performance metrics. Now I have the data, I'd like to gain insight from it so that I can improve quality and performance, or reduce costs, or meet other business needs. For that, we have a data science team, and working in conjunction with our analytics teams, we help companies derive value from the data. After all, there's little point in collecting it if you're not going to use it. While we use other tools and systems, I'm showing our preferred partners here. Zendesk for best-in-class ticketing, Qualtrics to help measure customer or employee experiences, Qlik for data visualization, and of course Dgraph for its 3 products, Ristoretto, Badger and Dgraph itself. With all of these tools, and with others in these market sectors, we need a way to integrate, synchronize and manage data. And for that, we have our own internal system, affectionately known as Glue. Glue works in harmony with Dgraph, Badger and other data sources to handle complex integrations with ease. It provides a scripting engine based on Google's Go programming language to federate GraphQL endpoints. It acts as a GraphQL wrapper around legacy interfaces such as SOAP or message queues, REST or custom APIs, database links, and so on. Glue has a central core and can work on bare metal or at higher levels through the stack as required. Its core engine has shifted between 2 different scripting environments. For the original model, we used a TypeScript engine, but battled with making it support concurrency and things that the Go language supports natively, channels, mutexes, and so on. As a result, we built a Go-based scripting engine, allowing us to concentrate on functionality rather than getting buried in language semantics. Lifting the covers off the core reveals a whole host of process management services, and these coordinate and synchronize between services, scripts, and provide state machines for the scripts themselves where necessary. Each runs in isolation to protect process integrity and maintain security. The engine wraps calls via a virtual import mechanism, and this provides direct access to Dgraph, Badger or its own internal mapped data and processing services. As a result, there's minimal overhead when calling Dgraph native functions from within scripts or when making requests to Dgraph Cloud. With Glue's high-performance parallel integration and Dgraph's horizontal scalability, we have a laser-precise and lightweight integration service that can handle almost any volume of data in real time. We leverage Dgraph's Jepsen-tested transactional integrity within Glue to give extremely robust data management and synchronization across disconnected or asynchronous processes. So let's put this into the real world. With Glue, we can, for example, track events in Zendesk so that when a customer opens a support ticket, we validate within 0 that the customer has an account with us. And for those on a drawdown support contract, that they have sufficient credit to allow us to resolve the ticket. If not, we send a message via Pipedrive to our sales team. Assuming that this customer has sufficient credit, we can allocate team members to deal with the support issue, having passed the ticket through Google Translate and Amazon's Comprehend to analyze sentiment. Then we send it over to Rike to manage the projects themselves and log the time spent. Finally, raising invoices back in 0 against the support project for the client. When it's all over, we bring in Qualtrics. Now we can measure the performance of our team. Was the matter resolved satisfactorily, and how was the service overall? How can we improve things in the future, and so on. This feeds back into the organization to help the business get better at what it does. Glue handles the interfaces. Dgraph keeps track of all the various systems, key fields, custom entities, and so on. Once again, back through Glue, we pass this to Qlik or Power BI or Tableau to provide dashboards and to help predict future support requirements. We're currently extending this part to provide a wrapper around BI tools to allow them to work directly off of Dgraph. You might have noticed that everything within that landscape sits within its own system. Zendesk handles the tickets, Xero the accounts, Pipedrive handles sales data, and so on. We don't need to move all of this data. Instead, we link to it, and we use Dgraph to help us maintain consistency and referential integrity throughout. The Jepsen tests become really important in this context. When I search for information via Dgraph, I know I'm getting a single, consistent view across all the platforms. Within CapVentus, we run Dgraph in several contexts. For developers, the flexibility allows us to iterate through schema changes without impacting other services. When running integration or migration programs, we use Dgraph to help us analyze the structure and composition of our data. And for our BI teams, we can choose where best to run analytics functions. Do we aggregate and simplify data within Dgraph queries, or is it better to pass raw data directly to the likes of Tableau or Qlik? And this brings us back to curve jumping. When I first came across Dgraph, I like things like the horizontal scaling and the ability to use things like RDF for data updates. I like DQL, the Dgraph extended query language, to search for data. However, Dgraph hasn't rested on its laurels. Instead, the team continues to develop and provides us with a way to go from initial proof of concept right through to commercial models simply by changing the connection URI. With the advent of Dgraph Cloud, we find ourselves in a position where we can offer implementations in several ways. For development and early test, and for smaller projects, we use open source instances within Docker containers. For the medium-scale production environments, we can host in AWS or Azure. When things get a bit more serious, we need enterprise-grade features. And for this, we can switch to our own hosting or use Dgraph Cloud. All of this is a seamless transfer. We can add nodes if we're hosting, or we can just pass the management of the whole thing and its associated infrastructure over to Dgraph Cloud. Not only that, Manish and the team brought GraphQL to the front of the stack here too. We still drive a lot through the DGO interfaces and use both RDF and DQL across them. However, we also have the option to bring in native GraphQL services within the Glue federation layer. With the GraphQL model, I can upload a schema, and Dgraph does the knitting behind the scenes. It provides all the standard functions required to integrate and update the data, and it does it instantly. It's extremely quick. And for schema-driven organizations or developers, it's a hugely effective way of managing data. When I first started our Glue project, I wanted to create something that I could use for discovery, integration, and orchestration, and do all of this at scale. We adopted Dgraph early on because I needed to find a flexible way to link data and let the integration services evolve naturally. This gave me a constantly changing landscape where I may need many integration microservices all linked together. Glue therefore deals with the APIs and message queues. It can federate queries across multiple backends, and it can operate as a single instance or part of an integration network linking multiple Glue instances together. I can run multiple Glue engines, each supporting concurrent and parallel scripts. Each of these scripts potentially handling concurrent transactions. It crosses the boundaries with components working inside the customer's infrastructure, or in the cloud, or across private and containerized networks. Conventional databases would force me to work in a different way. Dgraph frees me from the constraints imposed by traditional tables, with all that key field management and complex SQL, which invariably hides business logic in a hidden database layer. All of that's gone. Beyond Glue, CapVentus has started building a platform. We've based it entirely around Dgraph. And while it's early days, we're already seeing the benefits of building websites from the ground up using a flexible schema and having GraphQL as the primary API, with resolvers handling distributed queries and mutations, and any front ends simply plug into this entire model. Dgraph lets me work with data. It removes many time-consuming and restrictive processes, and it improves data visibility. In my integrator's world, I can see anomalies before they become a problem. We live in a technical world. We now have better ways of handling data, and Dgraph helps us to do that. For those reasons, for me, Dgraph jumps the curve. It scales, it performs, and it lets me keep data in place, or I can bring it inside the database. It has transformed the way we work. Instead of trying to shoehorn business processes into a restricted model defined by legacy database systems, I now concentrate on the business needs and let the data support those needs. Here at CapVentus, we're looking forward to a bright future, and we're extending our Dgraph team. We're hiring. We're developing new platforms for our clients with Dgraph. It's become a fundamental component in our development, and long may that continue.
Wow, thanks, Mike. I love how Dgraph was called a curve jumper. So cool. I'm pretty impressed that Dgraph has empowered easier integrations, and I'd love to take a peek at some of Glue's code. Making things easier seems to be one of the themes of today's talks. Our next speaker, Anthony Master, the founder and developer of MissionBase, is supporting digitized missionary operations around the world through the use of an integrated platform. He reportedly removed 50,000 lines of code after integrating Dgraph into MissionBase's system. Let's take a look, shall we? Take it away, Anthony.
Hello, and welcome to this presentation. I will be discussing how we went from SQL to Dgraph and our journey with MissionBase. After growing to over 500 users and implementing Advanced Access Control List, we faced challenges. After struggling to build our own GraphQL implementation, we believed there had to be a better way. We found Dgraph and fell in love. This is our story. Let me introduce myself. My name is Anthony Master. I'm the founder and developer of MissionBase. I have been using Dgraph since June of 2020. I have a bachelor's of theology but with no formal technical training. I'm a self-taught web developer by passion. Besides application development, I am the youth minister and missions director at my church. I have been involved in graphic design and web development since 2007. Let's talk about the idea of MissionBase. It all started with the address book, a spreadsheet, and a lot of time spent on the telephone. Here, let me explain. A lot of my friends are missionaries. These missionaries serve in different countries all around the world. To do the ministry work and support their families, they first must raise funds. These missionaries raise funds from independent churches all across America. They call these churches and book meetings to present their ministry. Many years ago, a few of these missionaries got together and compiled an address book. This address book has since been digitized and copied countless times. Since every person was using a copy, there was no good way to keep all of the address books updated. We knew there had to be a better way. If we could unify all of the users into a central address book, then when updates came in, they could be instantly shared by all of the users. At first, this seems like a simple task. There are various technologies out there that these users could have tried to accomplish what they needed. Some have tried to use Google Sheets, Salesforce, and many other collaboration tools such as Monday.com. But no perfect tool was found. Everyone had at least one of two problems. We needed to ensure our data integrity. We could not risk data being deleted by users on accident. The bigger issue at hand was data privacy. It was not clear at first the role that data privacy played in the user's needs. To understand this better, we had to look at our users' data. Along with a public address book, users also needed to store private contacts, private financial data, private and public notes, and personal tasks. All of these data points were linked together. Private contacts can be linked to public organizations. Private financial data is linked to contacts and organizations. Notes are linked to contacts and organizations and can be public or private. And personal tasks can be linked to public or private contacts and organizations. What we needed was an application that allowed our users to collaborate on the data to keep it fresh and up to date. This application also needed to be secure to keep personal finance data safe from other users. Users also requested that we provide tools to integrate this data with other services to keep their data connected. In about 4 months, we built version 1.0 of this application. We were using a LAMP stack. In this presentation, we are mainly discussing the MySQL portion of this environment and the problems we faced. To keep our users' data secure, we decided to namespace each user to his own database. We had a database to manage users, a public database to store and manage a public address book, and every user had their private database to add in their secure data. This was very secure, but became very complex. Growing to over 500 users, we had over 500 databases to manage. We quickly realized that our application was hard to scale, hard to build features, hard to fix bugs, and hard to analyze. Every time we needed to change the schema, we had to replicate that change in every database. Finding out how users were utilizing private features was very time-consuming because we had to query each user's database individually. Then came the biggest challenge we faced. We needed to add new team features. We wanted to allow our users to work together in smaller groups or teams. Teams should be able to import existing data, and we will enhance it with our third-party APIs. Teams should be able to share contacts privately. Teams should be able to limit their displayed data to only the data their team has verified. Teams should have ways to work together, such as notifications to other team members. Teams should be a first-class feature with premium support and future enhancements. Teams should no longer be dependent on email rings to get the data they need to share. Teams should be able to add custom fields to customize the application to suit their needs. Teams should be able to integrate their data with their pre-existing third-party applications, such as their financial systems. And lastly, team admins should be able to control the access to the teams and granularly control the rights of each team member within their application. We were excited to start building out these features, but we faced a big challenge. Where do we put all the team data? If we add the team data to the public namespace, then we cannot secure it. If we add the team data to the user's namespace, then we would have to replicate the data for every user. If we created a new namespace to hold all of the team's data combined, then we risk the problem of teams accessing other teams' data. We could have created a new namespace for every new team, but we were imagining exponential growth and we were not able to scale that model. There was really no perfect place to put team data. We needed to rethink and redevelop our data storage strategies. Up to this point, we were dependent upon the database to provide data security. For team features, we would need a way to granularly control access to a shared database. The only way to add access control on a shared resource, like we needed, was with an API. Many modern web frameworks are client-side only. Data security is not secure if it is left up to the client to perform. Data security was not the only factor, but we also had to think about data integrity. We needed ways to control data types and data uniformity. Data that was not uniform became very hard to manage. We were wanting to eventually build out native applications for users' devices, and we would need a flexible toolset in the API. This last point of access control was similar to the first, but also unique. We needed a secure data, but also needed to be able to granularly control and grant access privilege over that data based upon the authenticated user or application. Looking for the best practices in the API, we realized that all of our data is highly connected. We wanted to query our data in a graph. Our users needed to do deep traversals into our data structure to find the information they need. We learned about GraphQL, which provides a simple API for applications to communicate with back-end services. I said simple API, but that may be the overstatement of the year. GraphQL is hard, especially in a relational world. What GraphQL boasts of being simple and easy becomes very hard to implement. GraphQL is great at providing clients an easy way to ask for the data, but inside the API, resolving the client's queries is completely dependent upon the developer's implementation. The four main reasons I found to use GraphQL quickly became the four struggles I had with GraphQL. GraphQL makes deep joins look easy. You simply ask for the data as it relates to the parents. But joins in the relational world can cause very poor performance if not done well, and even have very small limitations when done correctly. To circumvent the problem of deep joins, many GraphQL engineers will create the N+1 problem. The N+1 problem is where n additional requests are needed for every parent request. This causes a lot of network traffic between the GraphQL layer and the database. Trying to solve the N+1 problem, we created dynamic SQL joins. This led to many performance issues though. The second issue I had with GraphQL is overfetching. In many of the GraphQL implementation examples I found, developers were selecting the entire row of data when they only needed a single field was being queried by the client. We circumnavigated this by only selecting the fields the client requested. We quickly realized, though, that what we had fixed in overfetching had evolved into our third issue of underfetching. When we only selected the data that the client requested, then we would have to select the additional data the next time the user requested more data about the same row, even if in the same request. This led us directly back to our N+1 problem. To top all this madness off, we found ourselves writing very complex middleware to solve our team features and secure our data. The middleware logic became not only massive, but it quickly aided our performance. We had to join more and more data together to have the data needed for our middleware algorithms. This cycle was endless. After 6 months, we were 50,000 lines of custom code into our GraphQL API implementation with no end in sight. This was not a good place to be, with users that were expecting our new team features right around the next corner. We were a very small team development at this point, with myself being the full-time developer and another developer pitching in part-time. We wanted to build out these new features in an application, but did not have the manpower, resources, or time to do it all ourselves. We had too many layers. We were trying to implement GraphQL layered on top of a relational database, but what looked easy was actually very hard. GraphQL is great in theory, but it fails in many implementations. Instead of making good on its promise to simplify the API, it usually just adds more complexity. The hardest part of GraphQL became the need to write resolvers. Every time the application changed and the API needed to be iterated upon, we found ourselves driving through more layers and thousands of lines of code. All of these lines of code and layers need to be updated separately for each change. We believed there had to be a better way. We asked ourselves the question, if our API is a graph, then why isn't our database? We began a search for a graph database we could build our API layer on top of. We tried many different ones such as Dgraph, Neo4j, Tigergraph, Azura, Amazon Neptune, and Janus Graph. Each database had a learning curve and challenges to face. We narrowed our decision down to two databases, Dgraph and Neo4j. Neo4j had just launched 4.0 and was getting a lot of buzz. There were examples of developers writing GraphQL layers on top of Neo4j, which made the resolvers easier to manage. What made the final decision for us was support. We opened 2 support questions on Neo4j's community, which are still unanswered now 6 months later. We opened support questions on Dgraph and were quickly surprised that support was not just from the community, but also from the Dgraph's engineers and even the founder himself, Manish. If I personally have to choose between the option of having support from the community or having the engineers directly, I will choose engineers every time. I quickly learned that Dgraph support was exceptional because of the values that Dgraph had set in place. So support made the decision, but the GraphQL API sealed the decision. With Neo4j or most any other graph database solution, we would still need to write the resolvers for the GraphQL API layer. Dgraph took the GraphQL API layer and put it into the core of Dgraph itself. There was no longer a need to write resolvers just to do the basic CRUD operations. Now to get to the heart of this presentation, how we transitioned to Dgraph. While studying different graph databases, we came across so many unique graph query languages. It seemed like every graph database had their own language. There was no universal graph query language that every graph database had adopted. Dgraph was no different. Dgraph had took the GraphQL specification as a query language for APIs and extended it to be their database query language. At the time they were calling this GraphQL plus or minus, and I like to call it GraphQL more or less. This eventually became so confusing with the GraphQL spec though, that it was renamed to DQL for Dgraph's query language. The great part about Dgraph was that I did not need to learn DQL to start using Dgraph right away. I did find value in it and used DQL for management purposes, but in my application we are able to purely use GraphQL, which we had already learned. The next transition we had to make to Dgraph was much easier than we expected. We had already developed a quite extensive GraphQL schema. A complete GraphQL schema not only includes types but also queries, mutations, and the inputs and output types. Using Dgraph's GraphQL API, all we needed to do was to provide Dgraph with our core GraphQL types, and Dgraph will generate the queries, mutations, and the inputs and output types for those types based upon the schema directives we provide. Look at this very small type of a person with only 2 fields. Now compare this to the left-hand side of how much schema would be needed for the same API that Dgraph generates. We could not even show all the schema and make it readable on this slide. Dgraph makes schema iteration very easy. The longest part in our transition to Dgraph was writing authorization rules. Other GraphQL implementations leave middleware completely in the developer's hands. We would have to write complex algorithms checking clients' tokens and contexts to ensure that we were honoring the business logic that we needed. Dgraph takes these complex algorithms and turns them into simple rules. The best part about these rules is that you can write them in GraphQL itself. That's right, a query rule that in itself is another query. In this example, we are adding a rule to a user type and only letting clients query users if they have in their token the matching username. When I first tried to use Dgraph though, my biggest struggle was deployment. In my Windows-based environment, I was directed to use Docker to get started with Dgraph, but even Docker at the time did not support my system. We turned to Amazon services to run Dgraph. Deploying an optimized instance of Dgraph can be a hard task. Dgraph was in the middle of launching their database as a service /GraphQL. I was privileged to be one of the early users for /GraphQL. It has since evolved to even more and is now called Dgraph Cloud. With Dgraph Cloud, we do not have to worry about tuning the deployment of Dgraph, and instead we get to focus on our schema and our data. After spending a week learning these things in Dgraph, we deleted our 50,000 lines of code in our own GraphQL layer, and we never turned back. We no longer needed to worry about the back-end architecture. Instead, we can do what we do best, develop the front end of our application. We were using GraphQL and consuming the data, but still confused by what a graph database was. We are very accustomed to modeling our data relationally that sometimes we find ourselves getting stuck inside the relational box. A graph database made more sense when I thought more about a graph. Here we have a line graph with 3 points and a line plotted on an x and y scale. Each dot has properties for that scale that describe the dot. The line connecting these dots together has a label describing it as well. This is a fundamental graph database theory. Every piece of data in the graph could be represented by dots like these. Each property of the data point could be represented as the values on a scale. If we take away the two-dimensional plane, we can realize how two pieces of data may have a different set of properties. The connections between pieces of data can be represented by lines with labels identifying the relationships. Probably the most helpful thing I can share with you to help you understand a graph is to understand the terminology. I thought it was so important that I even wrote a post and discuss around this subject. We have trained our brains to think in terms of tables, rows, pivot tables, columns, joins, and clauses. What we need to do is forget most of that and transition to graph terminology. A table becomes a type. A row of data becomes a node. Now in a graph, a type does not hold nodes, rather a node is labeled by a type. This type defines the properties that are available to that node. Back to the terminology. What we call pivot tables need to be thought of as edges. What we call columns or fields need to be understood as predicates. Joins and relational lingo can be understood as subgraphs. And our SQL clauses such as where, has, and order by become inputs and sometimes directives. So now that we had a fully functional GraphQL API to use, we could start building our application. We were only missing one part, our data. We needed to migrate our data from our 500 MySQL databases into Dgraph. This seemed like a big undertaking. We found the initial data migration though to be easier than we originally imagined. We needed to write a script that could take our databases and combine them into a single RDF file. We found out that our data translated to around 7 million triples. But what does that mean? What is a triple? A triple is the simplest way to represent data in a graph. Follow me through this example. On the left you see 3 tables from MySQL. The users, contacts, and a contacts have friends pivot table. We are able to represent all of this data and the relationships in the form of triples. Triples take the syntax of subject, predicate, and object. The predicate is a key, the subject is an identifier, and the object is a value. We use blank nodes to identify our rows of data. This allowed us to refer to the same node in other places without having a preset unique identifier that Dgraph later created for us. The _: syntax is a blank node. We use a table name and a row ID for the remainder identification of the blank node. This allows us to refer later to the same imported MySQL row in their RDF file. In this example, the user has a relationship to a contact by the ID of 1. We use the same subject, predicate, and object syntax to represent the relationship between the user and the contact. With the triples, we could easily make two-way relationships such as is done with pivot tables. After we scripted all of our MySQL tables into a single RDF file, we were able to use a process called live loading to add this data to our running Dgraph database. We could then access our data using the GraphQL API. At this point, our API was done. We were able to complete our API in 1 week, where we had spent 6 months on it before. I will admit though, using the GraphQL API from day to day is still not everything I dreamed it can be. There are a few features I still find missing. However, when I look at what it is compared to what I had before, I'm very grateful for everything that Dgraph does for the application developer. It would be unfair to you if I did not mention the features I find missing as of right now. While I review these, I remind myself that Dgraph's GraphQL API is just last month 1 year old. I think it is the most advanced 1-year-old I have ever met. I would like to see in the near future edge filtering. Right now we can filter nodes by properties of the node itself, but are unable to filter nodes by the property of related nodes. This is mainly due to the fact that the GraphQL spec does not support var blocks that Dgraph has extended DQL to use for such queries. By rearranging the structure of the query or applying a cascade directive, developers can still achieve the same functionality. I would also like to see work done to make ordering better in the API. Right now I can order by predicates of the nodes, but I cannot order parent nodes by predicate values of related nodes. I find myself sometimes struggling to redesign my schema to put more fields I want to order by in a parent node that I ideally want to be in a related node. And there are other features as well that would be very nice to have, but are not blockers that I can somewhat easily work around in my client. These include support for arrays holding duplicate and ordered values. Right now all arrays in Dgraph are actually stored as what many would describe as set. I would like to see actual JS hooks for pre and post mutation. This is being worked on right now. This still looks to be a promising feature to allow users to hook into the generated resolvers with their own custom middleware for even more complex business logic. And then I would also like to eventually see more string functions, datetime functions, and API generated timestamps. All of these things are features that I can work around right now on my client while Dgraph works on making the generated API and the database service even better. Without further ado, let me show you what we have been building. This is our application as of recording in its beta form. I do not have time to do a complete walkthrough, so I'll just show off a very few quick features. We have started right here with a table view of our contacts. We could switch views to see these same contacts in other views. We plan to build even more views in the future. Of course, we can search our contacts by name in the search bar, as well as sort and select fields we wish to see. We can open a contact's mini profile by selecting the contact. I'm going to close this back for now. In the hideaway sidebar, which we can pin in place, we are able to select a different type of data to work with. Below the data type selection, we have our sources and filters. The contact source or list includes our team features. Contacts can be owned by a team and shared by other teams. Selecting a list of teams here changes the source of the contacts to only show contacts from the team of those sources. What I really want to show you though is the filters. We created a filter builder user interface that allows users to build their own filters. In this builder, a user selects either predicates or edges to add filters upon. In our filter we copied, for example, we see that we are filtering contacts by their type and also by their address state, which is in the edge. These filters can be combined with different logic and even nested with additional filters to make very complex filters. If we go back and apply this filter, we can see that the only contacts that match this filter are returned in the main view. These filters can be hidden and rearranged to adjust the view to the user's preference. We don't have time to show off more of our application's user interface, but we're excited that we are able to spend more time now building out this application instead of building out the API. Thank you for your time, and a big thank you to Dgraph for allowing me to give this presentation.
Thank you, Anthony. That was an interesting insight into how Dgraph manages to replace the 50,000 lines of GraphQL-related boilerplate. Okay, it's been a big morning, so let's all take a 5-minute break. Refill your drink, stretch, do what you need to do, and we'll be back in 5 minutes. See you then. Welcome back. This morning I mentioned that Dgraph users come from around the world. Naturally, the stories that our users tell also come from around the world. Our next speaker is Pan Gao, who is the chief search architect of one of the largest real estate companies in the whole world, KE Holdings. Think Zillow, but on an even larger scale. He will tell us how Dgraph powers search for real estate in the whole of China. That's over 200 million real estate listings. Now, don't be alarmed, the talk will be in Mandarin. So, we have provided you with English subtitles and slides in English. That means if you're listening and not watching right now, make sure to change tabs and read along with the subtitles. Everyone, please welcome Pan Gao.
大家好，我是高潘，然后我是贝壳找房搜索平台的负责人。今天我给大家分享一下分布式图数库在贝壳找房的应用实践。这是我本次分享的一个主要的提纲。 第一部分我是为做图数据库做一个简单的介绍，然后是如何对图数据库进行技术选型，然后最后是我们那个贝壳图数据库平台的一个建设，如何是做图数据库平台的建设，然后是我对图数据库 Dgraph 的做一些原理的介绍，然后我们对它做一些的优化，还有它本身的一些不足的方面，最后就是我们最后的一个后期对图数据库这块的一个未来规划。然后第一部分首先介绍一下特别是为什么我们贝壳需要图数据库。一个主要的原因就是我们贝壳行业图谱目前已经到达了一个非常海量的数据级别，目前有500亿的3元组。贝壳的行业图谱主要包含，因为贝壳主要是做一个那个房产那个资讯平台，然后撮合房产这种交易、二手新房租赁这种，所以贝壳的行业图谱主要包含，比如说我们的房源，然后客户、经纪人、开发商、小区、地铁、医院、学校、超市、电影院等等，有非常多的这种 POI 数据。然后在基于这个海量的行业图谱，我们会在上面去做很多的数据分析，包括或者是一些查询等等。比如说我们设想有这样的一个查询，我们想一个客户，我们想要找一套房子，然后这个房子符合需要满足这些条件，必须它的开发商是某某某，然后它的小区的绿化率要求大于 30%， 然后它周边200米要有大型的超市，然后500米内要有地铁，然后1000米内要有3甲的医院，然后2000米内要有升学率超过 60% 的高中，并且房价要在800万以内，并且它要被最近经纪人带看次数最多的房子。那这样可能是这种房子可能是一个客户想要的房子，但是它的查询条件大家可以看到实际是非常复杂的。那我们应该如果是有这样一个查询，我们需要满足这样的查询条件，我们一般是可以用什么数据库来解决呢？比如说大家最常见的 MySQL 或者 Oracle 这种可以解决吗？显然是不行的，对吧？我们有非常多的表，如果是用 MySQL 或者 Oracle 的话，那么我们可能会关联几十张表，比如我们需要关联房源表和客户表，再关联开发商、关联小区、关联医院，关联非常多的表，这样的话性能是非常差的，特别是我们在这种海量的数据集下面。然后如果是 ES 可以吗？ ES 其实也是现在非常火的一个搜索引擎，它可以对于这种查询检索来说，它是非常流行的。但是其实我们这种需求 ES 也是无法满足的，因为它的这种查询条件还包括，比如说它要搜100米内有3甲医院，500米内有地铁，这种距离我们无法把这种距离字段然后作为一个，因为 ES 一般都是一个非常宽的表做一个查询，然后像这种距离它是可变的，有的时候比如说我这一次需要查500米内，下次可能就要查600米内，这个字段我们是没法把它放到 ES 里面去建倒排索引的，所以 ES 也是不行的。HBase 显然也不行， HBase 它只是一个 KV 的存储，执行这种复杂条件的过滤分析也是不太适合。其实显而易见，这种是一个典型的图数据库的查询，我们可以把房源想象成一个点，然后旁边的就是它旁边有哪些客户，有哪些医院，有哪些学校，这都是它的边，然后这应该是一个图数据库非常适合的场景，比如说 Neo4j 这种。所以我们就需要一个首先我们需要一个图数据库来解决我们这种复杂查询，其次我们这个图数据库还必须能满足这种这种500亿级的海量数据的查询，并且它的性能也是需要一个比较高的。然后简单介绍一下图数据库。什么是图数据库呢？图数据库它不是一个存储图片，它虽然叫图数据库，但是它不是一个存储图片的数据库，而是它存储的主要是节点和关系，并且是以图的结构来进行存储和查询。它的应用场景其实也非常广泛，比如它有社交网络，比如说社交网络、计算机网络、道路网络、电信网络等等。然后比如说刚才我们说到那种复杂的关联查询，包括特别是这种搜索推荐的领域，以及说风控的预测、风险风控管理、业务流程、生物流程、公司或者市场结构，以及事件及其之间的因果关系或者其他联系等等，这些应用场景其实都可以用图数据库来解决，因为它们基本都是一些存储的一些关系的查询。这是那个 DB Engine 上的一个排名，其实我们从这个排名上也看到，图数据库领域其实是越来越火，从13年到现在，整个图数据库的一个趋势是发展非常迅猛的，因为它的应用场景也越来越宽阔，然后现在 特别是在现在数据量越来越大的很多场景，很多需要复杂查询的地方，都是需要多关联查询的，都需要图数据库来解决。这是其次，现在图数据库产品也非常多，这也是 DB Engine 上的一个图数据库产品的情况。我们可以看到我这只是截取了前20个图数据库产品，其实可以有非常多，大家看到，比如常见的 Neo4j， 然后 ArrangeDB、OrientDB， 然后 GraphDB、Dgraph， 然后 Jain 等等，图数据库产品其实也非常多。OK， 然后我们刚才简单介绍一下图数据库，以及我们贝壳为什么需要这样一个图数据库。然后剩下的问题就是说，我们现在其实刚才只是说我们最核心的一个场景，其实刚才也说了，图数据库的应用场景非常多。除了刚才我们行业图谱需要一个图数据库外，其实我们贝壳也有自己的风控平台，然后也有自己的那个其他的一些那个平台，他们都需要图数据库。那我们现在想的就是说，我们是不是应该搭建一个整体的一个图数据库平台，然后各个业务都可以直接来使用这个图数据库，而不是说每个业务，比如说我们现在行业图谱需要图数据库，我们就使用一套图数据库的基础搭建一套，然后到时候明天风控部门又使用图数据库，它又需要自己来搭建这么一套，这样的成本是比较大的。所以我们的想法就是说，我们可以搭建一个统一的图数据库平台，然后解决底层的这种图数据库的存储和查询问题，然后上层业务可以直接来使用，这样提升整个公司的一个效率。所以我们搭建图数据库平台的第一步，那就是说我们必须先做一个图数据库的技术选型。上面刚才也看到，我们图数据库产品其实很多，那到底哪一种才是我们最需要的？所以我们进入第二部分，就是图数据库的技术选型。那我们作为一个图数据库技术选型，到底需要考虑哪些因素呢？我们现在主要考虑就是这8个部分。首先第一个，它必须是一个开源的产品。因为我们这个开源的产品，有2大优势。第一个优势肯定是它的成本会比较低一些，因为商业化的产品一般都是那个收费可能会比较高，然后开源的一般我们都可以直接免费来使用。其次就是一个在国内我们会考虑一个安全问题，因为开源的产品源码都是可见的，我们可以不用顾虑它有什么后门啊、安全之类的问题，不用担心自己的数据会泄露等等。这是所以开源是一个必备的条件，这是我们第一项要考虑的。然后其次就是这个图数据库产品的一个成熟度，它需要是一个比较稍微成熟一些的产品。然后就是说它必须要有一个很强的很好的扩展性。刚才也说到，我们数据量特别大，会有500亿的量级，所以它必须支持一个高扩展，单机肯定是无法支持的。其次就是它的文档需要是一个比较完善的，然后我们可以快速的去学习，快速去掌握它。然后是它的性能必须是比较高的。我们一般用这种做图数据库查询的话，就希望都是可以秒级的反馈，所以它的性能必须要比较高。然后其次就是稳定性，因为刚才说，首先它是需要支持高扩展，那它必然是一个分布式系统，然后所以它需要支持一个有一个比较高的稳定性。当我有某些节点挂掉的时候，我们可以对主体的业务查询和写入都没有太大的影响。还有一个就是运维成本，运维成本可能是大家比较容易忽略的一点，但其实运维成本也是需要考虑进去的。如果说我们这个系统搭建起来之后，后期的运维成本非常高的话，对于我们整体的研发效率也是会有影响的。后面我会举一个这样的例子。然后最后就是它的一个易用性，我们希望这个产品是一个非常简单易用的，可以快速的上手，快速的掌握它。然后基于这些条件，我们简单的对 DB Engine 上的一些图数据库产品做了一些粗略的筛选。其实光是跟那个开源一下就可以筛选出一部分，然后其次就是一些从开源和扩展性，然后这一方面就可以筛选掉大部分的图数据库产品。最后我们粗筛了这么几个，一个是ArrangeDB， 还有是 OrientDB， 还有 Jain Graph， 还有 Dgraph 这几个。然后 Neo4j 它虽然是一个商业化的，然后但因为它它是一个图数据库领域的一个长期的一个领头的吧，所以我们主要在这儿它大家和它做一个对比，所以把它也放在这儿。 然后所以我们主要对比的就是这5款数据库吧 ，Neo4j、OrientDB、AlgoDB、JSON和 Dgraph。然后我们对它做一个首先对它做一个简单的对比。Neo4j 首先是 Neo4j 大家就比较熟悉了，它是一个最早的做图书库这边，然后是2007年就开始，它是社区版是开源的，然后企业版是收费的，然后数据模型也是 Graph， 直接就是支持 Graph 图数据库 Graph， 并且然后现在还不支持 Circle， 它的存储系统是一个原生的，并且它企业版是支持分布式的，它的相关文档是非常多的。然后是 OrientDB 是2010年release 的，然后它也是一个开源的，但是它的那个 Web UI 管理模块是收费的，它的数据模型支持 Doc、Graph、LKV， 然后它的查询语句是一个类 Circle 的，存储系统也是原生的，分布式是后期支持的。然后 OrangeDB 也是一个开源的，然后它的一个区别就是它不支持 Circle， 然后它的存储系统是用的 RocksDB， 然后分布式也是后期支持的，相关文档也是比较多。然后是 JSON-Graph 是 JSON-Graph 和后面 Dgraph 都是近几年，比如2017年和2016年才开始发布的，然后他们两个也都是完全的开源，并且完全的免费的，数据模型也就是完全支持 Graph， 然后 Circle 目前都是不支持，然后存储系统区别有一些区别 ，JSON-Graph 存储主要是依赖于其他的存储，比如说 HBase、Consider 这些，然后 Dgraph 的存储是他们自己原生的一个存储，分布式两者都是原生支持的，然后但是因为他们俩都比较新，所以相关的文档会和前面几个数据库比起来会偏少一些。然后我们基于这个对比可以看到，那个后面4种其实都符合我们的，然后但是我们对 OrientDB 和 OrangeDB 做一个进一步的调研，发现因为他们的我们现在其实因为我们数据量比较大，所以对分布式的要求会比较高。然后我们经过简单调研之后，发现 OrientDB 和 OrangeDB 因为他们前期都是一个单机的图数据库，然后是后期才开始支持分布式，所以它对于分布式这块支持的不是特别完善，而不像是 JSON-Graph 和 Dgraph 它从设计之初就开始基于分布式开始设计的，然后原生支持分布式，所以他们的分布式都要比 OrientDB 和 OrangeDB 要做得好一些，所以我们后面把我们的主要的倾向放在 JSON-Graph 和 Dgraph 上，主要考虑这两个，基于这两个做一个深入的那个调研和对比。然后我们先看一下 JSON-Graph 的一个整体的一个架构。这是 JSON-Graph 可以看一下 JSON-Graph 它是首先它是既支持 OLAP 又支持 ORTP 的那个查询，然后 OLAP 也主要是通过 Spark、Hadoop 这些的和它的结合来做的，然后 OLAP JSON-Graph 内部实现了一些对它管理的 Manage API， 然后 TinkPop 的查询 API， 支持 Grammarly， 然后自己有它的自己的那个 API 的模块，API 层，然后数据 database 数据层，然后它的存储层。然后一个比较重要的，刚才也提到的，就是 JSON-Graph 它的存储层，这是主要是 JSON-Graph 一些模块，但是它的存储层主要是依赖于第三方的，比如说它存储可以依赖于它是没有自己的存储系统的，它必须依赖于第三方的存储，比如 Consider、HBase、伯克利 DB 等等。然后或者说另外如果说需要做一个那个索引的话，JSON-Graph 也是需要依赖第三方，比如或者可以依赖第三方的 Elasticsearch， 然后 Solr 或者 Lucent 等等。就是说它的存储和它的索引模块都是需要依赖第三方，而不是它自己本身的，这是它的一个比较大的特点。然后其次是 Dgraph， 这是 Dgraph 的一个架构。Dgraph 的那个 Dgraph 我可以简单介绍一下 ，Dgraph 它分为主要是四个模块，然后第一个是 Zero 是一个管理层，它是相当于是个集群的大脑，用于控制整个集群，将服务器分配到同一个组，并且做一些数据的均衡，然后它主要通过 Graph 来进行一个选举操作。然后其次是阿尔法模块，阿尔法就是核心的那个执行模块，它主要负责数据的存储和数据查询，包括位次的托管、一些索引的建立和索引的管理等等。然后还是 Graph， 多个阿尔法会组成一个 Graph， 然后数据会分片存储到不同的 graph， 每个 graph 内的数据是通过 graph 的保证数据的一致性的，然后不同的 graph 之间的数据是不一样的，是属于一个数据的不同的分片。最后是 Reto 是 Dgraph 提供的一个可视化界面，用户可以通过这个界面来执行查询或者更新修改 schema。大家看到 Dgraph 的一个架构是相对于简单的，我们这块的底层是通过 Zero 对整个集群做一个管理，然后中间是阿尔法不同的阿尔法组成不同的 group， 然后执行整个数据的存储查询，然后上层是连接层，通过 Reto 或者是 gRPC HTTP 来对下面的阿尔法节点进行一些查询，然后更新等等，这是 Dgraph 的一个架构。OK， 然后这上面是两个 CNS Graph Dgraph 架构的对比，然后我们又对它进行那个两个图水库分别做了一个性能的压测，做一个性能对比。我这边我不具体说，主要我们可以看到，我们查询性能压测我们分为写入性能、查询性能，写入又分为点和边，还有初始化。可以看到写入的时候 Dgraph 特别是边的话和 GNS Graph 写的速度测试差不多，点的话会比它快一些，然后并且 Dgraph 提供一个初始化写入的功能，会非常快，每秒可以写到20多万的速度。然后对于查询来说，我们看到前面的这些简单的查询，比如说点的查询、一度关系的查询一度那个点的连接，其实这些 GNS Graph 和 Dgraph 的查询性能都差不太多，区别不会很明显。但是我们发现越到后面的复杂查询，比如查询一度类所有的节点，或查询2度、查询3度，这个时候 Dgraph 的性能要远高于 GNS Graph。比如说查询2度的内所有的点和属性的时候， GNS Graph 需要300多毫秒，而 Dgraph 依然只需要3点几毫秒。包括或者查询3度 GNS Graph 需要一个基本上是一个线性增长，它会到700多毫秒，然后 Dgraph 依然可以在几毫秒之内完成。然后我们对它做一个整体的那个对比，做完性能压测之后，我们看一个整体的对比。Dgraph 经常是在架构上 ，Dgraph 是一个原生支持分布式的一个系统，然后 GNS Graph 它的分布式系统主要是构建于其他分布式数据库之上，比如刚才说到 HBase 或者 Consider。然后对副本上 ，Dgraph 它是一个强一致的原生支持强一致的，通过 RAW 来实现。然后 GNS Graph 也是依赖底层 DB 的一个副本一致性。然后数据均衡上 ，Dgraph 是一个自动的，然后 GNS 同样是需要依赖底层 DB。然后语言 Dgraph 支持是 GraphQL， 然后 GNS Graph 是支持 Genomics。然后对于全文检索、正则表达式、地理位置检索还有可视化这些 ，Dgraph 都是原生支持的。然后 GNS Graph 主要都是依赖于外部检索系统，比如刚才说到 ES、Lucene。然后就是我们前面提到的一个维护成本。然后因为我们前面说 Dgraph 它基本上它的都不需要依赖于三方系统，它的存储也好，它的索引也好，它的那个查询也好，都是自己的一个原生支持的系统，所以它的整个维护成本是比较低的。但是 GNS Graph 它的维护成本是非常高的，因为 GNS Graph 它的存储系统是需要于依赖于 HBase 或者 Consider， 所以大部分人可能是用的 HBase。所以如果需要搭建一套 GNS Graph 的集群的话，我们首先需要搭建一套 HBase 的集群，是因为它需要依赖 HBase， 而 HBase 它又依赖于 HDFS 和 Zookeeper， 所以造成我们要搭建一个 GNS Graph 集群需要搭建很多三方的系统，比如说 HBase 啊、Hadoop 然后 Zookeeper 这些系统都是必不可少的。然后如果说我们要做一个全文检索的全文检索的话，还需要再搭建一套 ES， 然后通过 ES 来进行一个全文检索。那这样的话 GNS Graph 需要依赖于非常多的三方系统，所以它的整个运维成本是非常高的。然后对于写入性能方面 Dgraph 也是比较高的，然后 GNS Graph 是比较高。然后查询性能 GNS Graph 是简单查询、复杂查询都非常快，然后Dgraph 是简单查询、复杂查询都很快，但是 GNS Graph 它的是复杂查询会比较慢。所以综合这个对比，大家可以看到整体而言 Dgraph 是要比 GNS Graph 要比较优一些的，因为首先它的性能，首先它的分布式各种都是原生支持的， 然后其次因为它的存储也是原正，所以它的维护成本会非常低，然后它的读写的性能也会比计算graph会高一些。然后综合这些，我们就决定我们最后的基础选型是用 Dgraph 来实现。OK， 然后确定完基础选型之后，就进入到我们第3部分，就是那我们确定我们使用 Dgraph 之后，我们如何搭建起我们贝壳的一套整个的图数据库平台呢？那要搭建这个图数据库平台，首先肯定是需要做一个这种，首先需要我们把 Dgraph 的集群给搭建起来。然后 Dgraph 的集群，我们现在是通过，这是我们搭建的一个示意图。我们这个简单示意图，比如说我们现在 Dgraph 我们现在都是通过那个 K8s 加 Docker 虚拟化管理的。这边比如说我们使用3台服务器，服务器1、2、3，然后每台服务器上我们启动了4个 Dgraph 的进程。然后第一个 Dgraph 进程是启动的 zero 模块，然后用它的每台机器都会启动一个 zero 的节点，然后它们会组成一个 manage 管理层，然后对整个集群做管理。然后每台机器我们会启动3个阿尔法节点，但需要注意的是每个机器的阿尔法它是有启动顺序的。必须先在机器1上启动一个阿尔法，然后机器2上启动阿尔法，机器3上启动阿尔法。那这样这个时候，这3个阿尔法会自动组成 group 1，然后再启动4、5、6，然后它们会自动组成 group 2，然后7、8、9会自动组成 group 3。这样的话，整个集群就搭建好了。然后前面说 group 1里面的三个阿尔法，它们的数据是保证那个主辈高可用的，它们的数据是一致的。然后Group 1、Group 2、Group 3，它们之间的数据是不一样的。比如说一份数据会分成3个分片，分别会存在 Group 1、Group 2、Group 3里面。然后在 Group 1里面，这个数据会分别阿尔法1、阿尔法2、阿尔法3，所以会形成3副本，保证一个它的数据的高可用。然后这是我们 Dgraph 启动的一个命令。大家也可以看到，这就是我们刚才前面说 Dgraph 的维护成本会非常低，因为它的整个非常简单，它整个 Dgraph 只有一个 Dgraph 的一个可执行文件，然后它启动的时候，比如大部分都不需要改太多配置，大部分都可以通过启动参数来设置。比如说我们要启动 zero 的时候，直接是 Dgraph 0， 然后设置一下副本数，就是比如 replic 3，就代表我们整个集群的副本都是3个。然后在 Dgraph 的阿尔法就代表我们启动一个阿尔法节点，然后再只需要指定一下 zero 的地址就可以了。启动整个 Dgraph 的大集群的搭建非常简单，只需要这几个命令就可以完成，不需要像计算graph一样，我们需要搭建 HBase、搭建 Hadoop 等等。这是它的一个主要的优势。OK， 然后集群搭建起来之后，我们就需要把数据导入到 Dgraph 集群里面去，然后为了提升，因为我们是一个刚才前面说我们是一个希望搭建一个图数库平台这样的一个角色，所以我们必须要有可能会有不同的业务方都往我们这里面去写导入数据。那我们如何提升各个业务方的一个导入数据的一个成本或者说性能和效率？所以我们我们开发了三种那个导入的数据流，分为比如说初始化的数据流、实时的数据流、批量的数据流。初始化的数据流主要是针对那些它需要有大量的历史数据，需要初次使用图数据库，然后它有大量的历史数据需要初始化一次性批量的导入到 Dgraph。这个时候它的特点就是它的历史数据会非常多，然后这个时候它需要非常快速的把这些数据导入到 Dgraph 集群里面去。这个时候我们可以忽略它的查询，并且这个时候是不需要做查询的，所以这个时候我们可以通过 Dgraph 的，主要是利用 Dgraph 的 bulk loader。初始化的数据流，我们是会有一个 Spark 的任务，因为大部分原始数据都在 Hive 或者 HDFs 里面，然后我们通过 Spark 的任务做一个 ETL， 把数据从 Hive 里面拉出来，做一个 ETL， 直接生成 Dgraph 的一个 RTF 要求的一个 RTF 格式，然后通过 Dgraph 的 bulk loader 直接加载 RTF， 然后生成 Dgraph 的一个存储文件。对于这种初始化的数据导入的性能是最高的。然后我们把历史数据导入到集群之后，当然第二步就是在日常中业务一定会有实时更新或者批量更新的。那对于实时更新，我们是会有一个 data acceptor 的服务，然后 业务方客户或者用户可以把他的数据，然后通过我们这提供一个 RESTful 的接口，可以把他的数据通过这个接口往我们这个接口里面去推送，然后我们这个接口 Data Acceptor 会接收用户的数据，然后写到卡夫卡做一个缓冲，然后还有一个对 Graph Import 的程序，从卡夫卡读入数据，然后实时的写入 Dgraph 集群，这是实时的数据导入。然后还有一些批量的数据导入，批量数据流会比实时的数据流会大一些，比如一般常见的就是说比如说实时一般针对于平时业务方白天它会有一些实时更新，然后批量可能就是晚上，比如说晚上它会做一个全量的更新，类似这种，所以这种会需要使用批量数据流，它的性能会比速度需要比实时会高一些，它的数据量也会大一些。然后批量数据流也是我们通过一个 Spark 任务，将用户 Hive 或者 DB 里面的全量数据通过一个 Spark 任务，然后也写到卡夫卡，然后 Graph Import 读取卡夫卡中的数据，然后再批量的写到 Dgraph 集群。这是我们整个输入平台一个数据写入的那个模块。然后集群搭建好，数据也写入到集群，然后就是我们最重要的如何把数据从集群里面查出来。这是我们通过 Dgraph Reto 提供的一个可视化界面 Reto 查询数据，把数据查出来的一个例子。我们这个例子是，比如说我们只要需要查询名字里面包含秀源，并且绿化率大于 30%， 我们需要查询这样一个幼儿园，它的名字里面包含秀源，并且它的绿化率大于 30%的小区的附近的1000米的幼儿园。这是查询一个小区的名字需要包含秀源，并且它的绿化率大于 30%， 并且它的附近1000米需要有幼儿园，是这样一个查询。这样查询还是比较复杂的。然后我们在Dgraph进行查询之后，基本上就可以得到结果。这边是它的查询语句，右边是真实结果。这些小区都是满足这个条件，它们的名字里包含秀源，它的绿化率大于 30%， 并且小区附近1000米会有幼儿园。然后其实大家可以看到，这是就是刚才那个语句 GraphQL， 这是 Dgraph 提供的一个语句，它需要，然后这是它的 query 里面需要它的名字里面包含秀源，并且它的小区绿化率大于30，然后它的距离最近的有1000米内有幼儿园，这是Dgraph 的一个查询语句。其实我们觉得这个语句还是稍微会复杂一点，需要一些学习成本的。然后我们可以对比一下 Grammy 的查询语句吧。然后 Grammy 它是这样的，然后 has 同样是 name， 然后包含秀源，然后绿化率基本 has as， 然后也是距离小于1000米，然后 select， 这是 Grammy 的一个查询语法，也是需要有一定的，虽然它会稍微简单一点，基本它是一个函数式的查询，也是同样也是需要一些查询那个学习成本的。然后我们在想，那个查询，既然我们是提供一个图数据库平台，那我们的查询也是需要尽量的，就像我们前面说到的，我们需要是一个易用的，那需要就是说，我们用户可以非常快速的上手，快速的学习，不需要太多的学习成本。那我们对于这两种语言都是需要有一定的学习成本的。然后我们想，是不是可以有一套标准的 circle 来对图数据库进行一个查询？因为基本大部分的研发肯定是都会对 circle 会比较熟悉，基本上对于 circle 不需要太多的学习，所以我们针对 Dgraph 设计了我们自己设计到一套 Graph Circle 的查询语言，然后是这样的，比如 select 小区名字，然后绿化率，然后幼儿园的名字，然后 from 这个关系，然后 where 它的名字里面包含秀源，并且绿化率大于多少，然后距离幼儿园的距离小于1000，这是我们自己设计的一个 Graph Circle 的查询语言。可以看到它的其实是相对于前面两种语言都比较简单一些，并且大家也会更熟悉一些，基本上不需要太多的学习成本。这是我们具体设计的一个我们自己 Graph Circle 的一个语法规范吧。它可以 select 点的名称、边的名称，然后 select 关系，然后也可以执行一些 count、agree 解释，然后包括可以查询最短路径，查询 n 度关系，然后 from 这是参考 cipher 的一个语法，可以查询我们点到边的关系等等。然后 where 里面包含一些常见的过滤条件，然后同时我们也支持 grow by、having、order by、limit 等等。OK， 这是我们通过一个我们自己的 ground circle 然后查询的一个例子，可以看到我们直接通过我们 circle 可以得到这样的一个 RESTful 的结果，这是我们需要刚才满足的那些幼儿园。OK， 然后这是就是我们整个集群搭建完，然后数据流和查询都建完之后，这是我们相当于我们整个数据库平台的一个整体架构。然后上层是我们有一个网关，统一的网关会对所有的流量进行一个健全分发、限流、熔断、降级。然后网关之下会有我们的主要的数据流模块和查询模块。数据流模块支持全量数据导入、增量的数据导入，支持卡夫卡做缓冲，然后支持有 Graph Import 从卡夫卡里面读数据，然后写到 Dgraph 集群。然后我们的查询层同时支持刚刚说，同时支持 Dgraph 的原生语法 GraphQL， 也支持我们自己的更简单的一个 Graph Circle。然后他们通过 Graph Client， 然后连接底层的 Dgraph 集群，然后执行一个查询。然后我们的整个 Dgraph 集群都是托管在我们的虚拟化平台 Docker 和 KVS 容器化管理部署的，整个运维管理成本会非常低。然后在最右边，我们有整套的服务治理的框架，包括我们注册中心、配置中心、负载均衡、熔断降级、链路追踪、监控报警等等。这是我们整个图数库平台的一个架构。然后我们再介绍一下Dgraph 的一个简单的原理介绍，然后我们对它做了一些简单的优化，以及它有一些哪些不足的地方。首先是 Dgraph 的一个原理 ，Dgraph 它的存储引擎使用的是 Bagger， 然后是 Dgraph 自己实现的一个 Benjer， 然后Dgraph 自己实现的一个高效的持久化的，也基于 LSM 的建值数据库，使用 Go 语言纯写的，然后是随机读写会比 RocksDB 快 3.5 倍，这是它自己的存储引擎。然后它的一个比较有特点的地方是 Dgraph 的一个存储结构，它的主要底层和其他图数库一样，基本都是一个 KV 存储，但是大部分图数库的 KV 存储都是它的 K 都是一个点，然后 V 是它的边或者它的属性。但是 Dgraph 不一样 ，Dgraph 它的存储结构，它的 K 是位词，也就是边，然后它的 value 是一个那个 value 是它的点或者是它边的一些属性等等。比如说我们要存一个我的朋友的关系，它的 K 是首先它的前缀 K 是 friend 是我们的这个关系，然后是我的 me， 然后再是我的所有的朋友会存在一个 value 的 sort 一个有序的list 里面 person 1 person 2 person 3，这些都是我的朋友，这是它的一个存储结构。然后数据分片 Dgraph 是根据位词的分片相同，所以因为它是 Dgraph 它的那个 K 是位词，所以它也是同样的，它的分片就只基于位词的分片。相同位词的数据会按照顺序存在在同一个节点，主要是减少 RPC 调用，后面我们会介绍一下，然后会定期做一个数据的均衡，这个主要是它的 rebalance interval 来参数可以决定，然后 grow 会根据 replica 阿尔法的启动顺序会来决定。然后是 Dgraph 的一个高可用 ，Dgraph 每个 group 至少会有3个阿尔法，然后互为副本，然后通过 rough 的协议保证它们的一个强一致性。然后其次 Dgraph 主要是通过 write apply level 来预写日来保证那个数据的一个高可用。我们简单介绍它的这个 Dgraph 这个存储的原理。比如说我们这个查询例子要查询我所有的朋友中就职于贝壳的人。那对于普通的一些其他的数据库，比如 Graph 这种，它的 K 一般都是点到 K 的一般都是点，然后 value 是它的边。然后对于其他的数据库可能就需要，比如说我们第一步是需要通过查询出我所有的朋友，这个可以 在一个节点上一步就可以得到我所有的朋友关系。那在查询二度朋友关系，就需要做一个广播的子查询，我所有的朋友，对于我的每个朋友，一个广播查询，我的每个朋友都再去查询一下我们每个朋友的二度朋友，查出我二度朋友的所有朋友，这是需要做一个广播查询，然后再做聚合出我朋友所有朋友的朋友，然后再要查出他们所有他们的就职公司，那就需要对这所有二度朋友再做一个广播查询，查出他们所有的几个就职的关系，然后最终再进行一个过滤，然后过滤他们所有的就职公司是贝壳，然后再做一个聚合，就得到所有我朋友的朋友中就职于贝壳的人。所以看到它的整个查询还是比较复杂的，需要做2次广播子查询，然后做一个聚合。然后做广播查询的话，其实就有一个非常大的弊端，就是说因为它是广播查询的，所以说对于它需要很多的网络 I/O 网络交互，并且同时稍微有某一个节点，如果说出现那网络阻塞、网络拥塞的话，这个查询它就可能因为一个木桶效应变成查询的短板，最终的查询性能都会被这一个点给拖慢。最终，所以我们看到Dgraphs它对于深度的，比如2度查询、3度查询，甚至更高维度的查询的性能就会极大的降低，这主要是它们这个原因。但是 Dgraph 它不一样，主要是它的 K 是它的边，所以它对于这种查询，它只需要，比如说第一步它查所有朋友的朋友的话，它不需要做广播查询，因为所有的朋友关系都存在相同，刚才前面说的，因为它的存储结构，它所有的同一种关系都在同一种节点上，所以查询2度朋友的朋友只需要在发到存储朋友那个节点上一次查询，一次 RPC 就可以查到所有朋友的朋友，然后再通过一次 RPC 就可以查到所有朋友的一个就职关系，然后对这些关系再有一个结果级的过滤，就会得到我所有朋友的朋友中就职于贝壳中，所以只需要2-3次的网络 RPC 就可以完成这次查询。所以它主要的优势就是它可以避免一个广播查询，一次网络调用就执行一次连接，然后基于这个原理可以做一个低延迟的查询，并且它的查询性能基本上是可以预测的，所以它的整个性能会远高于Dgraph。然后就是导入在写入方面一些优化吧，我们对包括 loader 进行导入优化，包括 loader 原来因为我们的数据量比较大，500亿，我们发现用使用包括 loader 导入的话，经常会出现内存溢出的问题，所以然后它的性能也会比较慢。那这原来包括 loader 基本上主要是一个单机多线程的模式，主要在单机上使用多线程进行 MapReduce 构造 Dgraph 的一个 RDF 存储文件。但当中的数据量特别大的时候，我觉得这种性能速度还是比较慢，并且它会有内存溢出的问题，所以我们对它做了一个分布式的导入改造。我们把原来的单机多线程的包括 loader 写入改成多机多线程，首先通过对这个 RDF 做一个 partition 操作，然后给它做一个一致性哈希分成多个数据分片，然后每个数据分片就可以分发到不同的机器上，然后每台机器并行的执行 MapReduce 操作，然后可以充分利用多台机器的性能，然后这样快速的提升导入的速度。通过这种方式分布式的改造，我们行业图谱500亿的3元素导入时间由原来48小时降低到15小时，大概提升了3倍。同时我们增加了一个数据均衡的开关，这样主要是为防止业务在高峰期间，因为这种数据均衡还是比较耗资源的，并且对于 Dgraph 而言，在数据在均衡的时候写入可能会对写入会有影响，所以我们增加这种数据均衡的开关，然后在业务高峰期我们会把数据均衡给关掉，避免它进行自动的数据均衡，然后影响我们实时的写入，然后比如到晚上业务低峰的时候没有查询的时候，我们再把它打开，然后让它在夜间的时候执行这种数据均衡的操作。然后是简单说一下其实说我们前面说了很多，其实主要都是说的一些 Dgraph 的一些优势，比如它的运维成本低，比如它的查询写入性能都非常高等等。但其实Dgraph 也不是说一个非常完美的那个系统，它也有一些自己的优势不足，当然肯定是不同的系统都会有自己的优劣势，优缺点。Dgraph 主要是有这些，目前还有需要可以提升的，比如说目前 Dgraph 还不支持多重编，对于任意一对顶点相同标签类型的编只允许存在一条，然后这样是 对于一些需要多重编的场景来说，可能是会有一些影响的。比如贝壳的带看，有一种比如说经纪人带客户去看一套房子，带看是一条边，而经纪人和房子可能他们是2个相同的标签的顶点，然后带看是一条边。对于Dgraph它就只允许存在这样一条边的，但是其实这种带看操作是可以有多次的，我可以在10点钟带看一次，然后第2天又带看了一次，这种是需要多重编的，这个目前 Dgraph 还暂时不支持。然后第2个就是 Dgraph 它的这是它的开源版本，一个集群只支持一个图，目前是企业版本可以支持多图，如果一个集群只支持一个图的话，如果像那个图比较多的话，可能会需要过多的集群，这是一个不好的地方。然后其次就是 Dgraph 可能比较新，它现在和大数据库生态的兼容不太够，如果是通过 Spark 直接往 Dgraph 写的话，比较容易出现 overload。然后其次也是就是说，因为 Dgraph 是按边去做数据分割的，所以它一个边同一个边那个相同边的所有数据都会在同一个节点上，所以会比较容易出现超级边。当然了，其他的数据库如果这个都会存在这种问题，如果说按点去做分片的话，也同样会容易出现超级点的问题。OK， 然后再简单介绍一下，说明一下我们未来的规划。刚才说我们前面基本上是简单介绍我们整个图数据库平台的一个搭建过程，然后后期的话，我们基本上是一个是会进一步对 Dgraph 进行一个深入的学习，然后对它的性能稳定性做一个优化，然后甚至会对它做一些源码的改进。然后就是说我们整个这个图数据库平台会作为 Dgraph 作为我们整个搜索中台的一个基础引擎，支持我们各种图数据库检索的需求。然后并且我们会把这个图数据库平台接入我们之前的一个搜索云平台，然后可以通过界面化操作快速的接入，并且快速进行配置管理，简化我们整个运维。比如说对图数据库 Dgraph 节点进行一些伸缩扩容，然后重启都会通过界面化操作。其次就是通过利用我们图数据库的 Dgraph 图数据库查询能力，增强我们整个的搜索功能，提升搜索效果。然后再就是当我们整个平台完善之后，然后去支持我们其他更多的业务，比如行业图谱、关系图谱、贝壳其他的一些知识图谱、风险风控管理等等介入其他的各种图数据库的需求那个业务场景。这个是我们后期的一个规划中的一个大体的架构图，因为我们整个其实是一个搜索平台，后面我们会整体做一个搜索中台，然后 Dgraph 会作为我们整个搜索中台会分为这么几层，最上层是我们搜索云平台，会作为一个业务接入和运维配置管理的一个平台，提升业务接入效率。然后效果平台主要是会做一些查询上面的一个效果优化和算法去结合，然后算法平台主要是通过一些模型特征的管理。然后下面就是我们三个主要的一个检索引擎，比如有文本检索引擎 ES， 然后图数据库检索引擎 Dgraph， 还有项目检索引擎 Face， 三大引擎去支持我们整个上层的各种的查询需求，然后底层都是统一通过我们的容器化平台多核加 KPS 进行对这3种引擎进行一个整体的管理。右面是我们刚才前面也提到整个服务治理的框架，保证我们整个搜索中台的一个稳定性。OK， 这就是我今天介绍的主要内容，感谢大家。
Thank you, Pan. That was definitely an in-depth look at how Dgraph is powering one of the largest real estate marketplaces in the world. Here's a fun fact about KE Holdings. They went public last year and raised more than $2 billion from their IPO. Speaking of facts about companies, our next speaker compiles facts about companies and then forms a knowledge graph of facts. Mark Boxall is the principal software engineer at FactSet, and he's here to talk about how FactSet uses Dgraph and DQL to build a point-in-time model of financial objects. Please welcome Mark Boxall.
Hi, my name is Mark Boxall. I'm a principal engineer at FactSet. And today I'm going to talk to you about how we used Dgraph and DQL to build a point-in-time model of financial objects. So the universe of financial objects, it includes things like countries, companies, securities, stock exchanges, indexes, funds, commodities, and a lot more. These objects are related in many different ways, and many of these relationships can change over time. So with the universe loaded into Dgraph, our clients can now easily explore these objects and their relationships as they exist today or at any time in the past. So in this talk, I'll give a quick tour of the actual data model. I'll talk about why we wanted to use a graph database and why we specifically chose Dgraph. I'll give some details of our Dgraph cluster, and then we'll run through some query examples. So first, let's dive into the data model and start nice and simple. We have just two nodes here, a company and a country, and they're connected with an edge called is domiciled in. And domiciled is really just the home country for a company. So we can see here that MarineMax is essentially just a US-based company. In this next slide, we're looking at a second company, Boatyard Inc., which is controlled by MarineMax. And that just means that MarineMax has 50% or more ownership of Boatyard Inc. and therefore controls it. Another way of expressing that is it's just a subsidiary. So Boatyard Inc. is a subsidiary of MarineMax Inc. And now expanding out to all of the first level subsidiaries. I don't expect you to read all that. It's just to kind of show the shape of the data. It looks as follows, and then including all the subsidiaries, all levels, it looks like that. And the deepest subsidiary is 3 levels deep here. And some other examples could go as deep as 20 levels of subsidiary. And in this slide, I'm including the securities now, and let's zoom in on some of those. So we can see MarineMax has some bank loans, some revolving lines of credit. It also has a fixed term loan, and it has a common stock. So zooming in on that common stock, we can see it's connected back to the company with is issuer of edge. So we say that the company is the issuer of the common. And typically, and in many cases, a common stock may have all kinds of other derivative securities that are based off of it. And the terminology we use is underlier. So we say that the equity is the underlier of the derivatives. In this case, we have an options contract, which has a strike price of $45 and expired on March 13th. Oops, March 19th. And zooming out, we can see the full picture. We have the common stock over here with all of the different options contracts that are derived from it. MarineMax in the middle here with all of the subsidiaries extending off to the left. So let's look at some of the other nodes, interesting nodes in the data model. We have things like the companies, the governments, various different kinds of securities like P notes, money market securities, mutual fund share classes, ETF shares, etc. But there are also some, perhaps less expected nodes like cheese and coffee. And these are included in the data model because these are the commodities that underlie all kinds of futures contracts. Looking at the edges, we've already talked about is controlled by, is issuer of, and is underlier of. A couple of other notables are tracks. So if you have a mutual fund or an ETF that's tracking a particular index, we link them up with the tracks edge. And is advisor of, if we have a asset management company that's advising on a mutual fund, the company, the advisor company, and the mutual fund will be linked up with an is advisor of edge. And now onto the properties or the value edges in Dgraph. A lot of these are just symbols and identifiers that are used to identify securities, but also to identify companies. So something like QSIP, CDOL, ISIN, ticker, these are all very common security level identifiers Something like legal entity identifier is a company level identifier. So typically our clients have access to these symbols, and they'll use these as a starting point to locate an object in the graph before starting any traversal. Is public is a flag that we put on the company nodes, and it basically just separates the private companies from the public companies. And this is a point in time property. So, a company would start out private, and then possibly a few years later, it might go public. And then potentially even, in some cases, it could even revert back to being private several years after that. So why did we want to use a graph database? Hopefully it's becoming clear based on the shape of the data that this universe of financial objects really does naturally form a graph structure. And in fact, there are many more relationships between the nodes that I wasn't showing that make it even more graph-like. So that was one reason. It was a natural fit to the data, but also ease of querying. And we realized graph databases come with these purpose-built query languages that are really designed for querying heavily connected data in a very concise way. And the queries that you use are a lot more concise, a lot cleaner than something like SQL, where your the meaning of the query, what you're trying to achieve with the query, that very quickly gets lost in all of the joins. And then the final point, the final compelling thing about graph databases is we felt that with a graph database and with a well-designed data model, it should actually be feasible to open up the backend database to all of our internal users and application developers, and allow them to explore the data on their own and write their own queries. So we're really talking about like full self-service to the backend database, and this really wouldn't have been possible with our old relational setup. There's just too many. It would require too much special knowledge of the tables schema, and there would just be too much scope for problems and bad assumptions. So this wasn't something we were comfortable of doing on the old setup. And the self-service model will really eventually allow us to retire hundreds of endpoints that we have today that literally exist just to bridge the gap between the applications and the backend database. So that was why we were interested in graph databases in general, and here are the reasons why we ultimately went with Dgraph. Open source, of course, that was a big one, and it's been really nice to be able to create issues directly on the Dgraph GitHub. It's also been really convenient to be able to pull and locally build unreleased code if we wanted to, check out new and upcoming enhancements and try out bug fixes. And also, we like the fact that it's, less of a black box. And if you want to figure out how something's working internally, we can go look at the code, crack it open, try to understand what's going on. Especially if we're trying to optimize for performance, it can be really valuable to be able to have that visibility into the code. We definitely like the scalable distributed architecture. And of all the graph languages out there, we really felt DQL was one of the more intuitive and something that we felt comfortable putting in front of our application developers with a good degree of confidence that they'd be able to start writing queries without a huge learning curve. And one of the unique features of Dgraph that we really liked was the facets feature, because we realized that we could use that to implement a true point-in-time graph, and that was something that we always wanted to do from the outset. We realized that these financial objects aren't static; they're continually evolving. Companies keep merging, spinning off, acquiring other companies, and every day new securities get issued. Other securities mature or expire, so things are constantly changing, and we wanted to reflect that in the data model. Even something like countries are not static. So I looked it up yesterday. Since 1990, there were 34 new countries that came into existence. So nothing is really static. And so a little bit more on the facets. So Dgraph facets are just attributes that you can associate with an edge. So what we did was for every edge in the database, we associated a start time and end time facet, which defined the interval over which the edge existed. And then at query time, we can filter on those facets so that clients can look at the graph exactly as it was as of a particular point in time, either today or any time in the past. We liked the overall reliability of the product. During testing, we didn't see any unexpected or unexplained crashes. And it did pretty well under high load. So that was a big plus factor. And it gave us great performance for our use case. And we definitely liked the flexible schema. We realized that our data model was going to continue to evolve. We're going to want to add new node types, new edge types. And with Dgraph, that's certainly possible with minimal disruption. We definitely wanted to be able to host on the cloud, and that's certainly possible. And the cost was definitely quite favorable for an enterprise license, so that was a big factor for us. And last but not least, the community. So right from the very start, the Dgraph engineers had been really responsive to our questions and very quick to release bug fixes and any enhancements that we had requested. So, we decided to go with Dgraph and finished the data model and started loading data and landed up with 160 million nodes, 2 billion edges, and that includes the value edges and the real relationships as well in that number. And we're currently hosting on 3 sort of medium-sized EC2s, 8 vCPUs, 61 gigs of memory, and 1.8 terabytes of storage. And we're running 1 alpha and 1 zero per EC2. And currently we don't use any sharding. Even though that seems like a large number of nodes and edges, we were able to comfortably fit that on 1 EC2. So there's been no need for sharding yet, but it's certainly nice to know that that is a possibility in the future if our data set got significantly larger. The next sequence of slides, we're going to look at some actual queries. Before I dive in, I just wanted to mention that the query language that we expose on our API, it's really just DQL, but with a couple of additional functions, helper functions, and directives that we've added just to make querying a little bit easier, especially when it comes to point-in-time querying. So let's start with this first query. The first query block is a var, which just means that it's not going to return any data. And we're matching on the name, Alphabet Inc., the name of a company. And we want to recursively follow the is controlled by edge in the reverse direction. The tilde just denotes a reverse edge. And we want to find all the subsidiaries and the subs of subs, basically expand the entire corporate tree of Alphabet Inc. So, we store all of these companies in the sub variable. And then in the next query block, we pull out the UIDs from that variable and count them to get a total count of subsidiaries. And then we're just going to list out the names of the first 3 subsidiaries. So that comes back as follows. We have 219 total subsidiaries, and here are some examples. Let's say we wanted to extend this a little bit, and not only do we want to pull in the subsidiaries, but we want to see what securities are issued at any level in that subsidiary tree. And to do that, we pull in the is issuer of edge, and the nodes on the other side of that edge will be your securities. So we pulling in, going one step further in the recursive traversal. So those securities are stored in this variable, and same thing again, convert to UID, count them, and then pull out, in this case, the long name and print out the first 3. So in total, across all the subsidiaries, we're picking up 34 securities. And these first few are a Class A and a Class B common stock and something known as a depository receipt. For this query, we're going to build it once again on the previous query, but not only do we want to pull in the immediate securities that are issued, but we also want to pull in derivatives that are that the immediate securities are the underlier of. So we add one more edge type here, is underlier of, and we're going to be storing the initial set of securities in S and the additional derivative securities in D. And then down here, we're going to be grabbing the UIDs for both the regular securities and the derivatives, and then grouping on type and getting a type account for each type. And we find that there are a total of 8 common stock, 11 bonds, 12 bank loans, and over 10,000 derivatives. And finally, for this, in this sequence of slides, we're going to look at which stock exchanges do any of these securities trade on. So we've found all the securities, we found all the derivatives. Now we want to see, across the globe, which exchanges do they trade on. So to do that, we follow actually 4 more edges. Lists in is part of in reverse, trades in, and has source. And the nodes on the other end of has source are the actual stock exchanges. And same thing again, we're going to count them and print out a few examples. And we've picked up 78 unique exchanges that Alphabet trades on. And here are some examples. Point in time ultimate parent. So before looking at the query here, I just want to kind of explain what that concept means. And quite commonly, a company might issue a bond, and that bond might mature many years in the future. And before the company's had a chance to pay off all the debt, it may get acquired. So at the time that it gets acquired, the remaining debt becomes the responsibility of the acquiring or parent company. But that parent company could in turn be acquired as well, and at which point the responsibility for the debt shifts once more. So really, at any point in time over the full lifetime of the bond, there could be any number of different ultimate parents that are responsible for the debt. And that's a question that our clients like to ask, and something that we can solve with this point in time model. So looking at an actual example, we have Interline Brands Inc. that issued a bond back in 2010 that matured 8 years later in 2018. But before it was able to pay back all of that debt, Interline Brands was acquired by Home Depot, who then essentially took over responsibility for that debt until the bond matured in 2018. So looking at the query, the first thing you'll notice is that the point in time is separate from the actual DQL query. These are provided under separate keys on our API. And what the user is really telling us here is they want to run this piece of DQL, and they want to get the results as of this date, as of this point in time. So looking in a little bit more detail in the query, we're going to, at this time, going to come in with the QSIP. And the QSIP is a very common identifier for identifying bonds. So we're going to match on QSIP, and then we want to recursively follow a couple of edges. We're going to go is issuer of to find the immediate issuer of the bond, which will be Interline Brands. But then we want to follow is controlled by to see if there are any companies that are controlling that issuer, and all the way up recursively to the top of the control tree. And as of this date, we don't find any controlling companies. So, this is a date before the acquisition occurred. So Interline Brands was still its own freestanding company, and it was essentially its own ultimate parent. But if we go forward one day to the day of the acquisition, we're now picking up one level of is controlled by, and we can see Home Depot now becomes the ultimate parent as of that date. So I've mentioned before, that we use facets for this point in time filtering, but let's look at how that is actually achieved. Here, once again, is the user query, and that gets rewritten as follows before we send it off to Dgraph. And it's really pretty much the same query, except now that every single edge is includes this facets clause. And really what that's doing is it's limiting those edges to those edges that are active on this date. So any of the other edges that exist that are inactive will just be filtered out. And this final example, we're going to look at another point in time query with a slight spin. And what we want to do here is query the graph as of this date, but for a particular field, in this case name, we want to see the full history over all of time. And in this example, we're going to match on a CIK, which is a US government issued identifier for companies. And then we want to pull the full name history, see all the names of that company over all of time. But then for legal entity identifier, we want to just get the currently active LEI as of this date. And you'll see here we've introduced this new tag called @history. This is not part of DQL, but something that we added in and support in our query rewriting layer. So what that gives you is 3 different names over time. So this company had 3 names over its lifetime, and the most recent name change occurred on 5th of March. So we get all the names along with their start and end time information. But for this other field, which did not have the @history tag, we're just getting the LEI that existed as of the 11th of March. And how is this done in terms of facet filtering? Well, here once again is the user query, and that gets rewritten as follows. And you'll notice for name, because it has the @history tag, we no longer do that filtering on the facet. And instead, we just will return all names along with their start times and end times. Whereas for the LEI, we're going to do the regular facet filtering and just get LEIs that are active on the 11th of March. And that's all that I had. Thanks for listening, and I look forward to taking your questions in the Q&A.
Thank you, Mark. Knowledge is power, and we love seeing how Dgraph makes accessing that knowledge even easier. Knowledge about companies is vital, as our next speaker, Alex Ridden, will attest. Alex is the co-founder and CEO of KNS Analytics, and she spends her time fighting financial crimes using knowledge graphs of companies and financial transactions. Please welcome Alex Ridden.
Hello, and welcome to my talk on building a centralized knowledge graph to power your analytics. I'm going to start my presentation by introducing myself a little bit. So I'm Alex Ridden. I've been working for about 10 years in industry where I've built advanced analytical models and utilized network graphs, a lot of the time generating features for those models. I'm particularly specialized in applying network graphs in the detection of financial crime. I worked in lots of different multinational banks and insurance companies. I mention that because I think that my experience with trying to integrate analytics with legacy systems and challenging data models is kind of relevant for this topic. And I founded KNS Analytics a few years ago, originally just to be a freelancer, but during that time I actually built some software that I now sell full time. So I'm going to start by talking about what a knowledge graph is and why you might use one. The bulk of my presentation will be about like how you should build a knowledge graph and a lot of the considerations and challenges you might face when you try to do that. And at the end, I'll go through a kind of cheeky plug of my software. So what is a knowledge graph? The truth is that the definition of this seems to be quite varied and vague depending on who you speak with. And so for the sake of this presentation, I'll use my own definition. And that is that a knowledge graph is a unified evolving data store, which is organized into a queryable semantic graph. And it enables kind of technical and non-technical individuals to utilize a wealth of knowledge. But there are a few things that are, I guess, universally accepted about knowledge graphs. First, that it should have a graph structure, and that graph structure should be well defined, meaning that the entities, the types of relationships and the attributes are all understood and concrete. And then the next thing would be that a single node aims to represent a one real world entity, object, concept. Obviously, that's not always achieved, but we'll talk about how you can achieve that. And then finally, that your graph is continuously growing and evolving, both in terms of how much data it can ingest, its volume, and the schema. So why is this useful for analytics? This first diagram, I think, outlines a common problem that a lot of data scientists and analysts face every day. So we're often starting by thinking about a business problem and then have to go and find the data that we think can help solve it. And oftentimes that data, even if it's within a data lake, is quite siloed. So the data sets that you might want to combine have different owners. There's probably one person in your organization that knows about it really well, and you have to go and talk to them a lot. But you want to essentially then find it, write these queries to extract it, and then spend a lot of time joining, manipulating, and transforming it. There's lots of numbers floating around about how much time data scientists spend doing those three tasks before they can then actually create their models. But regardless of what that percentage is, it's definitely considered one of the most frustrating and time-consuming elements of their job. So I think that the knowledge graph can be really useful in that every time that you need to start to combine, process, and engineer your data into something usable, you can actually put it in this centralized store and start building up connected data that can be used by other people within your organization, where they can query it and integrate it into dashboards, or just download it if they want to start analyzing it. And there's all sorts of kind of iterative effects of being able to do that over time. So apart from that, there's also a lot of really practical reasons why I think knowledge graphs can be powerful for analytics. The first one being that you get much more complete view of an entity and their interactions with other entities, and also all of their attributes are in one place. So instead of kind of going to many different data sources and having to find out where you can find certain pieces of information, the idea is that in a knowledge graph, it's already there, it's already defined in a way that you can understand what it is as well. And then once it's in a graph, especially if it's in something like Dgraph, you have a nice query language where the query itself is very intuitive. So even if you're not a particularly technical person, you can understand that a query like individual has address will return to you the addresses that an individual has. So aside from those things, of course, graphs are often used in visualizations, so why not store your data in such a way? And I think those of you familiar with Dgraph will have already used RATL in order to be able to like navigate and interpret your data and find it much more intuitive oftentimes than just looking at rows of data. And that kind of leads into the integration with web apps and BI tools being quite straightforward. And then finally, if you actually generate features on top of that graph and store them back in the graph, you can start to treat your graph as a kind of feature store or an object feature store, so that every entity or relationship within your graph, you can start to enrich it with the queries that you might be running on top of your graph. So I want to talk about a use case that I think's really poignant. So I've worked in many financial institutes, as I mentioned before, and what people who don't work in my industry don't really realize is that a lot of the times even similar problems are often siloed. So what I've got on the screen here is like two oftentimes separately handled use cases. On the left, you've got a transaction monitoring situation where a victim's account has had all their savings drained into a mule account, and that mule account has then sent those savings on into the ether of international banking transactions. And on the right, you have a money laundering use case, which is often the corporate world and often requires slightly different data, but it certainly is often tackled differently. So the models running on that data are separate, and the people who work on those things are often separate within the bank. But if you integrate some other data that might come from your cybersecurity department, such as device information, this type of information is often used in one or the other of these use cases, but often not as a connecting factor between them. But you can imagine that if you have a high risk transaction that comes from a device that is then used by a company that seems to be part of an investigation into anti-money laundering work, then of course it helps build your case and understanding around that investigation. So on to the meat of this presentation. How do you actually build a knowledge graph? What kind of steps do you have to go through, and what are the challenges that you will face? The first thing will be to design an ontology. An ontology you can think of as a schema, but with a few extra caveats. How do you incorporate a semantic ontology into a database like Dgraph? How do you actually go about deciding what your node types versus your attribute types are going to be? Once you know that, how will you map your data, extract those triples and quads from different data types? And how do you actually reconcile different entities and recognize that they are in fact the same representation of a real world person or business or address? And once you have all those things, you of course want to start loading them into a graph, and you probably want to build that graph up over time. It's a very different problem from bulk loading your data, which a lot of people have experience doing, but not as many people have experience actually productionizing a graph and using it next to their kind of data lakes or other data sources. And of course, all those mapping, resolution and loading into the graph steps are going to be continuous and hopefully alive. So once you have all those things, there's of course consuming data from that graph, and then a few different things that you should think about in terms of your solution, such as, do you want to have multiple graphs or one graph within your organization? How can you potentially combine data across these privacy boundaries, where it could be really, really useful to share data, but you're not allowed to, for example, because of GDPR here in Europe. So yeah, I'm going to dive a bit more into all those topics. The first one being the designing of the ontology. So firstly, you will have to model your data as an ontology, and there's some subtle but important questions that you'll have to ask yourself here. So my first example is, when you have a person with a passport, is that passport a kind of attribute of that person? Would you consider the passport ID an ID of the person, or would you actually like link a person to a passport object? And with that object then have, you know, the start and end date? Is it possible that it can be linked to more than one person? Is it possible to have or to handle it when a passport goes missing? Things like that. And then I also want to talk a little bit about how you can incorporate semantic ontologies into Dgraph, more specifically about semantic reasoning and logic and rules. So when you're defining and designing your ontology, there are a number of steps that I think are important to outline and consider. So the first one is, of course, answering a business question, or at least understanding what applications you want to use your graph for. And once you know that, you want to start searching for data sources. So here we have an example of customer data where a business has an account, and there are various things that you know about that relationship, like the start and the end date and the account number and the bank that it's associated with. Once you have those kind of triples or quads defined, then you'll also need to kind of build out almost a blueprint of all of the relationships and all of the attributes that you can possibly have in your graph. And the final and one of the most nuanced pieces of defining an ontology is also rules or business logic that you can apply based on the relationships that exist. So here's an example of where one business is a parent of another business, which means that you can infer that both businesses are part of the same business grouping. And I'll show you some examples during the mapping of the data as to why that's important. But a few things to note here are the ontology means that you have like a very strict definition of what can and can't be included in your graph. So your schema shouldn't just adapt to new data concepts that haven't been well defined. However, it's also important that your schema should be able to evolve over time. So let's have a look at mapping. So there's two main challenges that I've highlighted here. One is the mapping unstructured data. So this isn't something I'm going to dive heavily into because there's many hours of work that can go into this particular topic. But I'll show you a bit about what it looks like when incorporated into the graph with other triples. But the kind of interesting concept about knowledge graphs is this inferred logic and business rules that you can apply to the graph structure. So here we've got 3 examples that I put together to walk you through an example of what building up a graph from different data sources can look like. Firstly, we've got some customer data where you have an account ID, a company name, the registered date of that company and the account date, and that represented as a triple in your graph would be, business has account linking to an account. Let's say you have a news source which comes in, and you can use some natural language processing such as named entity recognition in order to start pulling out some of your triples here. So here I've got Umbrella Corp recently acquired Acme, and then that can be represented as the business acquired another business. And then finally, we've got company registrations. So a completely different company that we haven't seen yet. Virtucon is the parent of the child company Umbrella Corporation. And we've got some founding dates, but that can be represented in this way. A business is a parent of a business. And if we take that data and we just take very simply the names, then we assume that these are the triples that we get from my example. And once you load them into the graph, I think there's going to be some connections found here, which I'll dive a bit more into in the next section. But essentially, we've got Acme Inc. and Acme, and we believe they're the same, and Umbrella Corp and Umbrella Corporation we think are the same. So when you load them into your graph, it will look something like this. But the interesting part is where the rules come in. So since Virtucon is a parent of Umbrella Corp and Umbrella Corp acquired Acme, we can infer that Virtucon should be considered a parent also of Acme. And all 3 of those companies, because of this hierarchy and structure, we might want to say belong to the same company group. And if a company group inherits the accounts of the child companies, then you might also be able to infer that that company group has this account. And you can see how we've taken a relatively simple structure and we've kind of built up some extra links and nodes into it. But back to the point that I just mentioned, which is around the resolution of entities and how do you actually disambiguate your data? How do you start to collapse nodes together? So I have another example of why entity resolution is so important. Here's an example where we have 2 transactions, 4 completely separate accounts, and each account having an individual associated with it and addresses. And those addresses, if you resolve them, we determine that A and C were the same and B and D were the same. And so we've got this kind of ring-like structure where we can see that there's some connections already. And if we take that information, we might also recognize that 3 of these individuals are in fact the same. And so we've got some individual resolution. So the story has changed quite a bit from the original graph, where now that first transaction looks like money being sent to just another account owned by the same person. But the second transaction is now money being sent to someone that this person apparently lives with, or at least has registered at the same address. You can see why this would become very important when you're trying to follow money flows or when you're trying to determine the risk of a transaction. Disambiguating or resolving entities in particular is key to having effective models and features. So what are the challenges in doing this? Well, I think the most important one is that all identifiers have uniqueness problems, and some of them you might assume that they're not a problem for you, and a lot of them you'll find that are a problem. So I've even been a kind of victim of this myself. When I registered at my bank, I was registered as Mrs. Alex Ridden, but when I registered my business, someone accidentally entered Mr. And that actually meant that I couldn't connect those two accounts into the same app, and I wasn't able to actually log into both my business and personal account in the same interface. So it was not a great customer experience. But as you can imagine, as well as just human error, there's all sorts of other errors. So IBANs are not universal, even though within Europe we consider them quite unique. And phone numbers get reused, and of course you've got country codes. Address formatting is a very challenging topic that many people have spent many years trying to solve, and there's great solutions for all of these things. There's all sorts of resolution options available, and ultimately you're really trying to answer that question of what about combining data that doesn't even have a key, or especially when you're combining internal data with external data sources, or data sources that just don't have the same information available. So I wanted to just go over some of the options that are available to you if you're doing entity resolution. The first one is the most obvious one, and one that most people use, which is ID matching. So I've seen countless graphs built within companies where they simply just match on the bank account number. And like I mentioned earlier, account numbers get reused, but also one person can have many accounts. And so treating them as a single node attached to an individual, if you don't resolve those individuals, you never really quite get the full picture of all of their transaction history. So the next step for anyone who's spent a lot of time doing this type of thing is to do rule matching. An example of which would be in the UK, we have postcodes which are quite unique in that you only need the postcode combined with a street number to be able to identify a single address. That's not the case, obviously, internationally, and so you'd need completely different rules if you're trying to deal with international address resolution. And then the most advanced and newest versions of entity resolution combine machine learning and graph-based features in order to be able to determine which entities are likely to be the same. So once you've done all this, or hopefully maybe even before you've done all of this, you want to consider a number of things when it comes to productionization and architecture. So I just want to go over a few challenges. I don't have universal answers for everybody, but at least this might give food for thought when you're thinking about developing a knowledge graph for your company. So the first thing will be how on earth do you integrate with the existing ecosystem? We've got a nice XKCD slightly edited cartoon here, which just it reiterates a problem that is found in almost all, especially large companies, where lots of initiatives take place, especially around a similar time, and we end up with many, many different solutions to the same problem. And you want to think about, are you going to build a knowledge graph that's just essentially another data silo that's not actually solving the problem of combining data across your organization? Should it be a layer on top of like existing data lakes? Is it itself like a new form of a data lake? These are all questions that are challenging to answer because there's things like, is your resolution universal, or do different projects and different business parts of your business require different permissions and different types of resolution? How are you going to go into production? We've got lots of challenges around scaling, which happily Dgraph solves a lot of our issues for us. But you also need to think about ingestion of new data. How are you going to collapse multiple nodes? Are you going to keep a history of updated data points? And then related to that is, of course, updating, deleting, and streaming any new data in, and being able to infer or apply some of this semantic reasoning and logic to it that I mentioned earlier. And then finally, of course, operational challenges, kind of boring stuff, but important stuff. Access control, backups, high availability, upgrades, et cetera, et cetera. So, of course, Here at Dgraph Day, we want to talk about all of the problems actually that get solved by using Dgraph as part of your solution. And we've certainly enjoyed being able to utilize all of these benefits whilst building our application. So a lot of our customers particularly interested in Dgraph now being cloud hosted. That's great. And GraphQL being super easy to integrate with front end and easy to query by our clients. And scalability and DQL itself we use with gRPC for kind of internal speed and query flexibility, and being able to know that you can store more data and increase the amount of queries that you can respond to. Being graph native was super important for us when we were building our solution, and Dgraph really allowed us to have the graph database both as a data store and a query engine. And a lot of Dgraph's enterprise features addressed a lot of the operational requirements that I mentioned earlier. So a few other considerations. You want to think about how many graphs you should build. There's all sorts of questions. I can't go over all of them right now. There's obviously an architectural decision to be made internally, but it's an important one. How are you going to handle schema evolution and rule changes? It's not a problem to build these things on top of your loading logic. And I think that that's one of the nice ways to solve the problem. When you're thinking about data science, you might want to run certain graph queries or create certain features that you want to store back on the graph. And finally, an interesting problem is really data privacy, which I have something to say about in a minute. But I think first, I'll just talk about my company, KNS Analytics. So if this has been a kind of interesting topic for you, but maybe a bit too much to take on, then the goal of my company is actually to try and make this as easy as possible. So we've essentially built a graph engine which consumes data and solves a lot of the problems that I mentioned, such as mapping the data to triples, resolving entities, and applying business and logic and rules, and loading it into Dgraph. And that means that we've built our software in line with a lot of Dgraph's principles. So we wanted to be graph native, hence we wanted to choose a graph database that could keep up with our software. And we have a Kubernetes deployment. We're scalable, highly available. We support streaming and batch. And of course, we try to integrate with the big data landscape as much as possible. And some unique things about our tech is that we have our proprietary entity resolution algorithm. We can extract semantic relationships from unstructured data. We build and update the graph in real time, with an asterisk, because it very much depends on what real time means for you and your business problem. But so far, we haven't had a problem. We integrate mapping data into our engine with a kind of a standardized interface, and we have a number of pre-built models for industry problems, so both in terms of extraction of the data and the mapping to an ontology. And of course, we're able to expand that without interruption. So I'm going to finish on something I think is really interesting and exciting, hopefully, which is that we've been working with a company called Roseman Labs here in the Netherlands also to be able to do privacy preserving network graphs. This is important for a lot of banking and money laundering use cases where we really want to be able to share data and analyze data and detect, financial crime, but we're not able to do some of the more fuzzy entity resolution. I don't have time to dive into this topic because it's a big one, but if you want to know any more, then feel free to reach out to me or to them. We'll be happy to talk about it. But other than that, that's it for me. If you want to contact me, here's my email and my LinkedIn. Otherwise, thanks for listening.
Thank you, Alex. That was an illuminating explanation of what a knowledge graph is and how to go about building one. We will now take a 15-minute break. So make sure to grab a snack or lunch and come right back. When we return, we go international again, with speakers from New Zealand, Israel, France, and India waiting to share with us the awesome things they've built with Dgraph. See you in 15 minutes. Welcome back! Let me share with you an interesting fact. Did you know that there are 2 times as many cows as there are people in New Zealand? This is an important segue, not just because our next speaker hails from New Zealand. He's running a company that performs genome analysis on bovines, and they use Badger to manage genomic data. Let's hear from Dan Garrick.
Hi there, my name is Dan Garrick, and I'm going to talk to you today about Badger and how we're using it for some genomics applications, and specifically some software tools we've developed which use Badger as a data store underneath. And I wear 3 hats, if you like. One of those hats is that I'm the managing partner of Theta Solutions, which is a US-based company involved in statistical modeling, primarily for animal and plant genetic and genomic evaluations. I'm also the founder of the Helical company based in Whakatane, New Zealand, and is a sister company of sorts to Theta, supporting our operations. And I'm also an adjunct lecturer at Massey University. So just to introduce myself a little bit, my background, I grew up on a small farm in a little town, rural town in New Zealand called Colleton. And just before I turned 13, my family moved to the US. And my dad was a professor, got a job over there. So I went through high school and then subsequently university in the States. And I got a bachelor's and PhD in aerospace engineering at Iowa State, where I worked on the computational fluid dynamics of rotors and wind energy and multi-phase flow modeling. And there's some of that involved what we call helicopter brownout simulations, where helicopters land in the desert and simulating how the dust clouds form. I spent some time at Boeing in Philadelphia working on the V-22 Osprey, and then my PhD research was on developing methods to simulate fuel sprays and supersonic flows. And about the time I was finishing my PhD, I had an opportunity to join a new company that was working in the genetics and genomics field, and surprisingly enough, the equations that are being solved for genetics and genomics modeling are similar and use similar methods, similar linear methods to solve those equations as what we use to solve fluid flow equations. So there was quite a lot more crossover between aerospace and genetics than you might think, but that's how I got my start. And just to introduce a little bit of background here, genetics is the study of inheritance of traits. And what that means is really we're talking about looking at your family tree, which we call the pedigree. So your parents and the traits they have and how that's passed down onto the offspring. And genomics is in some sense an extension or related to that, where we're studying specifically all of the DNA and the DNA components and contributions to that. And when you're talking about traits, that could be performance traits, things like growth, and it could also be health traits or survival traits, disease resistance, those kinds of things. And this has applications both for humans, obviously consumer companies like 23andme.com and Ancestry are taking advantage of this science to market to consumers. There's also personalized and precision medicine applications and pharmacogenomics applications. And our industry, specifically, we focus on the niche that is plant and animal evaluations, which is all about selective breeding of plant and animal populations, specifically to provide more efficient food and timber production. And but these concepts can also be useful for managed conservation of endangered species, where sort of genes need to be carefully managed when you have a small breeding pool, so that genetic diseases don't take over. So just to give an idea of where where Badger fits in, I suppose, there's a schematic here of an information pipeline, if you will, which is common in the world of animal and plant genetics. And effectively, you start with a business objective, and that can vary depending on the industry you're in. But it's always would start with some kind of value proposition, which is typically going to be something like profit, but it doesn't have to be. And to work towards increasing that value, you'll have some kind of data that's going to feed into an information system. And going back to the previous slide, in our case, that's going to be talking about pedigree, recording those family relationships. It's going to be about the traits, those growth traits or health traits as an example. And it's also bringing in that DNA and genotype information. And you can probably see the little badger icon I've got there. So that's specifically what I'm going to be talking a bit more about today, because we have effectively built a genotype information system with Badger underneath. And just to provide some context about our company Theta Solutions, we develop software tools, GPU accelerated software tools for the types of linear modeling that involves taking in this pedigree, trait and genotype data and evaluating it so that you can get a merit ranking of animals to feed back into your decision support systems to decide which animals you should use to breed the next better generation. So digging in a bit more into that genotype part of it, what does the genotype information pipeline look like? And the general concept is that you'll have some tissue samples that you will be collecting, typically from farms. And these farms might be sending those samples to one lab, or they might be sending them to different genotyping labs. But in any case, that lab will extract the DNA using a variety of different techniques depending on the lab. And they will produce some kind of file with DNA content in it, which they will make accessible, typically via something like an FTP server. So we might have multiple FTP servers where different labs are placing these information with the DNA in it. And we have built a platform which can then check those FTP servers and download that information as it appears, stores it in a database built on top of Badger. We've built a web UI around that, a command line interface, and it's got a number of analytical tools built in around quality assurance and quality controls of those genotype samples, so we can verify that the samples do belong to the individuals that we think they belong to, and that involves things like parentage checking, which I'll get into a bit more soon, but also things like genomic gender estimation, which basically means looking at the sample to figure out what gender that sample came from, and then also duplicate resolution. So if you have one individual who's been sampled multiple times, for various reasons, you want to be able to see which of those samples is correct and whether the samples are matching or not. And we have a host of other concepts and analytical tools that we're adding to that all the time, which we will be announcing in the future. But as a starting point, that's the rough idea of the information pipeline, and data is being managed and queried out of that by various users and organizations. And we also need to be able to export data out of that for external analysis pipelines. So you might be thinking, this is Dgraph Day. Why are we talking about Badger and not Dgraph? But Badger is the database that Dgraph is using underneath. And so I was fortunate to be invited to give this talk. I guess it was interesting enough to talk here about it. And for our particular use case, we decided to go with Badger because it's got no dependencies, it's trivial to deploy, and we want to be able to provide our tools to some of our clients to use as a command line tool, and it means that we don't need to worry about having them set up other services at the same time. They can just have this command line tool to do what they need to do. And in particular, also the batch data import, or the write batch API and the stream API, are both really useful in Badger for our use case. And then the key only iteration provides a lot of really powerful features for us to query things out of the database very quickly, which has allowed us to build this a web interface on top of the database that we're using to store the genomic data. And it also means that we try to, all the tools we develop, we try to stick with a Unix philosophy where we have minimalist and modular software. So we have specific tools that do one thing, and they do that one thing well, more or less. And the idea then is that you can mix and match any of these tools with other tools you may have to fit them into newer existing pipelines. And include them with other tools you might have for manipulating and analyzing data. And the final reason is we have a custom, highly efficient encoding of genotype data, which means that we can store a large quantity of raw genotype data from raw files into a very small instance of BadgerDB. And Dgraph returns, I think, only RDF and JSON, as far as I'm aware, through the Go client. And we just wanted to be able to build some other analytical packages which make use of this encoding a bit closer to the hardware, I suppose, if you will. So effectively, we've built a command line interface we called Helical for manipulating, managing, and analyzing genotype data. It's species agnostic. It's been applied to cows, sheep, horses, dogs, and trees so far. It includes a web UI with user authentication for data management and analysis. And we can resolve multiple IDs per sample, multiple samples per individual, and hugely varying genotype chips. And I'll talk next about what that means. But we're able to import automatically and detect a range of different genotype file types. So we can import that data into Badger, which we're using as the underlying data store for all of this. So what I mean by varying genotype chips, just to give an understanding of perhaps more why we chose Badger. Genotype data can be of varying densities and varying overlap. And what I mean by that is if you have what we call whole genome sequence, that encompasses the entire genome, all of the DNA of a particular individual. And it's very expensive at the moment to capture the whole genome of an individual. And so what happens is, once we know the particular regions of the genome that are important to us for one reason or another, those have been effectively put on what we'll call genotype chips, so that those chips will just in particular look at those particular locations of the genome and nowhere else, and get that data out for us. But of course, what happens over time is we discover that some of those pieces we were looking at are not as important as we thought, and some other pieces might be more important. And so over time, the location and the data that's coming out of those chips is changing. And also, just the changes in the technology means that there might be increased amount of data in newer chips than there was in older chips. And so the data that's coming out of these can vary over time, and this makes it perhaps more difficult to fit this kind of data into traditional SQL tables, where with these data varying over time, you're going to have to fit them into lots of different tables and deal with all of that. And so it's a nice use case for things like Badger or even Dgraph. Another challenge is that you might have two different chips potentially coming from different labs who might use different chemistry to get that DNA information, and they might be pulling information out from the same part of the genome, but the names the naming conventions they use for that information might be different, and so you need to be able to resolve that in an easy way. So really what we've built on Badger is more of a data warehouse where we're storing effectively the samples against their raw manifest from these chips. And so what I mean by that is that we might have samples coming through on what I've called chip 1, which would have, say, 50,000 SNPs on it. And when I say a SNP, I'm talking about effectively a particular part of a genome which has got variation across the population. And so those are the parts that we're interested in, because it indicates things that might be different between one individual and another for us to measure. So one set of data might have 50,000 of these SNPs on it, and then another set of data we're getting from somewhere else might have 100,000 of those SNPs. And some of those SNPs may overlap to some degree. So SNP 1b might be the same as SNP 1a here, but SNP 1a here and some other data might be the same as SNP 2b. So we need to be able to resolve those kinds of connections between the data in an easy manner. And associated with each of these chips, we have what we call a map, which means for each one of these SNPs, we have an identifier, which is the name of the SNP, the chromosome that SNP sits on, and the position within the chromosome. And these numbers are made up for illustration, but that is the general concept. And taking that a step further, you can perhaps quickly see how we can build up these relationships where we are storing what we call a chip entity in the database, which corresponds with the particular maps for each of these types of chips we are storing. And then on each of these chips, we might be receiving multiple batches of samples. And so we are storing up those batches of samples, and we're storing the relationship between all of those samples and the associated chip. And we can do that for any number of chips and samples. And we've built a lot of functionality to be able to easily export that data out to a particular subset of those samples and SNPs that we may so choose. And taking it a step further, we actually also have individuals that all of these samples are pointing to. So one individual, one animal, might have multiple samples associated with it. And so that's another connection or relationship, if you will, between the data that we're keeping track of. And then in the case of looking at parentage, and you're looking at comparisons between samples, we need to be able to quickly query that information out of the database, and Badger has turned out to be very good for all of those kinds of use cases. So just as an example of some benchmarks, some real world data, I'm always a fan of using real world data in these kinds of benchmarks, and in this case I've illustrated the particular particular command that we use to export data out of our database, which is the DB here. And we've just provided a list of SNPs that we want to extract, and those are being placed in a gzipped file. And I've run this on my 6-core MacBook Pro, and exporting 89,000 SNPs out of a database of 170,000, or roughly 171,000 samples, which is stored across 58 of those chips I described, which range in size from 20,000 SNPs to 777,000 SNPs. And including the computation time it takes to resolve duplicated samples, which means if we have samples which are similar, we merge them, and if they're dissimilar, we exclude them. And we have some other QC steps that samples go through before they're allowed to be exported for use in an analysis. After all those steps, we get 148,000 samples finally exported, which amounts to about 13.3 billion SNPs. And exporting that to a gzipped file comes out to about 3.7 gigabytes, and it takes 1 minute and 41 seconds. And exporting that to a 26 gigabyte text file takes 1 minute and 21 seconds, which is roughly between those two, it's between 130 to 160 million snips a second, and on SSD hard drive. So pretty unbelievable performance numbers. I wouldn't say we've done a huge amount of optimization around those exports, but we have done a little bit, but I'm sure we can circle back around and get more out if we needed to. And so we're able to do these bulk exports really quickly, which is really powerful for us. It means if we want a different export, we can easily just delete that old file and generate a new export, and it's resolving all of that information out across all of those chips and batches of samples we're storing across all those disparate pieces of information. And it means we're also able to build a web UI around it. And this is just an example image from our web UI where we're looking at a number of different samples, and we're able to query on the fly information about those samples and extract out the particular SNPs we might be interested in that we use to predict the sex based on the X chromosome and Y chromosome, which I'll talk about in a second, and display those kinds of information. And it's extremely fast, which is great. So this thing can be real time. And this is important because managing the genotype data is what takes a lot of time. So in terms of QA/QC of these samples, one good check is we want to check if a DNA sample is supposed to belong to a female individual, we can inspect that DNA sample and come up with a prediction based on the X chromosome data and the Y chromosome data whether that sample belongs to a male or female, and we can check that against the record we have for that individual to see if that matches up or not, which is all a part of QA/QC. And then another routine check we're doing is something called parentage, which is based on the concept of when you have your sire, your father, and a dam, your mother, an offspring inherits roughly 50% of their DNA from their father and 50% from their mother. And what that means when we go back to those tables with the SNPs in it is if we have SNP1 represented by AA for the sire, and we have SNP1 represented by BB for the dam, we know that that offspring should be AB at that position, because it has to inherit an A from its father, and it has to inherit a B from its mother at that particular position. And that's an AB is referred to as a heterozygote, while AA and BB are referred to homozygotes. And when we're verifying parentage, what that means is when we're looking at one particular offspring, usually we know what the offspring DNA sample is and what the dam DNA sample is, so we'd be kind of working backwards from here. But to illustrate the point, we can go the other way. So in the case of a sire being AB and a dam being BB, we actually can't say for certain whether this offspring should be BB or whether it should be AB, because it could inherit either an A or a B from its father and only a B from its mother. So it could be either AB or BB. So in that particular case, that SNP is not useful information for us for parentage. And in SNP3, both the sire and the dam are BB, so that means we know the offspring must be BB in that location. So those are the kinds of queries we need to do across that data we are storing. And each of those samples for those three animals might be coming from different chips, and the SNP naming might be different, and we need to be able to quickly resolve all of that stuff to compute this kind of thing. And another very useful analysis that we're doing regularly is something called parent discovery. So for various reasons, for animals, you may not always know who the mother and father are. When an animal gives birth to its offspring out in the field, it's by the time the farmer goes out and discovers that animal that's been born, they may not have been around to see it actually happen, and so you can't always guarantee which mother it came from. Usually you can, but sometimes you can't, and obviously the sire is much more difficult, and in certain situations. And what that means is if we come across a situation where we don't know who the parents are for an offspring, we can search against the DNA samples we have stored, and provided the true parents have been genotyped and that we have their DNA somewhere, we can assign the correct parents based on the data we have stored. And so what that means is, if we have this offspring, let's say, and we're searching through the database, we can see that in SNP1 this offspring is AA and this sire is BB. That means they can't possibly match because those are opposite homozygotes, and for that offspring to have come from that sire, it either would need to be BB or AB. Its sire can't be an opposite homozygote. And so that is true for all of these SNPs. So in this case, the offspring is BB for SNP2 and sire 1 is AA, so it can't possibly have come from him. And so we're able to discount him as a potential sire, whereas sire 2, because sire 2 is heterozygous for SNP1, that's not a useful piece of information we can use for parentage in this case. But for SNP2 and SNP3, sire 2 is BB at those locations, and the offspring is also BB. So therefore, we can consider him as being a potential match. And I say potential because parentage, DNA-based parentage, works on the principle of exclusion, which means that if we have two samples and they are like sire 1 and this offspring definitively coming out as being conflicting, they are not a match, we can exclude them as being a parent offspring. But in the opposite situation, where we are getting a match between a sire and an offspring, we can't conclusively say that that means that animal is the parent of this offspring. We can simply say that they are a potential match, but we don't know for certain what the relationship is. It could be sire offspring, or it could be flipped around the other way. There's no way for us to tell which is the sire and which is the offspring, as an example. And for these kinds of activities, a lot of organizations typically utilize a small subset of SNPs, typically only 100 or 200 SNPs, for example, and there are a few reasons for that, but one of the reasons, as I understand it, is a technical reason around the storage of this data and the storage of these disparate chips. And just having, when you have these disparate chips, if you just use a particular subset of, say, 200 SNPs, you can always extract those 200 SNPs out of your disparate data into a singular SQL table, which makes it much easier for you to run these kinds of analyses. The problem with that is it reduces the probability of exclusion between what would otherwise be non-matching animals, and that's not so bad when you're trying to verify parents, but when you're trying to do this parent discovery process, if you have, say, one offspring and you want to see for that offspring out of these 50,000 potential male genotypes that could be sires, which one of those is the match, the difference between a 0.1% error rate and a 0.01% error rate could be the difference between, say, 100 sires being assigned or 10 sires being assigned. So it's being able to use more of those SNPs allows us to get a much more definitive and accurate result about the parentage between any two individuals. And because we are able to store and quickly query out these disparate pieces of genotype information in Badger, we're able to resolve a lot more of the information than we otherwise would. So just returning to sort of where this is important, and those are the kinds of queries we're doing with Badger and the way we're pulling the data out of it. And really, when it comes down to it, we're trying to solve problems for our clients, and in this case, the highest management workload for them is typically resolving issues between DNA samples and the animals they belong to. And so being able to automate as much of that process is very useful for reducing their costs. And those kinds of issues typically come down to either mislabeling of samples or poor quality or contaminated tissue. It could come down to a gender mismatch. And that could mean that the individual that we have recorded for that animal is, let's say, recorded as a female in the database, but then the DNA samples we receive all appear to be from a male. And as it turns out, that the animal itself is actually male, and it's the animal database that is incorrectly recording it as female. And so these processes help with rectifying this difference in information between these different systems. So it's all about automating that. And obviously there is a potential extension of some of those concepts to add Dgraph in as another layer, which we are exploring to especially resolve Dgraph-based, sample-based metadata from lab information. So finally, plant and animal evaluations is the area we work in, and I just want to highlight that this is a big industry. So for the New Zealand dairy herd, genetic improvement is estimated to be worth $300 million a year. And just to give you some context, the US dairy industry genotyped 1 million animals in the last 12 months, and that costs roughly $30 for each animal. So that means they're spending $30 million in lab costs alone, not accounting for the storage and management of that data, which is where this kind of tool comes in. So in conclusion, the increasing variety of genomic technologies and data require increasingly flexible tools for managing and analyzing that data, and gaining insights from that data is key to adding business value. But many of these raw data structures are not well suited to SQL and those associated ecosystems, so we're looking to address that issue. And we've found that BadgerDB is a powerful data store for custom applications like this. And we provide a flexible genotype management platform for managing this kind of data. Thank you.
Thank you, Dan, for showing how versatile Badger can be. We love seeing unique use cases like these, and science innovation always blows my mind. Speaking of science, data science is a very hot field. Managing your data is actually one of the biggest pain points in data science. Our next speaker will share how he leveraged Dgraph's community to build a data science tool. Take it away, Oren.
Hello everyone and welcome on board. My name is Oren and I'm a software engineer at Data Science Group. And today I'm not going to lecture you, but instead I'm going to tell you a short story. So get ready and let's start. From zero to hero with Dgraph community. Chapter 1. Once upon a time, before the COVID-19, in a far land in the Middle East, there was a software engineer. His name was Spinelson. His mission was to save all data scientists from the mighty tech monsters such as GitHub and Git, and bring peace to his kingdom. So he took his weapon, a map, and the enchanted book of all magics. And then the journey began. Riding on his horse, he headed to the land of GraphQL, ruled by the King Slash. After 3 days of riding, he finally arrived. But oh no, at the gate, there were lots of bugs. Luckily, League Knights were there to save the day. After a long fight of several days, they finally won. but Spin and Son ran out of time. Chapter 2. After the battle, Spin and Son went to visit the sage, a master 507, to consult his wisdom, tell him about the fight and all the bugs and unsolved problems he had. And then a master helped him to understand how to overcome everything. So for several weeks, they worked together in order to solve the problems Spin and Son faced. Spin and Son worked for about 2 months, and he understood that GraphQL isn't the solution he needs. So he started to move forward to DQL, and he didn't know what to do. Fortunately, at the same day he changed to DQL, a magical box appeared on his desk. At the box, there was a note. Spin and Son opened the box and found the community amulet. He put it on, and suddenly it felt like a new power filled his mind. It felt like his brain grew and grew and grew. And now he is able to develop anything. Chapter 3. Equipped with the power of the community amulet, Spin and Son jumped on his horse and rode back to his kingdom. Then he started to work on developing ML, a version control-like system, tailored especially for GraphQL. ML is a creature with 3 heads: a CLI, an SDK, and a UI. So after a year of working, ML is finally in its alpha version. Currently, it is not public, but we will publish it. Spin and Son will publish it soon. And all data scientists could live happily ever after. The end. Okay, now back to reality. As you can understand from the story, Spin and Son is actually me. I'm the software engineer who developed ML, together with my team, another 2 developers. It was a year-long of development because we switched between GQL and DQL, and we had to implement everything from almost 0. And with the help of the community, we actually succeeded to do that in time. And now we are working to create our base users. So a little bit more about ML. ML is, as I mentioned in the story, is a system that is combined of 3 parts: the CLI, the SDK, and the UI and backend. The CLI is implemented with Python built-in library, Click, and the SDK is also in Python. we developed the SDK since data scientists are more familiar with Python and have less technical skills than software engineers. So in terms of UX, we decided to give the best UX to the data scientists to work with ML. So if we considering the CLI and the SDK as the Git part of ML, so the CLI is actually really like Git, where you can create new branches, new versions, and push or pull information. The SDK gives you a little bit more capabilities and more features that can be implemented with Python and not with a CLI. So more logic that code can do. And the backend is where Dgraph taking part. Our backend is like what the part that manages the data that the data scientists index locally, and behind the scene, Dgraph is actually the database where we have the schema that I will show you soon that has all the information about branches, versions of each branch, and the repositories, the users, and everything inside each version, which is artifacts. I will show you soon what it means. And the UI part is what looks like GitHub. And let's see what it is. Okay, so this is ML. And as you can see, we have my repositories. So let's open the repository of Spin and Sun. And then you can see the members in the repository, how many members there are, how many branches there are, and all the artifacts. And artifacts is actually any type of file that you can imagine. Okay, so it can be data set such as CSV, a script such as Python script or JavaScript. And also we have data sets and also models, which are also artifacts, but they are not files. Artifacts can be also objects that look like a file, but not exactly a file. It's just the metadata about this file. And as you can see, we have the graph that describes the connections between each artifact. And this is where Dgraph actually works. Okay, so every artifact is a node inside the version, which also is a node in the graph. And between artifacts, we have the edges, inputs and outputs. And when a data scientist wants to investigate how a model is created, it can actually see the graph behind the research and what other collaborators in the research did in order to create a model. So here we don't have a repository that has models at the end, but it's a flow that describes how from data we can splitted the train and test data. And if we want to see our branches, we also have the forest view, which describes which versions of the branch we have and also which branches we have. Each branch describes one direction in the research, and each version describes a stage in this direction. So from one stage to another, we actually can see the progress of the data science research. And if we have more branches, we can understand that one direction is finished or there is another direction that we want to research. And we can also see the progress of this direction if we will have such one. And if I will click here, we can see another graph, which has actually a model, but is not connected to anything. And we have the same data that we started from the master, and it goes through split, and then it's split to train and test data. And also I can do this from here and switch and then see the master. Another thing that I can do is actually invite collaborators. So if I will add here my team mate, I can give her the admin and the inviter. So as you can understand, it's very like GitHub. I wanted to create the same language. So data scientists will have a comfortable way to find the gaps inside the system and inside the app. And actually start to work with it. And the reason we decided to do something like Git and GitHub is because we actually wanted to let data scientists things that that are not supported in Git, such as diffs between data that can have more than million records, and the ability to investigate the creation of a model against many versions. So if a model is appearing in several versions, we want to see how this model was created in each version, or to take models from different versions and check which data gives the best predictions from each model, which is impossible in Git, because in Git you only can be at one version of the code at the same time, and in ML you can be you can take models or data from many versions and apply it to data and models in different versions. So that's actually the UI and how it works with Dgraph. We use GraphQL and because we needed the transactions, and when we started to develop in GraphQL, there were one transaction. It's changed now, but we had to continue back then. And our backend is like developed in 3 layers. We have the queries, which is in DQL. I will show you a little bit what happens behind the scene. So we have the backend, the server, and we have the queries in DQL, and it's separated into modules. Each module handles different kind of data. So this is like a query that describes the pool branch. And we also have the data access layer, which is where we manage when we run the queries and like return the results to the CLI or the UI. The backend speaks with both of them. And we have our schema with all the artifacts, branches, memberships. Everything is managed by by DQL, by GraphQL. By Dgraph in DQL. And on top of it, we have the API, which is developed with Django REST framework. And there's an authorization layer, which is developed with Auth0 and JWTs. And we also have the UI with React. It's a React app with TypeScript. And another thing that we have is the CLI, as I told you, and the SDK, which will be open soon and become an open source. So if you want to join us and develop it, you will be able to do this soon. And the backend of the UI also will be published, not as an open source, but the UI and the app will be published soon. We are currently finishing the alpha version and starting to test it with our base users inside the company. And when we finish that, we actually will release the beta version and then the first version for everyone. It will take us, I think, about 3 months in order to reach this destination. And that's it, actually. That's what we have currently. And one last word before I finish the lecture is why I did this lecture. The reason I did this lecture is because it was important to me to tell you how much the community helped and how much is important for me and others to have a strong community of developers who can share their knowledge and can solve problems together inside the community and then help each other to actually get along with the technology that Dgraph developed. And I encourage you to also participate in the community as much as I did actually. I participated a lot and helped people and got help from other people, and that's how I actually managed to overcome all the problems and all the challenges I had, especially when I switched between GraphQL and GQL. And that's it. So thank you for listening, and you can find me in LinkedIn, in my email, and also in the Graph community as Pinansan, as you can probably understand. And thank you very much again, and see you in the Q&A. Bye-bye.
Thank you, Or. Emma looks really cool. To summarize, it's a workflow and version tool. Exciting stuff. Okay, strange question. Anyone strapped for cash? No, not money. I'm talking about caching. If you have a caching need, you might need Ristretto. Our next speaker, Sylvain, will walk us through how he created a caching system for Traefik using Ristretto. Please welcome Sylvain.
First of all, thanks to Dgraph organizers team to let me talk to you about my side project Will & Go, and obviously thanks to all of you who are listening, and I hope you're all doing well. Before diving into the subject, let me introduce myself and make my self-promotion to you. My name is Sylvain Combrac, I'm from Lille in France. Then, sorry for my baguette accent, but I'll try my best to speak as well as possible. I'm Traefik contributor. I'm also creator of the cache system we'll talk about, and you can find me on GitHub searching Darkweek and Darkweek Dev for Twitter. I'm working in a company called Letier.coop. It's a French self-managed company, and we are working mainly on web stacks like PHP and React.js, but we are working on Go softwares too. So let's replace the context of why I started to dev using Golem and how I came to do it. As I said, I'm Traefik user since 1.4, contributor and helper, and for those who don't know Traefik solution yet, it's a reverse proxy created to manage container architectures, and it's a container-first approach. It supports the hot detection deployment, the scaling, it load balances your request automatically using the wait one robin system, and use only a specific port for all protocols. Then Traefik manage for you the service resolution depending the host in entry. Then it's the pivot point of your infrastructure. It's like Kong or Nginx for those who have already worked with them, or like Caddy also, but really simpler to configure and to set up. Another good point is the fact you can install it on your development environment and continue your work instead of bigger reverse proxies like Kong, for example. Then, as you can hear me, I love to use Traefik, but after months to use this solution, there was an issue I was facing too. There wasn't any cache system internally to Traefik. Then all requests would have to resolve the associated service. Then it took many milliseconds to be done. I searched after a cache system solution, but nothing appeared to be as efficient as I wanted, or it was only POC. And after many nights spent to look after that, I decided to create my first program in Go. I was totally noob with this language, but it didn't scare me because I had a goal, and for every kind of project, when you have a concrete goal, you'll do your possible to achieve that as any possible ways. And it's different to start a language with a goal and learn a language through a tutorial. You are more implicated in your development. So that's how I came to learn Golang with all of its dark sides and obviously all of its light sides. This project called Swan is actually in 1.4.4, and for the record, the release names are free beer names, open source beer names, precisely, because I love to drink beers. So don't forget to leave a star because I've got an oversized ego and it makes me happy to view the Stargazer's count growing. For those who are using Varnish, there is an illustration to show you how Swan is versus Varnish, and obviously that's just for touring, and I send kisses to Fuckbot. So let's see together how it's easy to set up Swan through a demo. So here I'm in a folder with a configuration YAML and Docker Compose YAML file. So if I try to catch the configuration YAML content, we are defining a default cache key with a children named port to define that Swan will listen only on HTTP. And we are defining a TTL with a lifetime of 10 seconds. Then we are mapping the reverse proxy URL using the Docker service name because they are in the same network. And if I clear that and cat the Docker Compose YAML file, we are defining the first service, which is Traefik. Then the ports mapping are not important, and we are defining whoami service, which is a container which will show us what's the IP of the container or any other things. And we are defining a Swan instance as latest, which will listen on the HTTP port, and we are mapping the configuration. So if I try to make a Docker Compose up with detached mode, then containers will be running and will be starting. So it creates the containers because it's Docker Compose, and it's a little bit laggy because I'm recording at the same time, but everything should be okay now. And if I try to reach the domain.com, which is mapped to Traefik, we can see it took some milliseconds, and if I try to refresh, it takes less milliseconds, but it's a higher number than the production mode because I'm recording in the same time, etc. And as you can see, it's really easy to set up instead of Varnish. Now let me explain how to build fast application with Go and specify in my case which kind of Go features help me a lot. First, I can't talk about Golang feature without mentioning the Go routine feature. If you don't know that, a Go routine is basically a part of a thread which will run one task, one function, detached from the main thread, and will close if the main thread stops. In this example, we can see that the cost function will be delegated to another thread to be more efficient, and because we don't need the result of this execution, we don't store in any variable. Then here the update cache eventually is really cost effective due to headers validations, RFC checks, and other checks. And you can easily do concurrency with the Go keyword placed before function declaration and before function usage. Then Another big feature is the channels. We can wait in main thread for informations or push data to the Go routine. Today, a real Golang application without channels, and obviously Go routine doesn't exist, or it's really rare. A channel is like a bridge between the thread that instantiates the channel and the associated Go routine. For example, I use channels to thread the incoming request and be able to collect them if needed. And only when the response is available, I return it to the client. With that, I can manage multiple connections at the same time on different or same endpoints. And as a channel, as a type, we can define our OR channel channels like here. We are defining a reverse response channel that can take the same type as input-output, and you can only pass and retrieve reverse proxy type or nil. And a little tip, you don't forget to close your channels. For the record, in the previous version, I forgot to close the channel at the end of the function, and there was a higher memory consumption. Then for those who are asking in their mind, on lines 22 and 32, I manually closed the channel. I couldn't use the defer keyword just after the responses variable assignment because I have to close it as early as possible. Then if the response is valid, I can close it to avoid memory pollution. Then I was facing an issue that Go doesn't support generic tabs at the moment, but in the second version of Go, it will be done. So we have to find some tricks to be able to pass as a generic object as possible. The solution is to apply the dependency inversion principle to decoupling software modules, thanks to Wikipedia for this definition, and use interface instead of the implementation. It's a little bit tricky to implement an interface in Go because you don't have the implement keyword, and sometimes you can implement an interface under the hood without knowing you're implementing it. In Swan, we have some providers to be able to let the user decide which kind of storage system should be used, depending the matched URL in the full version. And here we are defining the type of each provider. Each provider defines the same functions like list keys, get, set, and other ones. And for each provider, these functions have the same signature. So to make a generic object, we can define an interface like the abstract provider interface, which will contain the method's signature, and each structure defining all the functions with the same signatures will be considered as implementing the interface and can be part of an abstract provider interface, for example. After that, we can pass our Redis and our Bootstrap provider, and as the two structures are implementing the interface, it won't crash, but your IDE will show you the auto-completion for an abstract provider interface object and not your real object instance method. The power of Swan compared to Varnish is the configuration part, which is simpler than the VCL or Varnish configuration language. Here you just have to define a YAML and it works like a charm. On the left you can find the minimal configuration to be able to run a Swan instance, and on the other side you have the full configuration for the full version containing Redis provider, etc. Then as it's YAML you can use anchors, you can write scripts to create dynamically the configuration, and the most of all, the configuration supports the hot reload. Then you don't have to restart Swan if you change the configuration, but I plan to disable it by default in the future to avoid memory leak, and because it makes a side Go routine running to listen the file changes and reload configuration when the file is saved. Then keep in mind that the existing keys are always stored and available in your providers and will be purged only when the TTL reach 0, or if you decide to purge the cache by regex or URL directly using the API, but we will talk about it later. As Traefik, Swan is container first designed to be compatible with as much as possible with existing systems. You can define a Docker compose YAML file for Swan, exposing the needed port, and map the configuration file path to the Swan container, and be sure the reverse proxy is in the same network than Swan instance to avoid the external request. This is the configuration for working with Swan out of the box. There is an available CatG module and the Traefik plugin, which will be released when they'll support plugins that use the unsafe library. I hope this day will arrive soon, but I don't know when. So it was so funny to dev this, but I was facing the most complex part. The first one was the RFC implementation and RFC support. Because supporting a RFC rule is really good to face and fight the depression, because you think you're done with that, but another rule comes and you have to rewrite parts of your code. The RFC for request for comments designs the semantic of the web and apps to homogenize and define standards of your responses, your behavior, and don't let the creator be free about implementation, like the logical parts and data processing, for example. And here is an example with the RFC 7234 single page, and there are 42 other pages, and that was a pain to support that, but thanks to other developers that implemented it partially in the past, and I could reuse their existing work. Then, when you're implementing an RFC, you realize that just if-else conditions, you can see in this example to manage the cache control header. It's just conditions after others to be able to test every cases. And that's the same, for example, for the expire header to check if it had already expired or always good to be served, for example. Another cool feature is support for the request coalescing. That means when you get multiple requests at once on the same route with same context, you'll temporize all incoming requests and you'll request only once your backend, then use the same response for all temporized requests. That's pretty cool because your backend service can be on cheaper server like Raspberry, for example, and it couldn't handle all requests if it was than if it was on Fortline. So thanks to Single Flight for providing a library that can be used to handle and coalesce requests. As Swan takes care of users and want to let them manage the cache through an API, it provides some endpoints and secures them with authentication. At the moment, you can only list keys to avoid content linking and purge cache for resource or multiple by regex. So let's see together how it works and how I did it to make it faster as possible without impacting the Bash cache system. First, the configuration about all the API endpoints are the following. You have to define the API block in the YAML configuration file. Then you can override the main bus path, which is Swan API by default. And at the moment, Swan supports only 2 APIs, but in the future, it will support more endpoints. For each endpoint, you can override the bus path, tell if it's enabled or not, and by default, it's not. Then, specifically for the security endpoints, you are allowed to define a secret and a list of users to be able to log in as these users. For the user endpoint, you can tell that you want to protect related routes behind JWT security firewall. For the cache management, the default bus path is Swan, and you can send a GET request on the bus endpoint to list stored keys, or send a purge request on an ID or reject purges. Here are some examples about the results when you are sending requests on these endpoints. As you can see, the bus path route returns an array containing all keys stored in the provider, and in the full version, it returns all keys for each provider as an associative array. The provider name will be the item name, and the item value will be the stored keys for this provider. The purge regex path returns nothing except an HTTP no content header to tell you that the purge is taken in consideration. So, as I said, Swan provides the JWT authentication using JWT token, and you can log in on the login endpoint sending a post request, a JSON content type header, and a JSON body containing the username and password. Then you can refresh your token sending a simple post request with a JSON content type header and a cookie called Swan authorization token, which contains the JWT token in it. Here is the result about the security API endpoint, which is located under the bus path authentication by default. The login request set an HTTP cookie if authentication is valid. Then the refreshed endpoint returns a new HTTP response, which tells that the previous cookie should be replaced by the new one. But you can tell you in your mind, okay, it sounds good, but I want to know how to cut this, so I'll tell you the magic under the carpet. Basically, I get the main bus path from the configuration. If it doesn't exist, it will use the default value Swan API. Then after that, I load each endpoint using the initialize function, which take a provider and a configuration. If the endpoint is marked as enabled, I just create an HTTP handle func with and without the trailing slash. And each endpoint have a property named handle request as the name specified to handle the incoming request. Then the bus path, is built from the concatenation of the main bus path and the endpoint bus path. This code is running at the Swan startup or the configuration warmer, and it takes only some milliseconds to be executed. Then the last tricky part is the key management. I'm using Ristretto library, but in Ristretto there wasn't a function or property containing the full list of stored keys. Then I had to declare it out of the Ristretto library. I called it key saver in the Swan code base. So it allow you to manage the keys with the hash key, the hash name in the Ristretto library, and as value the plain key. Then the key saver is basically a Go routine, and all actions on it will be run inside it. And get and delete functions are asynchronous. And with this approach, I don't have any problems with concurrency as I try to write something in the array while I'm reading it. So thanks to the rlock and rnock functions to ensure nothing can edit your list when we are accessing it. So after this very long technical part, we can now talk about the deployment system. The deployment is secured by Travis CI to avoid any regression. Then the GitHub action get back the lead to deploy only tagged version on master and full version branches. So first, the workflow for deployment or on tag branch is the following. Tests for Travis are launched, then the artifacts are built, And the last step is to upload artifacts on the tagged commit to be able to download the OS and Arch associated by node. So here is a diagram to try to represent the Traefik CI setup, and here is a configuration file about it. Let's see together what's done on it. First, I tell Travis to boot with a Golang environment. Then I add the Docker dependency to be able to run required containers. Then it ensures compliance with every system. And I decided to not sending emails to not being spammed. After this setup, Travis will run the make create network command to add the associated network, then make build dev command to prepare the container to run as development mode. After that, after all these steps, Travis will run the make validation command, which will group the linter verification, and if it succeeds, it will run the test to handle any regression. Then, after that, we check that the production mode can be built and won't crash to ensure the compliance with users that use the latest Docker image. After that, when it's merged on master and tagged, the GitHub action will be called and two jobs will be running. The first one is the binary generation to create artifacts depending the OS and Arch. It retrieves the tag name, pulls the tag branch, require Docker dependency, and enables the build system to be able to build Docker images. Then it tries to log into the Docker Hub using secrets credentials and build the prod container using the Dockerfile prod and push it to the Docker Hub as the latest full and tag branch name as image name. The only one line which differs from the minimal version is the 33rd line. In the minimal version, we are using latest instead of the latest full tag. And as you can see, here is the result on the Docker Hub. Our image is tagged as latest and is ready to be pulled, and obviously is tagged as the latest full for the full version. Then the last steps is the artifact generation and upload them to the GitHub release through the Go Releaser action. In this example, we build for Linux, Windows, and macOS for each Arch to handle most cases, and it uses a matrix to build the tool. And as you can see again, we have our artifacts on the referred release. Then every tests are and deployments are done. We can pass to the last part, which are the metrics. And for those who want to see what is the power and performances of Swan, here are some metrics to view how many requests it can handle per second. It took around 35 seconds to serve each 101,000 requests. The max response time was 56 milliseconds, and the minimum one was 0. But in fact, it took around some microseconds, but it rounded to 0 milliseconds. And it's due to Ristretto powerful in combination with the asynchronous updates. So what's next in Swan? There will be a fully support of Vary. It required a deep refactoring about stored keys, and it took some time to achieve that. And we worked on the fact Swan shouldn't try to coalesce request on an endpoint that already returned a private cache directive. These features are already available on master branch. And after that, we will support the new RFC cache status to replace the X from cache header And there is always the work on performances because this can always be optimized. Then I plan to release a new stable version on this week, and obviously if you want to contribute, you're welcome. So let's see together some another cool side projects. The first one is Merch. It's an open source pen test oriented platform to help pen testers to get enhancement on their missions. You can find it on GitHub, and I built a platform for discover KDE modules and simplify the life for making a xkd build command. You can contribute on the website, which is located in xkd.tech, and on the build on the module retriever. These projects are available on my GitHub. So to finish this talk, I just want to say thank you again to Dgraph organizers team. Thank you to all of you who are listening me. And don't be shy, you can ask me whatever you want. I'll try my best to answer it in the chat. Anyway, I'm available on Twitter if you find some question during the night. And like Gordon Ramsay is saying, thank you.
Merci beaucoup, Sylvain. I know everyone is eager for a break now. Our next talk will be short and sweet. Aditya Goyal is a senior software engineer at Delivery, a last-mile delivery and logistics company in India. In this talk, he'll explain how Dgraph powers their addressing model. Take it away.
Hello everyone. Welcome to Dgraph Day. My name is Aditya Goyal, and today I'm going to talk about unstructured addresses. Not how we as humans read and understand them, but how to store and query them. With storing, I'm going to talk about the challenges and how Dgraph helped in solving them. I'm a backend developer with Delivery. I have 4 years of experience with multiple backend technologies, asynchronous application, and NoSQL databases. I have been working with Delivery from past 2.5 years. Delivery is one of the largest and most profitable logistics company in India, which primarily focuses on digital commerce. It was established in May 2011. Its first 2 centers were in Delhi and Gurgaon. From there onwards, it grew on to become a multi-million-dollar company and now serves over 18,000 pin codes in 1,200 cities. It handles over 30 million orders a month and employs about 40,000 professionals. Recently, I have been working on graph databases to solve a few complex problems. One of them is going to be discussed in this talk. Apart from this, I'm also working as a data engineer and exploring big data technologies such as Spark. Before moving on to the core problems we faced, I want to make you guys familiar with the kind of data we were dealing with and the scale of it. The data is of unstructured addresses. Since Delivery is into logistics business, we need to deal with a lot of addresses. Those addresses can be of a customer, warehouse, shop, etc. And we need to predict some information such as its geo coordinates as soon as the address comes into the delivery system. Previously, we were storing this data and metadata in a MongoDB database as addresses string and query based on the localities of the address. That way, we were fetching more data than required for prediction. This process was very slow due to the size of the data being fetched. We changed the approach, and instead of storing complete address, we moved to store n-grams of an address and its metadata. Now, why do we want to store it? We wanted to query the metadata for a new address coming in based on its n-grams and predict some information based on historical data. Just to give you an idea of the size of the data, we had almost 500 million nodes and more than 1 billion edges. As you can see in the sample graph, we are storing n-grams and have an hierarchy which is connecting in higher to lower geographical area. Let's start with the problem we faced while designing a system to support the requirement and try to find the solution of each one of them. Since a lot of customers place orders on e-commerce, the rate of addresses coming into the system is very high. So the first problem was to import data of a new addresses which were coming in very rapidly in the system. And the database or model needed to load all of it while serving the queries of production with minimal impact on performance. Since the database is responsible to predict some crucial information for new addresses coming in, this needs to perform live loading with minimal impact on query performance. Otherwise, we would not be able to predict any information. The third problem was to store and query geospatial data. Since we were dealing with geo coordinates of addresses, we needed to store and query based on latitude and longitude. The fourth challenge was the query we wanted to execute. This was a recursive query of more than 50 hops on average and may reach as high as 150 hops. Here, one hop query is equivalent to getting all connected nodes of a list of nodes. I'm putting a sample query here for more understanding. We also require to store data on edges. So before discussing the solution, I'm going to present the points which became the deciding factor behind choosing between Dgraph, Neo4j, ArengoDB, and Amazon Neptune. Few factors which played a major role in decision making were availability. The database needed to support queries 24/7, scalability. Given the size of the data and its unbounded nature, the cluster needs to scale horizontally as well as vertically to utilize the available resources. Synchronous. The data should be in sync between multiple read replicas. And distributed. This is to support huge data size. Since there would be more queries in dense localities, we needed to support of caching to execute the following queries faster. As we talked earlier, the database needs to support queries on latitude and longitude. We needed high hop. We needed to execute high hop count queries in order to predict geo coordinates of a new address. This query is supposed to fetch all related metadata we have stored with respect to the new request coming in. In the evaluation process, we were monitoring the time and space utilized by this query. Given this graph is supporting transactional requests, the query execution time needed to be in sub-second latency. We needed to find relationship or connection between given n-grams. This required to execute query on reverse edges as well. Since the new address is coming into the system with high rate, the graph needs to support uptime, updation, and deletion with minimal impact on query performance. Let's discuss the solution on behalf of the evaluation process. First thing first, Dgraph met the basic requirements of availability and scalability, both vertical and horizontal. Dgraph supports query caching. Dgraph also caches the nodes which have been queried recently, and that improves the query time for dense localities where more queries are being executed compared to sparse localities. Schema design plays most important role behind query performance. It is best practice to design all possible queries upfront and decide the graph schema based on that. Here we indexed n-grams due to queries being executed on this and created a reverse reference to support fast query execution. Putting a screenshot of the schema for reference. Fourth is high hop queries. This played a major role in evaluation process and the comparative analysis between different graphs. High hop queries were being executed with excellent execution time due to reverse reference. Here Dgraph by far outplayed all of the other databases. So the Dgraph journey wasn't completely flowery as well, putting some of the challenges we faced while designing our system on Dgraph. The first challenge was to concurrently query on a Dgraph node. Here, we were not able to execute more than 5 queries concurrently. This was a major bottleneck given the node size was very high, and this could occur a huge cost for database management. I'm going to discuss the solution in the next slide. The next challenge is to update a subgraph with different RDF file using live loading. We were using batch processing to train the model, which results in an RDF file. We needed to update the dgraph with the output RDF file, and this is not supported in dgraph to automatically delete and insert edges based on an old and new RDF file respectively. Here are the steps taken to resolve the problem. To resolve the first problem, kernel level changes enabled us to execute multiple queries at once. The max number of open files became bottleneck while deploying a large graph. The variable given in the slide can be utilized to update the value of the same, which is net.core.somexcon. Moving to the second problem we faced, to update a graph with RDF file, we needed to delete the available subgraph using the previous RDF file and their IDs, followed by importing the new RDF file. This makes the subgraph unavailable for small duration depending on the size of it. That is how we are using Dgraph to solve one of our problems. Thank you for spending your time to listen my story of Dgraph.
Thank you, Aditya. That was an enlightening talk, short and sweet. Okay, folks, we're going to take a short 5-minute break. And when we return, we have talks from Fortune 500 companies. See you soon. Welcome back. Our next speaker hails from a Fortune 100 company in healthcare tech. We can't tell you their name, but we can tell you the cool stuff that they're doing. Rachit is the senior platform architect at this prestigious company. And in the next talk, he will fill us in on how Dgraph is used to build a customer 360 platform in health analytics. Everyone, please welcome Rachit.
Hello, everyone. My name is Rachit Bhargava. I used to be a platform architect for one of the Fortune 100 healthcare companies. And here's our journey of how we started using Dgraph from the initiation of the app to the time it went live. We started with like the basic version of Dgraph, and then finally, I think we moved to 20.19.3. That's the last release that I actually worked on, and it has like a major paradigm shift from what we started and from where we are. So one of the interesting questions that everybody asks, right, that why me as a platform architect started looking at Graph as a database, right? Why can't we do everything in the relation database? So that's a kind of a battle that everybody fights when you look at a Graph as a solution for your backend microservices. And it's a kind of interesting paradigm shift from what people used to do and what we are trying to do when you're trying to be truly agile and try to bring value proposition to your customers in a kind of pretty hard and fast way. So from a healthcare point of view, if you look at the data and the kind of things that we try to target from a health tech company point of view, customer or the subscriber or whatever you want to call it, right? It's the center of your universe. And when you try to look at the customer, right, if you try to visualize him or her, subscriber goes to a hospital, and then hospital he visits doctors, then he sees nurses, then he might be going for some ultrasound. So these are kind of different attributes that just originate from the user and the different activities that he or she's trying to pull. So in a nutshell, what you're trying to visualize and try to develop from a health tech company point of view, right, is a customer 360 representation of what all things he or she does. And there's nothing in the world better than a graph to do that versus relation database. Then another thing that also comes into mind, right, as you try to build applications which are pretty huge, right, and enterprise level application, you start talking in terms of relation databases, and that is where you start creating those multiple tables, right? And then in order for you to get a simple data, you have to join multiple tables and get that. And then again, because not everything you can require from a customer point of view is also always available, right? So then you start getting into those situations where, oh, I need data from table A, but I need data from table B, but table B might not always have the data, but I still need a query. So then you started getting into those queries in which you start using outer joins, inner joins, and everything else, right? That, as soon as you start introducing that, that kills the performance because typical relation database index doesn't store null values, right? So when you try to execute those queries, it just becomes so complex, right? And then the query size grows, and then troubleshooting, understanding, and everything else, right? It is, becomes very difficult. Another thing that we, at least from a health tech company that I was working for, one of the things that we always try to do is to understand what a product owner wants from their solution and the funding that they're trying to get from a business point of view, right? And all this it's very helpful if they understand from the early get-go itself, being not technical, but at least if we try to present the solution to them in a way, oh, yeah, this is what you will get as a part of MVP, this is what you will get as a part of your post-beta release, and this is what you will get finally in production with limited delivery or maybe a kind of a full RFLD release, right? So Graph presents a kind of a pretty easy way, and I'll just show you an example in my coming slides how actually that helped my team when we were trying to pick Graph as a solution, right? And then the fourth point is basically explaining the same thing. It just allows a neat way to stack your data and just allow everybody to visualize, oh, if I want to look at users, how many devices he or she has, right? That edge, which is a kind of an English sentence, just makes your life really easy to say, oh yeah, this user has 5 devices, 2 of them are active, 3 third ones are not active, and 4th and 5th are giving trouble. So maybe some sort of a automation could be done on those 4th and 5 devices to replace them. So kind of a typical workflow that my health tech company went through. And one of the challenges is, right, there are so many solutions in the market. You go, right, just to Google the word graph databases, right, it will come up with like more than 100 choices, right? So then you try to figure out a way, what exactly are you trying to do from a graph database point of view? And then we basically try to make sure, at least with the initial POC that we did with the first three Dgraphs, first three graphs that are listed, Neo4j, DSC, and Janus/TitanDB, is that we were kind of very interested in not to get get involved with a typical graph provider. And that's the reason we were looking for graph databases which are compatible with Gremlin. So Gremlin, I mean, most of you guys know, but it's just like a kind of a overlay on top of the graph database that interacts and provides you a kind of encapsulation that you need when you talk to graph databases. So when we started looking at Gremlin by Tinkerpop, the couple of databases that came up was DSC and Janus/TitanDB. So just Janus is like an open source version of TitanDB, which was kind of a project, and then it was scanned later. DSC is a DataStax product, which basically uses Cassandra as the database, and then of course Neo4j, which is like a true database. So when we started looking at these product rates, I mean, we did a kind of a POC, and the objectives were, if we try to do concurrency and how to get maximum value for our buck, right? And then other concern that we had from our graph database point of view is that we wanted to make sure that whatever product we are picking has some sort of an easy way for us to load our complex relational data into this graph ecosystem, and that should become a kind of a source of truth. And as we venture through this exercise, these are some of the selection criteria that we had, right? So one of them was concurrent transaction support and scaling. And then one of the kind of interesting use case that was requested by the business, right? I mean, we had to prove the value from a graph implementation point of view, right? Because if you're saying that the complex joins that the relational database produces are difficult to manage, right? And you have very complex queries, then how does a graph supports 3, 4, 5, or up to like 10 level of traversing in a kind of a very easy way, right? And then another thing was, because the kind of a health tech data, and we were talking about live customer who, I mean, in this case, for the business unit that we were trying to do the POC from a health tech company point of view, had some strict requirement on things like, oh, if this data is not updated in like a couple of minutes, then there's a chance that somebody could get hurt and even might get killed. So we always wanted to look at how quickly can we get the data back, and if asset compliance is available, it's like it's like one of the top things, or the checkbox that will make us choose this product, right? Then after that, we had a couple of other things which were like future things, but we still wanted to make sure that, oh yeah, the initial deployment will be on-prem, but then at the end of the day, we wanted to use a kind of a true microservice architecture. And the reasoning behind that was that every service should have its own database, and then that is where, right, you associate a subgraph or a graph to it, and then scale up the microservice with that, right? And another important thing that we were trying to look at, which we actually realized, and that was kind of one of the reasons that Neo4j was rejected, right, is that in order for you to have a kind of a horizontal cluster, right, or you want to have more resources from a Neo4j point of view, it was, even though they say it's a kind of a masterless technology, but still under the hood, right, it was still electing a leader, and then the copy of the data was kind of same. So basically, if you have like a 5-node cluster, you're making the same copy of the 5-node of your data in 5 different places, and that's like, to me, it's too much waste spaces of resources, right? Then cost, and then the last, analytical querying. This was something that we ventured as a part of a graph solution, but that was not something that was kind of written in stone. But the most value for bug that we got from analytical querying part, right, was from DataStax, because the Spark engine that they provided as a part of their interface itself was kind of pretty cool. Dgraph and Neo4j perform in a kind of a pretty similar way. And you want to do like basic count queries and try to do basic group bys, but then the other graph solutions are kind of pretty high. But eventually what we ended up doing is that we made graph as a source of truth, and then we used something called as Apache Druid to look at our analytical requirements even for statistical data review. So we picked up Dgraph, and that's the reason I'm talking to you guys, right? So what made us pick up Dgraph? I think one of the key driver was it is an open source solution, and it was the fastest when we did our math around what is the concurrency, how faster the system scales up, how easy it for us to do rebuilds of the system from a backup point of view, from a restore point of view, right? And then one of the coolest thing that we found out about Dgraph, right, is the data sharding concept that was explained to us by the core Dgraph team, and we actually implemented it. So this feature basically allows you to create multi-zone clusters, and the idea is that you create those indexes in such a way that, oh, this region requires data in such a way, so then that shard of the data was only residing in that cluster. Obviously, other copies are also available, but then that created a kind of a local zoning for us to allow the users to say, oh, you are in East Coast. Most of the data that you're looking will be somewhere from the New England area, right? As an example. So that allowed us to pull data in a kind of pretty fast way. Then another thing that we found very interesting in Dgraph, right, which was kind of also available from Neo4j point of view, but the option of having commits, which is, because it was supporting ACID, so we were able to get read commits, immediate reads after the commits. And then there was also an option in which if you have kind of a high load, there is something called as a best offer query that you can execute, which basically, the idea behind that was like to have eventual consistency, but that helped us in some certain use cases in which, oh yeah, we're running a bad job. We know this data will not be there, but then with the best effort, right, it allowed us to pump the data into one side of the cluster, right? And then we knew that it's not going to be sent to other clusters till it's available, right? Because of the best effort. So it allowed us to write pretty big data scaling system with batch processes with eventual consistency. So it didn't put much load on our prime main machines or the leader, right? And the data was actually being pumped into the non-leader clusters, and then we were able to do them. Then the third is kind of a pretty important, as I was saying, is that we wanted to seed the data into our graph database as we were trying to get in, right? And we went through multiple exercises with the Dgraph folks. Initially they were only supporting the RDF-based load, but then they worked with us and they provided us a way to load the actual JSON data that we extracted using our processes, right? And we're able to load them. Then a bunch of other things like indexing with native reverse edge support. So if you go for a kind of a traditional graph, right, like for example, if you go for Neo4j, you have to explicitly define a reverse edge as you are trying to do any data loading from a graph point of view. In Dgraph, reverse edge is just like a annotation that you can add as the time when you're creating an index. Security aspects with RBAC. See, these RBACs are kind of a term that I stole from Kubernetes, but at least in terms of Dgraph, right, more specifically, I'm referring to ACLs, which came as a part of our Dgraph's enterprise solution. Pretty useful thing that, in the beginning, it was kind of not there, but as we grew from our product point of view, plus from Dgraph point of view, right, everything started adding together, and that allowed us to have like granular RBACs or ACLs to allow the user to say, oh, you have only access to this predicate, not to anything else. If you don't have access, then you will not be thrown an error, but what you will end up seeing, right, that nothing's being returned. So that basically allowed us to have everybody access to this new tool in our production ecosystem, and then also made sure that we are not getting into those issues with HIPAA, or to say, oh yeah, this guy should not have access to this data while he or she is looking at somebody's SSL, even though it's loaded in Dgraph, right? And then I think the last thing basically summarizes what I was trying to talk about from a bulk loader point of view, is that out-of-the-box JSON support. So one of the things that people don't realize, and it might sound kind of pretty trivial, but when you do API development and when you create hundreds and hundreds of them, right, you would like to use a system in which you don't have to use Jacksons or the JSONs of the world to do your data formatting, And what I mean by that, right, is that still we have not left the world of writing those plain old POJOs. So you still query the graph, you convert that to an object, right? And if something is coming out of the box, and Dgraph is kind of pretty flexible with the annotations that they provide, right, as a part of their GraphQL ecosystem, it makes life real easy to say, oh yeah, here's my class, here's the output that I'm going to consistently get in a JSON format, and there's no need for me to write a custom parser to look at the data that I need, as compared to what we have to do for even for something like a DSC or for Neo4j. So in my previous slide, I was talking about how and why we were trying to use Graph, right? So one of the reasons why we wanted to use Graph, right, is to make life simple for the product owners, right? We want to tell them their requirement, whatever they need. At the end of the day, obviously, it will be written in some sort of a language, right? But if you make the use cases simple so that they know what exactly are they getting, right? So for example, we modeled our graph database and the APIs around it, right, using simple English sentences, so that when we communicate to the product owner, right, we say, oh, this API will do this, and this is the model or English sentences that we'll use to say to get to your requirements. So the product owner say, I want to create an app in which user should have access to KCircle, they belongs to KCircle, and they do blah blah with that KCircle, right? They have to pay for a bill. They can use different methods to pay for a bill, right? And then they will have devices. So when we started writing those GR stories, and when we started to onboard the developers as well as different teams, we presented them with these kind of English sentences as a part of modeling to say, yeah, you said user should be a part of a KCircle, right? So in our case, it will be like user belongs to a KCircle, and it kind of ties pretty well with the modeling that Dgraph supports, which is like subject predicate model, right? And they keep it simple. We also try to keep it simple. So the user belongs to KCircle. User pays bill for a service. User uses payment method to pay for bills. User has devices, and then the chain goes on and on and on, right? And the key thing over here, right, as the conversation started, user is our center of our universe, right? So everything starts with universe, and it's not saying that you can't say devices have some other attributes, right? Or KCircle have different roles, right? Or service is a premium service or a kind of a secondary service, right? So all those kind of possibilities are there, right? But it just makes it really easy from a user point of view and from a developer as well as a product owner point of view, right? That how my data is getting stacked and how I'm trying to build this interconnection, because it's always easy to relate it to something that we live and breathe every day, as compared to writing a requirement says, oh, go to this table, fetch this, and this column will have this. Well, like from a product owner point of view, they care less how the data is being. So all they need is, yes, I need these 4 attributes, right? And they will be there. And another thing with Graph that it's kind of inherently not visible is the flexibility with data model, right? Because Dgraph supports JSON out of the box, it allows us to add and remove attributes at will, right? Okay, so I kind of a pretty simple example of from these English sentences that we had, right? We created a kind of a logical model, and that helped the business partners, right, and the product owners to visualize what and how the application is going to interact, right? And then it kind of presented a pretty clean clarity from application developer point of view, right? To say, oh, I want to write this user service. Oh, and by the way, it needs to have a connection to this KCircle. So when I'm modeling my class, right, I need to make sure that there is a way for us to add this edge belongs to, because that's what my English sentence says, right? It said user belongs to KCircle, right? The user has devices, user uses payment method, right? So whenever we have these arrows going from this user to a payment, right? This arrow going to the payments node, that's the edge, and by default it is a reverse edge also, so you can query in either direction without having any sort of penalty, right? And this provides us so much flexibility. Like for example, right now what you're not seeing over here is a kind of a complete data model, but the opportunities and the flexibility that this provides is enormous, right? So in future, if user has devices and user is trying to subscribe to devices which are not from the healthcare provider, they are third-party devices, right? then all you need to do is, right, you need to add another node, which is of type has device, and then create some attributes which will define that it's a kind of a different device. It could be a node or it could be an attribute that can sit on this device's node itself. And you just use them as they require, right? And then as Dgraph is evolving, it also allowed us to patch data, or we were able to kind of write pretty simple Python scripts also to when we had to move data here and there by using the PyDgraph library that we got from Dgraph. Challenges. So one of the things that comes with any new system that you're trying to bring in from your legacy enterprise point of view, right? So working in a kind of a startup, it's kind of pretty easy. You're starting with a green field and things are and whatever you want, right? And if there is a mistake, you just go say, oh, I'm going back to drawing board, right? And let me start it fresh because there's no baggage that I'm carrying. With respect to legacy, huge legacy and Fortune 100 companies, the legacy enterprise systems, right, they don't go away. So what you try to do is, right, you try to find a way of how to make them understand that, yes, relation was the way, but there are certain things that you could do in NoSQL databases, right? Which doesn't mean that, oh, I want to have my billing system also run out of Graph. No, Graph is not designed to support a billing system, right? At least in my opinion. But what Graph can do is to create that logical collaboration between different business entities so that you know where your data is sitting and how is the best, and what is the best way to reach out to it in a way, oh yeah, I know this patient data is over here, this device data is over here. If I just create an edge between these two nodes, right, and I should be able to get each and every information from this, and that becomes my source of truth as compared to going to hundreds of tables and try to find simple answers to your basic questions, right? As we were working with Dgraph, right, we had some challenges with respect to best effort queries, right? So even though it's a kind of a consistent system and it's a support asset, but in some cases what we observed, right, and that is in the kind of initial versions of the Dgraph and maybe with the latest one, right, is that the best effort queries were not returning us all the data. And the problem with that was we had a pretty big live application in which there were thousands of concurrent users. And if the data was going here and the right, not saying that it was impacting each and every customer, but in some cases we saw that the data that we had on one node was kind of different from the other node, right? And then the third point is basically describing as we go through with the new product, right? And the challenges are we learn with them and the team that you're working with, right? Also learn with us. So we started with Dgraph right from the very basic version, right? And then once we moved to production, it was a kind of a pretty big and hefty exercise for both the teams for us to go to the latest 20.3 releases so that we are using the latest and greatest version of Dgraph. Right? The analytical queries, as I was describing, one of the criteria for us was to look at the analytical stuff. I mean, Dgraph did what it can do, but again, it was not as impressive as what we had with DSC, but it did the job. And then finally, when we were able to integrate our solution with Druid, it helped quite a lot from just creating a pipeline to extract the data from a transaction Dgraph and that put into some sort of a warehouse, right? Maybe in future, there might be a tool that that will be requested from Dgraph and it might be available, right? Large data set migration. In the initial phase, we had pretty huge data, and then the only format that was supported was RDF. And while we had own challenges with converting from JSON to RDF, right, or write that, we worked with the Dgraph team, and then finally they were able to provide us a JSON library that allowed us to do that huge data migration. And when I'm talking about huge data migration, I'm talking in terms of terabytes of data. So it was not like a couple of GB data that we are talking about. We're talking about a couple of terabytes of data. And that too is a kind of a transform way, because one of the things that you try to do is, right, you try to take your normalized data and try to denormalize it as much as possible from a graph point of view so that it provides you flexibility, and then whichever way you want to query it, right, makes it easy, right? The second last item was kind of a wish list from our product team, because one of the things that large enterprises do, right, is that most of their core reporting comes out of the existing legacy solution. We move to clouds and use solutions like Redshift, etc., etc. But again, it's RDS underneath, right? So right now, the request was always, oh, you have all the data, you are the source of truth, right? But I still need some sort of a pipeline to extract the data and put into some sort of a RDS solution, because there is no direct interconnection between NoSQL to databases like Dgraph, right? With the reporting tools that people use, like Tableau, or what was there's one more that we use, right? So it's a kind of work in progress, but something that we had like initial, like back and forth with the architecture team to say, oh, yes, it's checking on 5 boxes, but the 7th one, it's kind of important, but then we have to come up with like creative solution of writing pipeline and then dump the data. Then the last one is subgraph for logical separations. So this was kind of partly resolved using the ACL that came in the enterprise version, but in the initial phase, right, we had to go with like a big holistic Dgraph, and then have the own node types embedded, and we have to write our like own custom ACLs in our application microservice code, so that it knows, oh yeah, I'm trying to write to this guy, but if I can only talk to this node if I have this, right? And I need to make sure that this is not overwritten when this workflow is kind of requested. So ideally, from a microservice point of view, right, the way you try to visualize is you try to have their own independent databases. So that's something that we were looking from a subgraph option for doing logical separation. But it was kind of partly achieved using ACL. Maybe it's some sort of a work in progress. And here is an example of what I was trying to explain with kind of a complex join with multiple tables as compared to kind of a sample query that basically uses the logical model that I showed and use all the kind of bells and whistles in a kind of pretty straightforward way from a Dgraph point of view. So in a nutshell, what this query is what it's doing is, right, it's trying to say from application point of view, I'm trying to log into my app, right? And as soon as I log in, right, I want to see who all people are there for this user, which belongs to my care circle, right? And then once you get that information for all the people that belongs to your care circle, you try to find their name, who's the guy who's getting the service, right? And then who's paying for the service. And then you can add as many blocks of GQL that you need, right, to get more and more data, right? And the cool thing with all of this is, right, it comes back with a JSON. So we were just saying, oh yeah, comes like this. There were classes that were already defined and were readily converted to kind of a Pojo. And that's pretty much it. Thank you for listening in.
Thank you, Rachit. That was a fascinating inside view of a Fortune 100 company. Speaking of top-tier companies, our next speaker is Rob Lee, who works at another Fortune 100 company, this time in telecom. In trying to build an analytical dashboard for his company, Rob encountered issues with performance, scalability, and ease of use. It's no wonder he ended up using Dgraph instead. Let's hear more from Rob Lee.
Hello, welcome to Dgraph Day. My name is Rob Lee, and today I'll share my journey of using Dgraph to build analytics dashboards for a Fortune 50 company. Let's get started. I'm a full stack developer with a Fortune 50 company, as I just said. I have extensive experience building analytics dashboards and financial reports. I've been working as a developer for over 15 years, working with multiple front ends, back ends, and DevOps environments. The past 5 years, I have focused my attention on building responsive and scalable UIs and analytical dashboards for large enterprise companies. Let's jump in and talk about some problems and solutions. The company I work for, I'm on a team that was tasked to build an analytical dashboard. We started off with the hybrid LAMP stack using Drupal as our backend and React as our front end, but very rapidly we ran into roadblocks with our backend in scalability, performance, and data management. First problem that we ran into was the excessive amount of joins that you would get with a relational database. The data is very heavily interconnected, so querying the data required many joins on a large amount of tables containing a large amounts of data. This was difficult, especially given the fact that the data was heavily normalized by default, and we didn't have the time and resources to spend building out specialized denormalized tables specifically for reporting on this data. Optimizing SQL queries requires a deep understanding of not only the data, but SQL itself. And we could spend a lot of time optimizing through specifying indexes and creating those denormalized tables. But this would be spending time in an area we really didn't have time to spend in. This was difficult, especially given one of the role of the dashboards is to allow executives to build a la carte dashboards. So we didn't know upfront what they would be querying for. And let's face it, SQL is not an easy language for executives and managers to use. It's hard to create a library around building dynamic queries with SQL, given the intricacies of the language and the lack of flexibility when it comes to denormalizing the data on the fly. On the technical front, writing resolvers, especially in a LAMP stack environment, is not fun. Having to specifically create resolvers for important relationships that should be generated for us by default is something we just didn't want to deal with anymore. Having to explicitly define every reverse relationship for every entity in an ecosystem that needs to be a la carte for anyone looking to create and develop performant dashboards is not scalable, and it's not easy. Furthermore, importing data was a massive bottleneck, dealing with ins and outs at a high rate with a high amount of rows. Whenever we imported data, we had severe slowdowns on the front end, regardless of how large our relational cluster was. We ran into issues with database connectivity, issues with dealing with a large variable rate of imports. This could cause lookups, lockups, and eventually data irregularities. Lastly, because our data is highly interconnected, we would frequently need reverse references. Being able to easily get reverse references for specific entities was always a pain point. No matter what solution we looked at, this was always something that was never perfect. It was never something that was easy to deal with. And this is true in both relational and graph databases other than Dgraph. Dgraph makes reverse references so easy, it's a dream come true. The only thing we need to do to grab reverse references is to make use of the tilde character, and we're good to go. In other environments, this would require developing custom resolvers and also managing indexes to make sure the queries are performant. So some of the graph systems we've considered, Neo4j, Amazon Neptune, and Dgraph, we played around with these environments and we realized that these weren't solutions that worked out for us. So early on, we realized we needed a graph database because of how our data is structured. We considered these three databases first. So Neo4j is, of course, the most popular graph database out there. When you Google graph databases, one of the first matches that comes up is Neo4j. And Neo4j gives a few problems to deal with, one of which is the fact that Cypher is a tough language to generate queries for programmatically. This is something that we needed to do to make it work with an a la carte dashboard. So that's something that made Neo4j a less ideal solution, as we spent a lot of time digging into creating a library for this. Dgraph is another solution that we looked into, and it presented similar issues as Neo4j. They both have languages not really suitable for on-the-fly query generation from code. We wanted to stick to a more GraphQL environment, or something that was at least close enough where we didn't have to rewrite all of our queries and redo our entire querying layer. And Neptune is kind of in the same boat, where we don't want to spend a lot of time dealing with Cypher or Gremlin or some other query language that Neptune offers. And one specific area that Neptune provided a challenge was we needed all of our data to be on-premise. There's no exceptions for that, unfortunately. And while I love working in AWS, this was kind of a non-starter for us. So for us, what a graph database needs to do it needs to be scalable horizontally and vertically, depending on the resources we had. We needed to work with a familiar language, GraphQL, that would be used and adopted by the organization and ecosystem of developers. We needed a way to query reverse references, and this is one of the biggest items, without having to write custom resolvers and making custom queries in an arbitrary language. We settled on Dgraph for its seamless integration with GraphQL, its ease of setup with Docker, and its performance. We had to have a solution that was on-premise only. So Dgraph being open source as it is, we were able to fire that up through Docker very easily. We needed a solution for importing a large amount of data daily and to not have the import completely shut down the site or lock up any queries that were going on the front end. And the reason Dgraph is the solution for this is because it scales both horizontally and vertically. If we needed to add another node to the cluster that we have, we could easily do that horizontally, adding another server. If we needed to add more memory, we can scale up vertically. GraphQL, of course, is the biggest reason we stuck with Dgraph as far as the query language perspective, using DQL and having it be basically compliant with what we already have for our queries. This is especially true with like the reverse references that we have, being able to use our existing GraphQL queries with the custom resolvers that we have and just swapping in a little bit of syntax sugar to be able to do reverse references was huge. It saved so much time. Not having to write resolvers, these custom resolvers that we had to do before, not having to do it for another language that we switched to. This was something that really also saved a lot of time. So GraphQL being supported out of the box was a huge item for us. And of course, it being on-prem, this was easy to set up with Docker. We had good performance out of the box. And we were able to import a large amount of data without having it impact the front end or impact any queries that were already in flight using the live loader. So those items itself were something that made Dgraph a really appealing solution to us. So how we're using Dgraph, we define our schema in a JSON schema file. And this is where we're able to reuse a lot of the schema definitions that we create for generating forms. We needed it to use for generating entity pages. Anything that we need to do as far as the schema, we can pull in to our front end and generate whatever we need off of that schema, and also have it be generate a schema file for us on the back end to import into Dgraph or to make any schema changes, which is seamless. It makes it super easy. It doesn't take any time, and it makes it very easy to manage. So the schema file itself is generated through a series of JavaScript scripts that we wrote. They're not very large. They're easy to use. And all we have to do is update that schema, the JSON schema file, and generate using an NPM script to generate the schema file, which is imported directly into Dgraph. And this takes seconds. Being able to declaratively describe our resources and dependencies without having to get bogged down on every minute detail really made it easy for us to focus on other areas of our code and our data. So that's how we basically define and work with our schema as far as managing updates and version controlling our schemas. So this was a huge plus for us being able to manage it in this way. And this automation workflow, here's a little example of how we kind of structure this in a JSON schema form. We have a declarative nature for our entities and describing the fields that are being used. And so this entire block of code could represent an entire entity that we use to generate a schema entity that we're using in Dgraph. This was something that didn't take very long to develop, and it was something that we could easily create a conversion script to generate our schema file for Dgraph. So using this approach, we saved a lot of time. We were able to modify the schema and add fields, remove fields, update entities without having to spend time really diving into the code and wasting hours just rebuilding a schema that we really didn't want to spend time on. So this was another level of automation that really let us focus on the data and the code. And as I mentioned earlier, we have existing GraphQL queries. As we were using in the LAMP stack as our backend using Drupal, we already were using GraphQL, and we didn't want to go to something like Cypher or Gremlin where we would have to deal with rewriting queries and rethinking of how this data is connected. It's something that would really spend a lot of time in something that we didn't have a lot of time to spend in. So DQL, which is GraphQL, which is Dgraph's query language, was something that's basically GraphQL on steroids. It made it so much easier for us to use reverse references to basically take the queries that we have in GraphQL that are plain GraphQL queries and build them out more, really reduce the amount of code that we had to write or use with GraphQL. We didn't have to make any custom resolvers, which was something that again, we didn't have a lot of time to spend on. We didn't really want to sit around creating resolvers for every possible solution or every possible query that might occur. So Dgraph basically taking care of that out of the box was a huge selling point for us. Being able to just take a query and tweak it a little bit and then have it work right out of the box was something that was surprising. We didn't expect it to work right out of the box as it did, but it did. And it saved us a lot of time for writing complex queries, which, as I said before, we're generating queries on the fly. People need to build dashboards that are a la carte. So this really saved us a lot of time in having to write those resolvers and kind of define explicitly all of our connections through these resolvers. So this was definitely a huge selling point for us. And so some of the technical issues that we did run in with Dgraph. Dgraph uses a lot of memory. This was something that was tough to use for development purposes because not a lot of developers have a lot of memory on their computers. So this was something that we kind of had to get around as far as how we're going to develop locally with this. We were able to fire up an instance on staging that developers can hit against, so they don't really have to run a local copy of Dgraph. But this was something that we had to kind of figure out early on, as it does spike in memory quite a bit, depending on the queries that you're running, of course. We wanted to be able to import easily and be able to update data easily. And one of the issues that we ran into is being able to delete edges and update edges at the same time was something we couldn't really do with the live loader import, because if we have something that's referencing multiple other entities, like a one-to-many scenario, we would have, if we wanted to completely override that edge, we would have to clear it first, make it null, and then we add to it or insert or update that data. Not being able to do that in one go is a little bit of a problem for us. So we're able to solve that in different ways, which we'll get into in a second here. The first thing we do is we generate a file for deletion on import. So basically when we're importing, we basically decide, okay, these items need to be replaced. These edges need to be replaced. So we need to set them to null first. So we create basically a clear or a delete file that we run before we do any inserts or updates. So we create two files on imports, and these are run in transactions with the live loader that really, it doesn't really affect anything on the front end. It doesn't affect any queries that are in flight because it's running in these batches of about 1,000 at a time. And this really helps us with maintaining the speed, making it transparent for people that are using the portal itself. So that was one of the issues that we solved by creating those two files, creating the clear file, the delete file, and then of course the second file, which is the actual inserts and updates. As far as the memory goes, we did the staging environment, so developers can use that staging environment to hit against as far as not having to set up a database locally, which would use a lot of memory. And of course, a lot of the developers don't have that memory up front. So having that staging server was important for development. On production, we could just simply add more memory to our cluster, and that's basically what we did, which solved that problem for us. So so that became kind of a non-problem after a certain period of time, but it does take a getting used to, especially if you're not used to using that much memory, or if you don't have the resources to add all of that memory. It's going to become something that you're going to have to address. But those two problems are really the only problems that we ran into, and they're not as big of a problem as, you know, writing all these resolvers or using a language like Gremlin or Cypher to generate queries. These were problems that were, we could deal with this. So that is basically the way that we were using Dgraph in a production environment for these analytics dashboards. And I appreciate you allowing me to take this time to tell this story to you. Thank you.
Thank you, Rob. I always find it interesting which elements of Dgraph appeal to different people, and it's great to hear how Dgraph has made reverse references a breeze. Last but not least, our final speaker for the day hails from Australia, where the sun is just rising as we speak. Adam James built a semantic search engine for social media using Dgraph, and he'll be walking us through how it was built. Let us welcome Adam.
Hey everyone, my name's Adam James and I'm the founder of a pre-seed startup called Kin. We're a search engine for social conversations. Before I begin, I'd like to acknowledge the traditional custodians of the land we're working on, the Whadjuk Noongar people, and pay our respects to their elders past, present and future. I'd also like to thank Dgraph for the invitation to present today. I've got about 20 minutes. And so what I'll do, I'll quickly run you through my story, a bit more about Kin and what Kin currently looks like, where we're at in the startup process. I'll run you through a customer case study, and then we can go quickly through or briefly through the Kin stack at a high level, and more specifically how we use Dgraph with Kin and the benefits that Dgraph provides for early stage startups such as Kin. So first, nice photo of me. Let's talk a little bit more about my story. I'm a 3-time founder, reformed quant, PhD dropout. I'm very contrarian how I think, and I definitely default to doing things instead of actually thinking them through. So I first became interested in machine learning when I left high school 20 years ago. I taught myself C++ and built my first machine learning algorithm to beat a casino game, believe it or not. Then I went on to apply machine learning across a range of quantitative finance problems, including developing the strategy for a $1 billion fund. Over my career, I've founded 3 startups, as I said before. My first startup focused on developing and commercializing an algo trading strategy. Then I left quantitative finance and I partnered with my wife in setting up an e-commerce store, and I couldn't help myself. I used a lot of, or tried to implement a lot of machine learning features with that. A bit of overkill, I think, and now Nadia runs that without me. And Kin is my 3rd startup. Now, before we talk a bit more about Kin, I want to ask a question, which is, how do brands create more meaningful connections with their audience? And I guess more importantly, why should you care about that? Well, something I've learned as a founder is that building products is pretty easy. choosing a problem worth solving is a little bit more difficult, but still relatively easy. However, earning the trust of a market is extremely difficult. So this is the real hard thing about startup, is building the market. So if you're an early stage founder, then you would probably be familiar with the term product market fit. Now, founders tend to focus on the product side of that instead of the market side of that. They tend to neglect the market a little bit. So if if there's one tip that I can give you about startup, is if you want to actually give yourself the best chances of success as startup, the easiest way is to start by building a very supportive community from which you can actually launch your product upon. So this answers the why you should care, but we're still left with how do brands create meaningful connections with their audience. And like many startups, Kin actually began exploring a different problem in a different market. It took a lot longer than I would have hoped to actually gain the insights from that market for me to pivot away to tackle a different problem, which is essentially the problem that 90% of startups face, which is how to find, empathize, and connect with customers. Okay, so what is Kin anyway? Well, in a sentence, Kin is a search engine for conversations happening across digital communities and social media. We recently launched our MVP, which is experimenting with conversational search across Reddit. Using that, you can go to kin.so and search for broad topics. Then from the word cloud that's presented, you can drill down into specific subtopics and then see the related statements and questions that are happening around those or that relate to those subtopics. And why this is really cool is because it allows you to basically gather all those insights that you need to understand the context of a customer's problem instead of having to go and talk to them all. So in startup, that's really, really useful. So we can get a better understanding of the pain points of our audience as well as the language that they're using to talk about those pain points, which essentially helps us to create content calendars that align with those pain points and also build rapport by matching the same language that our customers are using. And then we can insert those pieces of content or links to that content into the discussion. So we're adding value to the conversation of the audience or the users within our audience, and they end up in our sales funnel, which is great for them. It's great for the startup. So what I want to do is take you through a case study of one of our early customers, which is the Profile Laundry. And the Profile Laundry, what they do is provide advice and tips on how to improve your dating app profiles to get more matches. So let's jump over to the kin.so website, and we're simply going to type in dating apps. Right, Kin. We can see all these phrases that are presented. And all of these phrases are related to dating apps and conversations that are happening around dating apps. So we've got discussions on photos, grooming. This one looks to be how to get more matches on dating apps. maybe openers, so how to actually open a discussion on a dating app. So let's grab one. Let's have a look at more matches. So I click on more matches, and I get taken to the conversations that are actually happening that relate to how to actually get more matches. So we can see, no more matches, is it really my profile, or is it due to something that's happening on Tinder? So if I was the profile laundry, I could use these questions to start creating content that address those issues. So if people are asking about how dating apps or how the algorithms use and how the matching works, then we could create content around that. And then we could actually click on this particular conversation and share that piece of content directly into that discussion. That helps answer this person's question, as well as gets this user into the marketing funnel of the profile laundry. So we can scroll over. We're trying to maximize the number of matches, paying for boosts on Bumble and Hinge, and if it's really worth it. So if we're going through, we can start building up a profile of the different types of questions and the different language and the different, like what's really important to the customers. And whenever those come up, we can actually click through and go back to the go to the actual conversation as it happens and share our content. So I'm just trying to find a decent one. Oh, that one's a big one. So this is interesting. This is exploring from a woman's perspective. No more matches, is it really my profile? So that's the one that we saw before. I thought I saw one about photos before. So yeah, so let's see if we can jump out. Oh, here we go. So this is interesting. So if I want to offer a service around optimizing photos for dating apps, so I'd be looking for these types of conversations, and then I could go straight to that conversation on social and share my service. And what's really cool about this is that because we're adding value to the conversation, we're adding value to the community, and we're addressing these problems in a timely manner. So people who are having similar problems are able to see that content and how you help solve that problem, and you get a much, much greater amount of traffic or higher converting traffic by engaging in marketing this way. So if we recap, Kin makes the customer journey mapping, the message mapping or the message matching and the prospecting much easier. Like you can pre-qualify leads instead of doing broad-based top of funnel marketing across, Facebook and annoying people. And our test results, we got up to 10 times more leads for 30% of our test ad budget compared to some of social ads. So now that we've seen what Kin is, let's talk about how we actually built it. And we'll go through a little bit of the back end at a high level. Now, when I'm building a product like this, I want to make sure that I'm building something that can scale, right? So we don't want to, we want to avoid banking technical debt as much as we can. And when we roll stuff out to production, we want to make sure that it's actually something that we're not going to have to, ideally not have to change much in the future. That's not saying that we build an entire app as our MVP. That's definitely not the case. We incrementally build tech that's going to sustain us at scale. So how do we do this with Kin? So we used highly scalable, first-in-class infrastructure such as Kafka, Spark, and I'm happy to say Dgraph. How this works is that our data is ingested into our Kafka pipeline. It goes through a machine learning transformation pipeline that's orchestrated and performed in Spark. And then those features are connected to the original data and stored over in Dgraph as a graph. Now, let's quickly go into the Dgraph schema. And one of the reasons I really like Dgraph is because compared to SQL, something I've found in my past is that SQL type data gets quite tricky when you're handling complex relationships, especially complex relationships that are going to have to iterate. However, whereas Dgraph makes the design of a schema really easy, and you can iterate it as your understanding of the customer problem also evolves. So the Kin schema is actually based on what's very similar to a schema that's outlined in one of Dgraph's online tutorials, being the message board app tutorial, which is available at this link. And so we essentially have these underlying entities, very much like what is presented in the tutorial. I actually got these images out of the Dgraph tutorial. So these are the nodes that are created in our schema. And these are the predicates that are stored or that are presented in this tutorial. And we use the majority of these in Kin as well. Plus we have the predicates that are associated with the machine learning feature enrichment of the data. So what I really like is that this is a fairly simple schema, but Dgraph makes it really easy to do powerful and really fast search queries. And we can string them, we can string these together in a bit of a pipeline. So, one of my favorite features on Dgraph relates to searching, and it actually allows you to do partial matches on a broad matching phrase and still return it. So instead of doing exact match searching, you're able to search for substrings contained within a larger string and return those results. So that makes it much easier for doing machine learning or returning results that are associated with natural language processing. So why would I choose Dgraph again if I was to go back? 100%, definitely. the schema itself and being able to iterate that schema. So having that flexibility to iterate that schema very simply, where our understanding of the customer problem evolves, is invaluable. But not only that, because we're able to leverage Dgraph/service, so that's like Dgraph as a service, and combine that with GraphQL, we're able to build a MVP much faster than if we had to manage and administer the Dgraph cluster ourselves on our own Kubernetes cluster in our own cloud. Overall as well, like Dgraph is a robust and scalable and blazing fast database that allows us to do semantic search, complex search, and utilize the latest, best-in-class graph-based machine learning. So 100%, I would definitely choose Dgraph again if I'm going to start another startup. So overall, what the benefits allow us to hand off the management of the database side of things to the Dgraph team, and that means that we can do what we're good at, which is focusing on building machine learning and a robust, scalable data architecture, so that we can help our customers connect better with the people that matter to them. So if you want to if you want to do some exploration on King, please jump on king.so and have a look at trying to connect with your customers. I'd really appreciate your feedback on how you think the app works, how it solves your problems, or what you think that you could use it for if you've got some interesting problems to solve. And generally your feedback around the usability of the UI. But otherwise, go ahead and grow your startups. Thank you very much for listening.
And that's a wrap. Thank you for joining us for Dgraph Day. I would like to thank all of our speakers who have so kindly shared their expertise and best practices with us. And a huge thank you to all of you for attending. If you want to continue the discussion, please head over to discuss.dgraph.io and keep the conversation going. Talk to you soon. Bye.